Okay, welcome everybody. Welcome to Germany, welcome to Mainz, and welcome to JuliaCon 2026. It's great to have you all here. And yeah, it's my pleasure to hold this opening ceremony. I want to hold it short because, you're mainly here for the main conference program. So let's get started. First of all, of course, thank you all for being here. It's great to have so many people here. Without you, JuliaCon wouldn't be possible, but also JuliaCon wouldn't be possible without all of our sponsors, and in particular also our local volunteers, the organizers, the finance chair, the program committee, and everybody else. So let's thank all of these people who made JuliaCon possible at all. Thank you. Then it's great to have you here. So you already know at least where this building is, and I see also a lot of badges, so you found some other building. We have campus plans like this one here, scattered around in the rooms. So for example here, this green room building is the one where you got your badges. We will also have coffee break in there. We will have a room, HS11, reserved if you just want to talk to people, and you can do so in that room. It's in the same building over here. We will also have 2 lecture halls over there, so after the keynote, people can go over there. Then we have a few keynotes over here. It's the building directly next to our tent here in this direction. There are 3 rooms, and 1 and 2 and 3 with a lot of talks. Then we have the big tent. All of the keynotes will be in here. And then if you follow along the same street and you walk over here, you go to the canteen where we will have lunch. So you have received these vouchers, the blue ones. You can get lunch over there at counter 3 and counter 4. And it's a menu, so you get a soup, and you get a main dish, and a salad, a dessert, and you can grab a bottle of water or something to drink like that. If you arrived already on Monday or even earlier, you may have missed the Julia stickers that we distribute there. So you can go back to the Alte Mensa, the green building where the registration desk is, and grab some stickers that you may want to have. Yeah, so here we are. Then there are some things that I would like to know or to tell you. First of all, Julia is a great software, and that's one part why we're all here. But the other important part is that the community is a great community. It's great to have so many people here. So please, let's continue this. Let's make it a welcoming and great experience for everybody. Adhere to our code of conduct, the JuliaCon code of conduct, the Julia community code of conduct, NIM focus, and so on and so forth. Then there's something else, the schedule. You're here, so you know about the schedule. There may have been some last-minute changes. So just in case, please check the schedule online. You can do so also using the JuliaCon.jl package, at least if you wait maybe a little bit until the package servers have been updated. Right now, you can add it only if you add it at the specific tag of it, but then it will also work, and it will tell you what you can see where and so on. Then a few additional things. We will have the conference picture. So you see we have a photographer around here for today, and we will also take a conference picture. It is happening this afternoon. It's at 5:30, and the conference picture will be taken over there at the building where the registration is. So there are a few stairs. Please be there 5:30 for the conference picture. Then a few additional special things on the agenda. We have a poster session happening tomorrow afternoon, tomorrow evening. It is after the last keynote, after the talks. So there's nothing in parallel to the poster session on Thursday. And we will also have some catering, some food, something to drink for all of this poster session. It's in the same building as the registration desk. During the conference, in the room next to the registration desk, we will also have some food like cakes and cookies and fruits and so on. So during the coffee breaks, you can go over there, find something to drink, find some coffee, and just chat to people and enjoy the conference. And then after the main part of the conference, the talks, on Saturday, we will also have another big part of it, the hackathon. So you can stay here. The hackathon will be mainly hosted in the same building as the registration. So it's everything over there. In one of the rooms, we will have chairs, we will have tables, so you can sit down and work together. And for catering, we don't have anything special for that. You just need to go out of the building, and if you go down the stairs on the right-hand side, there's a beer garden which will be opened where you can buy something to drink, something to eat during the hackathon. Then, yeah, photographer, I already told you about that. If you want to take some pictures on your own, for example, same building where the registration is, we have a photo wall in there, so you can take some photos there. Please feel free to share them. And yeah, I don't know, if you want to take a photo on your own, share it on LinkedIn or whatever, or share it with the organizers, share it on Slack, Zulip, so that we can also advertise JuliaCon better. And then JuliaCon will be streamed on YouTube, as we did in the last years. So the live streams include all the talks that we have, starting today until Friday. The live streams didn't include the workshops that we had yesterday and the day before, but everything that's going on now will be live streamed, and it will also be on YouTube visible for everybody around the world. And yeah, some sessions, like for example the BOFs, will not be live streamed, but all the talks and the main things will be there. So this also means for you, if there are questions in the audience, I mean here, if there are questions at the end, you can just raise your hand and then shout loud enough so that everybody here in the room at least understands your question, or at least the person standing in front of you can understand it. But for everybody giving a talk and answering them questions, because we want the online audience to also be able to understand the question, please first repeat the question and then answer it so that everybody understands what's going on, what was asked. And for live streams, well, we just mentioned questions. This means you must leave room for questions in your talk, right? So if you have a talk of 15 minutes, please reserve at least 3 minutes for the questions. If you have a longer talk for half an hour, please reserve at least 5 minutes for questions so that there can be some interaction, because interaction is why we are here, right? So otherwise you could just be on YouTube and watch it. We are here for the interaction, so please leave room for questions in your talks. The session chairs will also have some cards maybe to really show you, okay, 5 minutes left or 10 minutes left, and you must stop now. And please, really, if they show you the sign, stop now, then you really stop. Are there any last-minute questions from your side? Doesn't seem to be the case. Great, so thank you again. And now it's time for our first keynote speaker today. It's Simon Peter Jones. You can see him over there, and he will come up to the stage immediately. He's very well known in the computer science community, in particular for functional programming. And today I'm really excited to have him here to talk about Haskell, origins, evolution, and future. Thank you.
Thanks. How long timing is?
Timing is perfectly fine. So we have an hour including questions.
An hour including questions, good, yeah. Okay. All right. Good morning, JuliaCon! Whoa! I bring you greetings from your brothers and sisters in the land of Haskell. And I have come to dwell in the belly of the Julia beast. So I'm going to learn a lot about Julia in the next 48 hours. But I've been asked by the program committee to speak to you a bit about Haskell, which is a language that I helped design, and to tell you a bit about its, how it came to be, some of the human stories behind it, and where it's going, and what's important and interesting about it. So, as I'm speaking, it will be more fun for me if you ask questions as it went along. You know, I want to see your eyes, and I will keep an eye on you, and we can have quick questions for clarifications as we go. You don't need to save them up to the end. And that would reassure me that you are actually listening to me, okay? All right. So, I want to take you back a long way to 1976, 50 years ago. John Hughes and I went to Cambridge University to study mathematics. At that stage, 4 kilobytes was a lot of memory. The university had one computer that was a big time-sharing computer, which we used at night exclusively. John was a very good mathematician, had no problem with maths. I was a terrible mathematician, had great problems with maths, ended up doing electronics. At the time, we learnt about functional programming from a guy called Arthur Norman, who was a professor there. And we learned about bits about this weird idea about programming without assignment, which seemed completely bizarre to us at the time. And at that time, also, a guy called David Turner was writing papers about so-called SK combinators as a way of executing functional programs. I think I'm going to have more fun down here, if that's all right. And there was also a big buzz around lazy functional programming in the United States with Dan Friedman and David Wise. There was a big research group at MIT doing data flow architectures and something called the id language and the monsoon processor. There was a lot that was sort of in the air. So we inhaled deeply, and we were intoxicated. And then, as you remember, we were like 19 at the time, so it's easy to intoxicate 19-year-olds. At that time, then, John Backus, the guy who invented Fortran, or one of the guys who invented Fortran, got the ACM Turing Award, which is like the Nobel Prize for computer science. And his talk at his Turing Award lecture was this: can programming be liberated from the von Neumann style? And he was essentially advocating functional programming. The guy who invented this extremely imperative low-level language, Fortran, was saying, no, functional programming is the way of the future. Moreover, he said, we should design new computer architectures to execute those programs. Can you see how exciting that was? He was kind of, guys, let's reinvent programming and let's reinvent computers. So we became John Backus's prophets, and he was God, and we were his prophets in the wilderness. And he was saying, have no truck with the grubby compromises of imperative programming. Let's just transform the world with functional programming. So this is very exciting, very exciting. So what then happens? There was a lot of chaos, lots of research groups around the country. By this time, I'd left. I was working in a small company, though I came back to university in about 1984 or so. Lots of functional programming languages were designed, lots of bright young things in different research groups. There were new conferences. There was even a conference called Functional Programming and Computer Architecture. That was the title of the conference. Do you see how much we put in our minds together a new way of programming and a new way of building computers? That's pretty exciting. So it was all a bit chaotic and fun. So then a bunch of us met at FPCA in, when was it, 1987. And what we discovered is that we'd all been designing, we'd had our research groups and we'd design our own languages. And we thought, if only we could share a common language, then our different implementations or compilers could share this common language. That would be sensible, right? And at that stage, we thought there was a pretty good consensus about what that language should look like. It was embodied by languages like ML or Miranda and Sassel. So there was quite a bit parametric polymorphism, algebraic data types, that kind of thing. But the rallying cry was laziness. So we were the lazy guys. There was a bunch over here, there was a bunch of strict guys who were doing ML and Lisp and so forth, and we liked them, but we were excited about laziness. So Haskell was going to be a lazy language, freely available, really a laboratory for extending ideas. Right. So it took us, we thought it would take us about 2 weeks to design this language. It took 2.5 years. And then we produced the Haskell report. Okay. So this is, remember, 36 years ago. 36 years ago. So Haskell is kind of middle-aged. Julia, you guys, you're teenagers, right? So it's interesting to, so we're going to compare these languages a little bit. Another thing that happened to me at that time was I moved from UCL to Glasgow. Glasgow Computer Science Department at that time had John Hughes and Phil Wadler and Mary Sheeran, and astonishingly, they had me as well. I had no PhD. I had one published paper, but I got hired as a professor. Wasn't that amazing? It was at a time when there was a shortage of computer science faculty, so if you had a pulse, you could get hired, and apparently I had a pulse. So there was a pretty exciting time at Glasgow. It was a very fertile moment. This picture at the bottom, actually, is me. You can see me in the picture. This is like only 5 years ago when at an computing education event, because I'm quite involved in computing education. But anyway, Glasgow was very influential on me, and there was a particular moment at which these particular group of people came together, did a lot. Glasgow's not so much in functional programming. Also in 1990, very important to me, my son Michael was born. These are my 3 delightful birth children. I have 3 younger adopted children, but this is Megan, Michael, and Sarah. Michael, he was born in 1990, the same year as Haskell, and 36 years later, his professional job is programming in Haskell. I think that's the most deep compliment a son can pay to his father. I'm very touched by it. He works for a company called Circuit Hub. Okay, here is Haskell the cat. So even our cats were named after programming languages. This is Haskell, alas, now dead. But our new cat is called Scratch. Not, I'm sorry, Julia. That next cat, maybe. Current cat is called Scratch. Also Ginger. Now, when you design a programming language, it is a risky endeavor. What happens to most programming languages? They get one user, and they last a year or two. I mean, languages are easy to invent, right? Vertical access is time horizontal, a number of users vertical, okay? So what happens to successful academic languages? They get a few hundred users and die, but they just die more slowly, essentially. What happens to languages like C++ and Perl and Java and Ruby? They pass what I call here the threshold of immortality, at which they can no longer be allowed to die. So COBOL is here as well. Now, I guess I'm interested. I have not plotted this graph for Julia. I don't know what it would look like for Julia. This is committee languages. Now, Haskell, as you got it, was designed by a committee, a group of about 25 people. Committee languages tend to have no users ever. But this is what's happened to Haskell, right? So we've sort of grown slowly over time, a bit of a plateau at times, but I think gentle growth. And this is a very unusual trajectory. And also, it's a very long one. Remember, Haskell was born before Java. Right, probably most of you were born after Java. You just thought it came, with the atmosphere. No, Java's a little Johnny-come-lately. Right? Haskell's truly ancient. Julia is sort of somewhere on here as well. So this is what happens to programming languages. Now, I had a look at langpop.com, a sort of website that gathers, GitHub things and sees how many people are using what kind of programming languages. And here's the table from a few days ago. And interestingly enough, Haskell and Julia are on the chart, which is pretty amazing, right? So hence we're not dead yet. And B are adjacent to each other, so that's rather lovely, right? And C are at the bottom of the chart. So I think there's a lot to like here, actually. We sort of have a solid following, fairly niche-y. So what is similar about our languages? Well, it's very noticeable that both in the Julia community and in the Haskell community, there's a lot of passion and enthusiasm about. They're sort of mission-driven languages. I was talking to Viral and Valentin today, describing how in Julia you just want to get stuff done. But I read some of the earlier posts about Julia. What was this one? We're inexcusably greedy. We want to have it all, right? And so we just went off and designed Julia to do that. That's a mission-driven language. So our mission was take one idea, that of laziness, and explore it, right? So a bit of a different mission. Your mission was get stuff done. Our mission was let's have fun with laziness. But they sort of have come back together in a way. I've also put joyful here because one of the compliments that I most love when people tell me about Haskell is not that it's a very interesting type system, but I just love programming in Haskell. And I know that you guys love programming in Julia. It sort of makes you feel good about yourself to write code rather than just getting the job done. It's actually fun. And here, this is one fairly recent blog post, actually, from somebody who describes Haskell as making him think in a different way about the entire enterprise of programming. Yes?
Would you share for us your definition of laziness?
Oh, would I share my definition of laziness? I've got a whole section about that, yes. So we're going to talk a lot about laziness. Okay. Anything else at the moment? Another thing that we share in common is I think both of us lack a single controlling corporate sponsor. So controlling typically bad thing, right? So that gives us a lot of scope for anarchy and we can develop things the way we want. But on the other hand, we have no money. I'll come back to that at the end. That's a bit of a problem. Okay, so these are similarities between the languages. Here are differences. I don't know, this is just my little analysis based on a fairly superficial analysis. What have I done here? So Haskell was designed as a general purpose language, whereas Julia really came out of a particular application area, engineering and science applications, that is, and many of you here, I believe, are engineers and scientists primarily rather than computer scientists. Is that true? Hands up, engineers and scientists. Yes. See, look at that. Mostly. Wow, so you're very brave coming here to talk about Haskell. That's very good. So Haskell's a bit different, right? General purpose, no killer app. So one thing that's important about Haskell is I think of it as a laboratory in which to explore ideas. Whereas Julia's clearly gets stuff done. For Haskell, I work really hard. I spend hours and hours, days, weeks, years working on performance. But in the Haskell world, performance is nice. In Julia world, performance it's all about, that's what you have to have, right? That was the thing. We want to have all this expressiveness, but we must have performance. What's this? Oh, this was Valentin. I had a 45-minute conversation with him 2 weeks ago that turned into 2 hours. But one of the things he said that I wrote down was, in Haskell, you're trying to prove that despite static typing, we can still make programmers productive. So I don't really agree with that. I think static typing makes me productive, but nevertheless, this is Valentin's quote, right? Whereas in Haskell, despite the dynamic dispatch, we can still make it fast. So in both cases, we're trying to prove something. Haskell is remorselessly pure. We're going to talk quite a bit about purity and laziness. Whereas Julia is it has a strong functional encouragement, but is an imperative language. And type classes and multiple dispatch are different ways of thinking about the same kind of territory. We're going to talk a bit about that too. I also, you may be interested in this, I got Claude to help me count the lines of code in GHC, my compiler for Haskell, and in Julia. So GHC, remember, is 36 years old. The code base, it is the same code base that we started 36 years ago. It's now 300-odd thousand lines of Haskell code. And the Julia compiler is 100,000-odd lines of Julia and C++ code, something like that, yes? I've looked at the comments are interesting, right? We have lots of comments, long notes. So you can see the proportion of comments here is very different. The runtime system, it's actually surprisingly similar. GHC's runtime system is written in C. And there's a bit about runtimes, yes. So there you go. So it's just here, I should just say the compiler part, for the compiler part, I know it's a bit blurry, right? A lot happens at runtime in Julia, so I think we counted type checking as compiler. And doc strings count as comments. They count as comments, yes. Okay, good. That's just a little bit of, but we're in the same kind of territory. It's not 30 million lines of code, nor is it 3,000 lines of code like a single person. So clearly these have to be multi-person community projects that involve a lot of people. Okay, so far so good. Now I want to talk a little bit about what I think makes Haskell an interesting. I talked about it being a laboratory. What's the laboratory for? It's for exploring ideas. What ideas? So I'm going to talk a little bit about that. Anybody got any other questions so far? Try to look excited. Okay, so was that somebody? Yes. Many comments that what?
You showed us you have a high percentage of comments, but these are not just comments. It's easy to add many comments, right?
Yeah.
These are good comments in Haskell, that's my experience. How do you get that?
Oh, the question is, how do we make sure that the comments in the source code of the Haskell compiler are good comments? Well, so this is the cultural thing in part. So if you look at GHC source code, it's on GitHub, you'll see that search for note something. There's a standard form for these comments, because often you want to write a comment that isn't about one line of code, it's about the design of a little feature or something. So we write a note, underline it, and then you describe what's going on and the moving parts, and you point off to the code, and you can point back to the note. That's a sort of culturally embedded idea. And when anybody does code review, very often a comment will be, can you please write a note that describes the design of the fix that you have just put in? And so there's a sort of positive feedback loop. And then the reviewer will read that note first. And they will say, I didn't understand that. I'm not looking at any code until yeah. But a bit cultural, I suppose. Anyone else?
There's a question.
Oh, yes. Hello. What happened to Lisp? Oh, what happened to Lisp? So Lisp was definitely part of this, this nexus of excitement around, in the 1970s. And Lisp is alive and well today in various forms, particularly Scheme and Racket. There's a programming environment called Racket that is really Scheme. which has a lot of, it's probably got a community that's as big as Julia's community, maybe bigger. So Scheme is very much alive and well. Common Lisp is alive and well. I know less about it. So Lisp has continued to evolve. In some ways, it's the great granddaddy of things. Oh, I forgot to tell you about computer architectures. Back in the 70s, a company, another part of excitement was Symbolics was designing Lisp machines, actual hardware designed to execute Lisp. But as it turned out, all these exciting ideas that John Backus put in our heads about designing hardware to execute functional languages, execute SK combinators in hardware, bad idea. Bad idea. It turned out all we were doing was we were building hardware to interpret at runtime stuff that could be done at compile time. That's always bad, right? So it turned out that all these new architectures were doomed. x86 just won, partly because it's very difficult to compete with hundreds of billions of dollars being spent on very advanced silicon design, but partly, I think, because it's genuinely the case that you should do a lot of work at compile time that means you don't have to do work at runtime. Yeah. Okay? All right. What's good about Haskell? I've got 3 things. 1, keep faith with some deep, simple principles. 2, be a joyful laboratory. 3, this is sort of why it's still active. 3, that it's increasingly good. As time has evolved, Haskell's got better at getting stuff done. We have a kind of informal motto that says, avoid success at all costs, right? And that can bracket 2 ways. It can mean, like at this first one, avoid success at all costs. That is, do not compromise your deep, simple principles in order to get stuff done, right? But you can also bracket is, avoid success at all costs. And that's to do with not passing through the threshold of immortality so that you can no longer change your language because there's too much code written in it, right? The more successful you are, the harder it is to change. We're beginning to experience that. I don't know. You have to tell me later about whether you are. Let me see, I've got a few quotes. I think I'm going to skip these quotes over here. I rather like the idea. I can only conclude that Haskell is a mimetic virus, and monads are the eggs it lays in innocent programmers' minds to entice others to become infected. These are all sort of, nerdy enthusiasts. Okay, now, let's see. I think I'm going to skip this too, because I've said it more or less. Except to say that now this avoid success at all costs thing, we're not doing so well on that. Haskell has become more successful. And I'm pleased about that. But it has meant that I spent a lot more time thinking about backward compatibility than ever I did before. 20 years ago, I just add something to the compiler and say, suck it up. And in fact, and Haskell users did. We once released a version of GHC, and 3 weeks later, I got a message from somebody saying, did you know that on Windows, if you compile a module that's in a different directory than your current working directory, so you say ghc-c foo/bar.hs, then if there's a type error, GHC will print out the error and delete the source code. Bad programmer. I do not want to see that program again. You might think that the user would say, you guys are just a show. I hate you all. But no, he said, don't worry about it. I've just got a job that copies all the source code to a new place before I compile every time. So we had those kind of users. Sadly, those kind of users are no more. It turned out that every compiler has a kill list of temporary files that it deletes, and somehow the source code had ended up on the kill list. So it's a little bit sad, a little bit embarrassing, but it was quite funny. Okay, now, I talked about deep, simple principles. Let me tell you what I think they are. Number 1, a tiny core language. Number 2, purity and laziness. Number 3, types. Okay, so let's talk about those 3 in turn. Tiny core language, what do I mean? Haskell is a very large language. If you look at its abstract syntax tree, it has dozens of data types, each of which has dozens of constructors. That is a big language. But what happens inside GHC is that entire big language gets compiled to a really, really small language called systemfc. And systemfc is a statically typed language. Now, here it is. This is the data type taken from the source code of the compiler today, into which every Haskell program is compiled. Look at this. Expressions have just these, how many is it? 6, 7, 8, 9, 10 constructors. That's all. That's a really small data type. And moreover, this language is statically typed. I think GHC is, as far as I know, the only compiler in the world that maintains a static type system right the way through the optimization pipeline, right up to the back end. So it means that, of course, it doesn't need to be statically typed, because if the compiler is correct, then if it's correctly typed at the beginning, it'll be correctly typed at the end, right? But is the compiler always correct? Alas, no. So this is a very powerful check on the compiler. Instead of waiting until your program says segfault, you get pass 3, produce the type incorrect program. That's fantastically helpful, fantastically helpful. Okay, let's see. Now, I want to introduce you to Phil Wadler, who's my colleague at Glasgow. He's a functional programming guy. And when we were thinking about this intermediate language thing, I was describing to Phil various obstacles that I was encountering. And Phil said, Simon, you should just use System F. Now, I can't tell you, System F is a type theory, logic and semantics kind of language. It's a slightly grown-up version of the lambda calculus. In fact, here it is, right at the top of this slide. An expression is a variable, a constant, a type, an application, or a lambda. Or it can be a big lambda, which can abstract over types. Pretty small language, invented independently. Curiously, System F was invented quite separately by 2 giant-brained people, John Reynolds on the left and Jean-Yves Girard on the right. And here are their papers that describe System F. But it was very much programming language, semantics, theory, pointy-headed people. But Phil was saying, Simon, you should just use this as the intermediate language for a compiler. I thought he was smoking something. But it turned out it was exactly right. So I'm not going to have time to describe the details, but I love the way that what seemed like a very theoretical concept turned into an actual, practical, still 36 years later, directly in use every day, language into which every Haskell program is compiled. Pretty amazing. So here's the sort of compilation pipeline. So lots happens. You know, we rename, we type check, we optimize the loop with the blue box there. That's the little optimization pipeline. We run around doing lots of transformations, some of which are listed on the right. And all of them go from this language to the same language, to the same language, to the same language, statically typed all the way. And you can see the output of the compiler at each stage. Okay, lovely, lovely. So that's a small language. Very, very helpful structuring mechanism. Also good sanity check. If you want to add an extension to the source language, if that would require a change to the intermediate language, that would be a big deal. If it can be desugared into the intermediate language, that suggests that all you're doing is adding syntactic sugar, which is much less of a big deal. Do you see the point, right? So it's kind of like a sanity check that tells us if an extension is a big one or a small one. And, by the way, this language has not changed for the last 15 years, and it only changed once for the previous, it's really only changed once in 30 years. It's very, very, very stable. Okay, so much for that. Now, laziness. This is your question, right? So remember that laziness was our war cry, right? We were the guys, 22 to 25-year-olds who just thought laziness was the coolest thing since sliced bread. And John Hughes wrote our manifesto. He didn't think of it. It was a little internal working note, but it's become very famous. And if you haven't read it, it's worth reading. Why Functional Programming Matters. But it should really be called Why Lazy Functional Programming Matters. So he articulated in a very eloquent way how laziness can form a very powerful glue. It's not just a convenient mechanism. It enables you to modularize your programs in ways that are hard to do otherwise. So it's a very good manifesto. So it was sort of part of what inspired us to do, whoa, let's go off and make laziness happen. Now, but of course, laziness is all, what does laziness mean? So you asked me to define it. So when I call a function, f applied to g of x. Now, in Julia, you'd evaluate g of x and pass the result to f, yeah? In Haskell, we'll build a suspension for g of x and pass a pointer to that suspension to f. If f throws it away, then g of x will never get computed. If f needs it, it will evaluate it just once and overwrite the suspension with the value. Sometimes the suspensions are called thunks, right? So they're a little heap-allocated cell that says, if you ever need my value, here's how to compute it. But if you don't need my value, that's fine, just throw me away, right? That's why it's called laziness, because it says, oh, I don't want to do any work until I'm absolutely forced to. That's the idea, okay? Now, the trouble is that it's expensive, right? Instead of calling g of x, I have to heap allocate something right into memory, and later, when f does want to evaluate that suspension, he's got to go read, and then execute code to evaluate it, and then write to put its value back. Lots of memory traffic, bad. Okay, so laziness is expensive. So why did we stick to laziness? Why did we wear the hair shirt of laziness? Well, as I say, that was our rallying cry to begin with, but it forced us into something that only later we realized was important, which is this paper by Pat Helland. He put it best. This is the best paper title I have ever seen. Immutability changes everything. Isn't that a lovely title? A beautiful play on words? And what he's really saying is that not just in programming language, but also in log-structured file systems and in accountancy, all over the place, caching systems, wherever you look, you'll find that people are sort of, instead of overwriting things, are sort of making a new copy and swinging pointers. Right? So this paper is about looking broadly across computer systems and seeing the effect of immutability. But I like his subtitle, We Need It, We Can Afford It, and the Time Is Now. So we can afford it means it does cost you something, but it's worth it. Right? The prices, and that was the line that we were pursuing, right? So that was our plan. Immutability changes everything. So once you committed to laziness, and really we were ideologically committed to laziness, to be honest with you, right? That was just our rallying cry. Then you have to be pure. If you're in a call-by-value language, it is almost impossible to resist the ability to just say print X in the middle of a function, right? Or open the valve, or put this thing in the database, right? Do things with side effects. So, but in Haskell, because it's lazy, that makes no sense. Look at this example. F of print yes, and that's F applied to two arguments, print yes and print no. What does that do? Does it print yes and then no? Or does it print no and then yes? Or does it print yes but not no? Or no but not yes, or neither? It depends on what F does with its arguments. And it's even worse if you put them in a list and then pass it around, right? So really, laziness and unrestricted side effects are incompatible. See the point? And so that effectively forced us to stay pure. Do you know, the first version of Haskell could not do I/O. The entire program had type string to string, and that was it. That was the whole thing. This is the joy of being an academic language. You can do silly things like that. Whereas you guys, to get this stuff done, you couldn't have done that, right? We could string to string. So there was a long period of about, I suppose, 5, 6, 7 years, in which it was just a bit embarrassing. We had this cool language, but we couldn't do any I/O, really, to speak of. Or we only had inconvenient ways of doing I/O. And then Phil Wadler appeared again. Oh, beg your pardon, sorry. I just want to divert into... Some of you may have seen this little meme on the top left-hand corner. If you look for Haskell and my name, this very often comes up. I don't know why it's so popular. It says Haskell is useless. Right, it was a little 5-minute conversation in the corridor that somebody videoed. But the idea that I wrote a little diagram in which this axis was dangerous and safe languages. So I was saying Haskell is very safe, right? But a vertical axis is useful and useless. But Haskell wasn't very useful because you didn't have any side effects. So it was safe but useless, right? On the other hand, C was very dangerous but very useful. And so what we want is languages that are both safe and useful. And Haskell is converging on that nirvana from below, and other programming languages, we might wonder about where Julia lives on this picture, are converging in a different direction. So, and there's cross-fertilization between these, right? I learned about STM from the imperative world, actually, but it worked out rather well in Haskell, as we might see. Okay, so now back to Phil Wadler. So Phil, the same Phil, then wrote this paper, Comprehending Monads. Have you ever heard of that paper? It's a very nice, easy-to-read paper, bath time reading. This is not a technical paper. And he took some ideas from a different giant called Eugenio Moggi, who's an Italian logician and computer scientist with very, very small round glasses, completely incomprehensible. Phil read his papers. Phil could understand them, and he translated them into English. Well, Moji wrote in English as well, but maths, really. Phil translated them into this paper, Comprehending Monads, that explained how to use the idea of a monad, which Eugenio had been developing in collaboration with other logicians, and use it as a practical programming paradigm. And he discovered that the option type, the maybe type, and lists were all monads. And then he and I, subsequently, a couple of years later, realized that I/O was also a monad, right? And so that led to this program, this paper, Imperative Functional Programming, whose slogan is Haskell, the world's finest imperative programming language. So very briefly, here's the idea. How are we doing for time? 9:14, good. Okay, halfway through, yes. So the idea is, very quick introduction to monads. In a Haskell program, an expression of type IoT should be thought of as a sort of action, or if you like, something like a shell script. A shell script is a piece of text, right, which you can execute. A value of type IoT is a bit like a shell script. It's a something which is a value you can pass around or store in a data structure, just as you could store the characters of a shell script. So it's a thing that you can pass around, but you can execute it, which is a separate step, right? So a value of type IoT, first-class value you can pass around, and when you execute it, it does some arbitrary input-output and returns a value of type T. So the function toUpper, which uppercase this thing, is a pure function. It takes a character and delivers a character. But the function getChar is a parameterless function that is an I/O action that, when performed, will do some I/O and get a character from the terminal. PutChar is a function that takes a character and produces one of these I/O actions, which, when run, will spit that character out on the screen. Does that make sense? It's important to get the distinction between actions and performing them. Then, and the main program, of course, is just one big action. Now, we've got to string our actions together. How can we string them together? How can we get a character and then put it? Well, we can string them together with this top thing here, the angle equals, which is actually so important. It's become Haskell's sort of, what are they called? Logo, brand, icon, something. It's called bind, and this type was written by Eugenio Moji, so we took it straight from him, right? So it's taken an action an I/O action that delivers a value of type A, and a function that, given a value of type A, produces an I/O action that produces something of type B. Glue them together to make a single big compound action that produces something of type B. So here's a little program: get a character. The second argument is a function, hence that lambda. That \A is a lambda. That's the function argument. And then we'd get another character and put it and then return AB, okay? So, and then Mark Jones, this fellow, was also on the Haskell committee. He invented do notation, which said, this is purely syntactic sugar, that said, I want to write the stuff on the left instead of the stuff on the right instead of the stuff on the left. So this do open curly braces and semicolons. Ooh, that looks like C. Oh, C programmers are going to love this. So it looks like imperative programming, but it's just syntactic sugar for the bind notation. And in fact, you can use the same notation for any monad, not just I/O. Okay. So this is very, very, very successful. The other thing to say, I said I/O actions are first-class values. It's very important in Haskell that as first-class values, you can pass them to functions, you can return them as results, you can store them in data structures. Here are a couple of examples. Forever takes an action of type I/O unit and performs it in an infinite loop forever. So the forever function is a perfectly ordinary function. It's not a language construct. It's not a built-in looping mechanism. It's just a function. In fact, I've given you the code for the function right here. And repeat n is a for loop that says repeat this n times, right? So suddenly, it's like I can design my control structures as ordinary functions. They're not built into the language. They're just a library. That's very powerful. Okay. Right. A little bit about concurrency. Very quickly, because I want to say a little bit about STM. So once we've got I/O, we can then do, of course, we can read and write things, but we could also spawn concurrent threads. So this guy here is, spawning a concurrent thread to do something in parallel. So that's fairly straightforward. The trouble is that then the threads can interact with each other badly. So what do you want to do? You want some mechanism of synchronizing concurrent threads. And I learned from a talk about Java, transactional memory in Java, about software transactional memory. And with Tim Harris, we realized that we could instead of writing a program like this, what does this program do? It forks a thread that calls addr. What does addr do? It adds one to the mutable cell. Remember, this is in the IO monad now, so we do have mutable cells now, but they are clumsy. Look at the type signatures at the top. We can new ref takes a value of type A and produces, and side-effectingly produces a mutable cell containing a value of type A. Read ref takes a ref cell, a pointer to a ref cell, and side-effectly reads it. Similarly, write. So you can read and write, but it's clumsy, right? There's a tax for mutability, which you have to do all this do notation. Right, so now I can make two threads that both mutate the single reference R, but of course, they're reading it and writing it, and they might do in any order. So what do? Locks and locks and things? No, no, no. We use transactional memory. Here, we're going to say atomically, look at the atomic word here, and this is a built-in function that wakes up the STM, and it says, run the effects of the thing enclosed in the atomic brackets, and do those like a transaction. So either it happens completely or not at all. So now that addr thing that does the read and the write will happen atomically, right? That's beautiful. So it's a very nice way. It's much easier way to program concurrent programs that are modifying mutable structures. It's fantastic. But, bringing STM from Java into Haskell allowed us to invent two new ways to make these things compose, namely blocking and or else. And here's the paper about it, which you might enjoy. So this is more like an advertisement for something that worked really, really well in Haskell. But I want to say a little bit about why, right? The type system guarantees things. So it guarantees that you cannot modify a mutable variable outside of a transaction. That would be bad, right? The type system prevents you doing that. The type system also allows you to compose little transactions into big ones. That is very good. Interestingly then, the rest of the world, after a 10-year love affair with STM between about 2000 and 2010, the rest of the world has abandoned transactional memory. Why? Because it's too expensive. But in Haskell, it's great because you only pay the cost when you're mutating things. But in Haskell, we're already making you pay a heavy tax. You have to write read, ref, mumble to read. So we do very, very few mutable operations. So Haskell programmers are already trained to do very little mutation. So if there's side effects if there's cost to doing mutation, the cost is paid on very few operations, and so it's perfectly tolerable. So STM is alive and well in Haskell. It comes in the box when you download and run GAT. It's just fantastic. You might enjoy this blog post by Joe Duffy that explains the sad end of STM in the mainstream. But I just want to say it's rather ironic that a technology that was to do with imperative stuff, concurrency and side effects, has come to its most full blossoming in a purely functional language. Don't you think that's rather remarkable? And has been abandoned by the imperative mainstream. Okay. Right. I think I could skip quickly on. Yes. But I do just want to mention here that going back to this question, we thought that our war cry was laziness, but it turned out we were wrong. Our war cry was really purity. Right? Laziness is kind of optional. If you're designing today, if I was doing it again, I might design a strict functional language, which is pure. It's controlling those side effects that's the big thing that Haskell has given to the world, not so much the laziness. Nevertheless, the laziness was what drove us there. But we realized that it was a scaffolding that we could do without. Okay. All right. Anything else? Yes.
So, in theory, one could implement a Haskell-like language that is eager and always just eagerly evaluates, of course, with purity and making copies.
Yeah, in theory, could you have a Haskell-like language that was call by value, yes, but pure? Absolutely, yes. Indeed, with GHC, if you say -x strict, you get that language, right? So you can give a flag to the compiler that says just evaluate everything strictly anyway.
And that's just like a performance trade-off?
It's a performance trade-off. Well, it's an expressiveness trade-off as well, yes. Yeah. So, in fact, every strict language has some forms of laziness, like iterators are a form of laziness, right? And every lazy language has some form of strictness. Haskell has gone quite a long way with that, right? I don't know any language that truly allows both in a totally fluid way. It's very difficult to get a good point in that design space. Yeah. Sorry, loudly, please.
Was there interest in using some of Intel's transactional memory stuff with all of this?
Oh, right, yes, you mean the transactional memory story was so exciting that Intel designed hardware to execute. It was called HTM, hardware transactional memory. Went nowhere. So I think we could use HTM probably to implement GHC's STM, but I'm not sure anybody put the engineering effort in to do so.
You don't.
We don't, no. But some of you could. It's an open source project, yeah.
And one small note about the laziness, it might be useful not only for performance, it's also really important in distributed processing. For example, a system called Spark,
Yeah.
it's doing distributed processing on big clusters, and it's basically lazy functional language of distributed. And if you lost a node, it can be just recomputed because it's pure
Right.
functional thing.
Oh. Yeah, so what my colleague here is saying is just that big distributed systems like Spark, if you look at them in the right way, they're really just doing lazy functional programming. Is that a way of summarizing what you just said? Yeah. So, yeah.
How is this different from imperative programming languages that construct a big graph of calculations for lazy evaluation?
How is it different? Just ask the question again.
So in most imperative programming languages, you can still construct like a graph of deferred computations, like
Oh,
that.
I see. You could program laziness in an imperative language, right? But there's an extra layer of bureaucracy to do that. It makes the program, if anything, harder to understand. It might be important for performance. So, yeah, of course, in C you can do anything, right? You could write a Haskell compiler. Yeah. Okay. So, how are we doing? We have, okay, 20 minutes. I want to say a little bit about types before we finish. In fact, quite a lot about types. Look, so Haskell is a statically typed language, and this is a point of difference with Julia. So I want to give you a little bit of a sense for what that means. So our starting point was the language called ML that had this idea of parametric polymorphism, that reverse was a function that didn't just take a list of integers and produce a list of integers, or that took a list of characters and produced a list of characters. Reverse had type for all types A, list of A to list of A. That's called parametric polymorphism. It's called generics in other things. I'm sure Julia has something like it. So, and ML also had type inference, which Haskell has too, and it had algebraic data types. So this was part of what we started from. Okay, but a problem that we rapidly got stuck on is that there are quite a few functions where they cannot be polymorphic, right? So things like printing or serialization or sorting. If you're going to sort, you've got to compare things. What did ML do? ML compromised. They said, oh, built into the runtime system will give you some kind of built-in equality or built-in ordering, right? But it was very, then you soon before long you want hashing or something else, and then you're out of luck. So there was no good solution at that time, no good solution. So there was this tension between parametric polymorphism and wanting to get stuff done, honestly, in a beautiful way. And then, Phil Wadler reappeared. Astonishingly, Phil is really responsible for some of the most fundamental ideas in Haskell. He and his student, Stu Blott, came out with this paper, How to Make Ad Hoc Polymorphism Less Ad Hoc, that described Haskell's type classes. So at that stage, the Haskell committee was wrestling with this problem, the one I've just described. And then Phil produced this paper completely out of the blue, and we sort of fell on it and said, that is the way to do it. Now, here's the idea very quickly. Instead of square having type for all A to A, which isn't true because square will work on floats and it'll work on integers, but it won't work on functions, right? Instead, we say square says for all A such that num A has A to A, right? For all A's that lie in the class num. So you could think of it as bounded parametric polymorphism. A doesn't range over every type, just over every type that is an instance of this strange thing called the num class, right? And then we can do the same thing for other things, sorting and serialization and membership and so forth. So, simple idea, but now, so what are these classes? Classes in Haskell is really more like an interface in an object-oriented language. So it just defines the signatures of the operations the class does. So for the num class, the operations, things like plus and multiplication, here they are, okay? And then to make a type into an instance of the class, we say instance num int, and then we give an implementation of plus for int and an implementation of star. So to make a new type or an existing type into an instance of a class, you just give a declaration that witnesses each of these methods, okay? Now, what was really cool about what Phil described is it came with an implementation technology as well, and here it is. Every one of those bounds, things like num_a, turns into, it looks like part of the type system, turns into a runtime argument. Let me say it again. Every type class constraint in the type becomes a runtime argument that's passed at runtime. And what's in that argument? It's a little vector of methods. It's like the v-table for an object. So in Haskell, the v-tables travel separately. They're called dictionaries. It's just a little vector of methods. So here in the blue is what gets translated. So the square, in the source code, it looks like square x is x times x. But in the intermediate language, in that system FC I was showing you, it looks like square takes two parameters, a d, whose type is num_a, and the x. And how does it run? It uses the what's that multiply in the blue? The multiply in the blue is just a selector. It says take the third field of the d. The d is a little tuple of methods. Pick the third field out and apply that to x and x. Yeah? Very loudly, you have to shout.
Would this work for squaring a matrix?
Would this work for squaring a matrix? Absolutely. Yes. So all you have to do is to make matrix into an instance of num. So going back here, I would have to say instance num matrix, and then the code that I would give would be the code for multiplying matrices. So absolutely yes. So it is very much not to do with built-in types. And then corresponding to the class, we get a little data type declaration that says the implementation of a class is a little record containing methods, that is, higher order functions that implement the code, the matrix multiply code, would live in that record. Okay? So it's very, very simple. Yes, question back here. Valentin, can you give me the microphone? Thank you.
Thank you. This looks to me a bit like type erasure, or you might call it in Java or so, because you make this type into a runtime value. But in the beginning, you said that you have this static typing throughout. So it seems like a contradiction.
Okay, so we still have erasure. We still have erasure going on. Right, so in this little intermediate language, I haven't been quite truthful with you. In the intermediate language, square actually takes three arguments, a type and a dictionary and an x. But in the compiled code, when you finally run it, it only takes two. So the types are erased, but the dictionaries are not erased. So, so for overloaded types, if you've got a num_a double arrow, that's going to be passed at runtime, unless we... What might we do? We might specialize, yes. Right, so if you see square called at type int in a lot of places, you could say, maybe I could compile a special, some specialized code for square that works just on ints. And then I don't need to pass the v-table to that because I know it's going to be the v-table for ints, right? So Haskell does specialization, well, my compiler for Haskell does specialization like crazy, just like you do. Lots of specialization going on. Okay, so where are we? Right, now, so far, num_a, I've just shown you single parameter type classes, but it wasn't long before we invented multi-parameter type classes. Here is binum, which actually has three type parameters and says that if you know the first two, then you know the third one. And then you can add up, three, you can have int plus int produces an int, or the bottom line says, if I add an int and a float, I'm going to get a float. So we can have multi-parameter type classes. And these are very like multi-method dispatch. So multi-parameter type classes and multi-method dispatch, they're addressing exactly the same territory in slightly different ways. And I would love to talk to some of you while I'm here about how those different ways play out. I've made my best guess as a little table for how these two approaches to overloading and specialization take place. So they're both really powerful, right? So I put Julia multi-method, super powerful, and Haskell, super powerful, one super, right? So I think because you do a lot of stuff at runtime, and we do all our specialization at compile time, so I think you're probably even more power. So, so all of our specialization is static, yours is dynamic, right? Lots of opportunities to specialize. Oh, I've learned from Valenta now, I was a little bit horrified. He looked slightly ashamed, but nevertheless, it's the way things go, isn't it? That when you, exactly what will happen in Julia depends on the order in which you load your modules or something like that, because anyway, you can tell me afterwards about how wrong I am. So in Haskell, it's not order dependent, but it's still a source of there's some mild embarrassment about there, but it is complicated when you've got overlapping instances. It's quite complicated. I read this paper about, what's it called? Julia subtyping, a rational reconstruction. At least I attempted to read the paper. This is a quote from it. It's quite complicated, right? Quite complicated. Well, Haskell is pretty complicated too, in type classes, but I think maybe a bit less, I don't know. But they're quite different in their formal presentation. You have really amazing types like transpose of array. We don't have that at all. I think we could, but I don't think anybody's tried it. So you've gone a lot further in developing interesting types for what you might call views of arrays, where if you transpose an array, you don't actually transpose it, you just change the type, is that right? So that you don't actually do any data shuffling?
Yeah, and the index operation.
Yeah, just change the indexing way, right? Yeah. So there's a lot of that kind of work going on in Haskell, but I think your take on it is different. And one thing I just want to say, in Julia, you can't overload on the result type. And with type classes, you can, and that is really important. I do think, I want to spend a moment on that. So here, in the num class, there's this method from integer, whose type is integer arrow a. Notice that the a is in the result. There is no argument of type a. Ooh. And when you write this function double, with type double of x is x times 2, now, what is happening here? What is this 2? What is this 2? Well, we really want it to be a 2 of the same type as x. But what type does 2 have? Well, the 2 desugars to from integer 2. So what the type checker sees is x times from integer of 2, right? And now we can overload from integer's result type must be the same as x's type. That tells us which from integer to call. So the final code we get is double takes a dictionary D, and from integer picks one method from D and applies that to 2, the integer 2, and then multiply picks the multiply method from D. Do you get the idea? So being able to overload on the result type is really quite a big deal for writing modular programs in this way. Quite. And so to answer your question about matrices, you'd have a matrix, you'd have from integer for matrix. I don't know what the matrix 2 would be, a diagonal matrix or 2's everywhere. You'd have to decide, but it would, you're overloading all your constants. So that, I think, is quite a big value, and I think that is a difference. Right, so I'm going to skip this. So type classes, you know, we developed this for this quite narrow purpose, right? Just dealing with plus, and also numerics, and sorting, and serialization, and hashing maybe. But it's turned out they've been extraordinarily fertile. We've got multi-parameter type classes, and I think I've got a little picture here of all sorts of extensions of type classes. It turned out to be a seed that grew into a fairly mighty tree and has infected many other languages. Many other languages now have type classes in them. Okay. Let me just say that one other thing that is really useful in Haskell, really useful, and surprisingly little appears in other languages, is the idea here. This is, do you remember I was talking about monads and return and bind? Now look at this class declaration, class monad M. So that's saying that the types M lie in the class monad if they have a return operation and a bind operation. And look at the signature of return and bind. That has M applied to A in it. Right? So that means that M must be not a type, but a type constructor, like list or tree or IO. So now we've got type variables that range over not just types, but over type constructors. That is a big deal. That single innovation allowed us to take the whole idea of monads and marry it together with the whole idea of type classes to make overloadable monads, which has been huge, huge. I don't know why this idea is not more widely emulated. It's very, very powerful. It means you need a kind system as well. Okay, enough on that. Before finishing, I just want to mention that, yes, I've just talked about type classes, but in fact, Haskell has turned out to be a laboratory in which all sorts of type system innovations can be explored. So we've done a lot of developing of crazy type system ideas. It served very well as a laboratory. I don't want to say that it's necessarily better than anything else, but I'd be very happy to debate this with you over coffee. But I do want to say that it's been a really good lab, right, in which you can see what happens if you take the idea of static typing and really push it. Higher kind of type variables, polymorphic functions as function arguments, existentials, generalized algebraic data types, on and on, on and on. Lots of stuff, type level functions. So it's been very, very rich, I suppose. Okay, yeah, Vima.
Quick question. So, a lot of the people here sort of would understand, how Julia works with complex numbers and imaginary numbers. And I was just curious if you could, say a little bit about how Haskell deals with it.
How would Haskell deal with complex or imaginary numbers?
Yes, like if you have square root of -1 versus square root of 4, they are different return types.
Yeah. Oh, so Haskell would deal with complex numbers very straightforwardly back to over here, just as a library. So we just define a data type of complex numbers, perhaps in rectangular form or polar form, whatever you like. You define a library of operations that work only over those, and then you make complex an instance of the class num. You say class an instance num of complex, where pluses add complex, minuses subtract complex, and suddenly every function that worked, like this double function, would then immediately work for complex numbers with no modification, and it could be specialized for complex numbers. So I think really just as in Julia, the idea is you can write generic code once, like this double function, and use it at all sorts of new types, including types that have not yet been thought of. Yeah, and complex numbers is a good example. Matrices are another, but people have all sorts of crazy types that they do in all sorts of, yeah.
So with all this stuff going on with these algebraic data types and everything, right? I know that everyone uses the word safe that comes out of Haskell for this, right? I wonder if, I come from a different kind of world where I say, a lot of what's going on is floating point calculations. And so for me, a calculation, I can proving correctness of a calculation has to do with, proving if I have, floating point accuracy.
Yeah.
And this doesn't touch floating point accuracy. I wonder if what you think about, like, how over time, like, the words, Haskell is a safe language here, whether that's, like, evolved or kind of needs some, like, added words to it or something?
So the question is about what does safe really mean. So it has a very precise meaning in static type systems. It means the slogan is, well-typed programs don't go wrong. Now, what does going wrong mean? It means things like, it mainly means memory safety, right? I'll never dereference a pointer that's not pointing to anything, and I will never add an integer to a character, or I'll never take the square root of a Boolean. So there's a certain class of errors that are provably cannot take place, right? But you might still take the head of an empty list, right? Really, the type system is not going to prevent you you might have a type of non-empty lists, but they might be less convenient to program with for some reason. So in many Haskell programs, you'll see some pattern matching that has a case that says this can't happen, and that will end up in a runtime failure, right? Not a seg fault, but nevertheless a runtime failure. And you were talking about floating point errors in which your calculation doesn't converge, or you've lost precision in some way, and it's going to give you no help at all with that. So you have to be, I agree, you have to start to be precise about what you mean by safe. It definitely does not mean, I think it's the same true when people talk about verified programs. You never mean It's definitely right, because verified always means verified with respect to some spec that might be wrong, right? So we need your work just as much as we ever did, but we want a language, and I'm sure Julia and Haskell are both striving to do this, to be languages in which you can express, once you've figured out how to do your floating point calculation in a way that is, what shall I say, safe in a floating pointy way, since I lack the vocabulary, then you'd like to build libraries that make it impossible for you to write programs that are not safe in a floating pointy way, right? Are our languages expressive enough to do that? You're probably further ahead on Julia than we are on Haskell, but I'd love to talk to you about it. Yeah.
And how does what do you think about the composition of like laziness with safety when considering issues such as floating point? Like how does Haskell try to make sure that it doesn't because for example changing from x plus y plus z to x plus z plus y can change floating point answers even if it's
Oh wait. So you're saying does laziness and this kind of floating point safety interact? Answer no. Right. So laziness means that you might not evaluate something. It will not change it will never reassociate addition. It'll do the same operations in the same order, but it might omit some of them altogether if they're not needed. So if they don't contribute to the result, we won't do them, but we'll always do them in the exact same order. So they don't really interact at all. Yeah, we've got to finish. So, but nevertheless, we'll just stop. I'll ask questions. Yes.
I have a question which is not related to Haskell, but related to Epic. How do you use...
You want to talk about Epic? Yeah.
How do you use Haskell in Epic? It's a game engine company.
Yeah, okay. So I'm going to be talking about Verse, which is the programming language that Epic's designing. I'm talking about that at 12:30 today, yeah? And here, so you can hear about Verse then. But the answer to your question is, we're using Haskell as the language in which to write the Verse implementation, the prototype, the research prototypes of Verse. That's a short story. Okay, so we've got to finish. Let's see. How are we doing? 9:45. Yes, so I'm going to go to my go on. Right. I'm not going to talk about any of this. Oh, I do want to talk one thing. Yes. One thing I would like to talk to some of you about, right? So I'm sure you are grappling with the same thing. Increasingly, as I was saying, we have the problems of success. People are using Haskell, and then they become, cross if it doesn't work for them, or if we release a compiler with bugs in it. And they rely on a big ecosystem, Haskell language server and library infrastructure and so forth. So they rely on this stuff, but they do not want to pay for it. Now, the individuals all do want to pay for it, and they realize that it's in the interest of their companies to pay for it because they are actually relying every day on this infrastructure working, but they can't persuade their chief financial officer because he or she says, well, it's free, isn't it? I'm sure you have this problem with Julia too. So we're struggling with this a bit. The Haskell Foundation is you have an equivalent to, is meant to sort of glue together all of these things into. But I feel as if before I retire, I want to figure out how to solve the tragedy of the commons for the open source ecosystem. So talk to me about that. I'm here for the next couple of days. So I think I will just finish with this, just to say that I'd love to. I'm going to be here tomorrow and the next day, all of today, all of tomorrow, but not Friday. And I'd love to talk to you about any of the things on here, about anything else that you'd like to talk about. Are there any other sort of questions or observations? Yeah.
Just an idea that I've been floating to start discussions. Open source service contracts from funding agencies. So where everybody who gets a grant from a funding agency can allocate 3% of the grant funds to...
That would be great, yeah. So when you get grants from funding agencies, you should be able to put in a budget line for supporting open source, yes. But I would love companies too, when they're consultancies, when they're offering to do a job for somebody, they're going to say, well, it's going to cost us this for Amazon Web Services. They say, it's going to cost us this for the Haskell ecosystem. That would be nice too. I don't know how to make that work. Yep, anybody else? Okay, good. Let's have one, but I'm conscious that it is, we have to stop, right? So let's have one. Yeah. Oh, lean, yes. So what about lean? Well, so Lean is a language in which you can, it's a functional language, right? And it's a language which is optimized for writing proofs, developing proofs, and to do formal reasoning. So, and many of the Lean people are hardcore Haskell guys, right? So there's a lot of, cross-fertilization that's taking place. So I don't think the Lean people, Lean is busy. One of Lean's big war cries is, let's formalize all of mathematics. And there's a really serious academic project to formalize large bodies of mathematics in Lean. But I don't think yet anybody is using Lean to, I don't know, fly aircraft or even do database transactions. So at the moment, I would think of it's not yet a language for what you might call industrial applications. But it might, who knows, it might go that way. Might go that way. But there's a lot of engineering in these things, and their engineering is largely about proof, and everything takes effort. So, yeah, now you're in control, right? I'm just going to go on until you've stopped them. Oh, sorry, louder, please.
No more questions. We need to disperse.
Okay, no more questions. Fine, good. Okay, thank you very much. Yeah, good.
Great, thank you very much. And now it's time for everybody to either stay here for the one track here, go to the next building over there for the tracks N1, N2, and 3, or go to the building for the registration desk where we have the other remaining tracks. Enjoy the conference, and thank you very much.
Good morning, everyone. Can I ask everyone to have a seat while we finish setting up here so we can get started on time?
Hello. I'm Gabriel. Welcome to Optimizing the Optimizing Compiler. Kind of big shoes to fulfill after such a good talk by Simon, but I'll do my best. So we're going to talk about a little bit compiler latency and precompilation time, and I think that's a pretty common thing that people have always say in Julia. So I think most people have seen this comic about what are you doing? Get back to work. Oh, I'm compiling. And it was, okay, So it's like, it is a pretty common experience, especially as a base developer, where you compile Julia potentially several times a day. It just, like, you kind of want to have multiple things going on at the same time just so you can have something to do while Julia is compiling. So what can we do about that? And yeah, also, who cares about it? Apparently, most people. It's been the #1 asked thing in all their developer surveys since, I think, at least 2019. There's 1 or 2 years where static compilation was above it. And go to the Julia C talk if you want to hear more about that. But it's been a frustrating issue, I think, for most of you and for myself as well. And we've gotten better. If you remember, pre-1.9 days, we didn't even cache native code at all in package images. So we've gotten really good at caching code, but not particularly better at actually compiling it, which causes the frustrating thing of instantiating an environment taking very long, even if when it's actually done, using Julia is pretty snappy. And well, why is that? Why does it take so long to compile? Well, compiling Julia is kind of tricky. We have several steps I think people have potentially seen in other talks. The fonts may be a little small, it's just because otherwise it doesn't fit. Like a small piece of source becomes a larger piece of lowered IR, which becomes a actually similarly sized piece of typed IR, which becomes a huge piece of optimized type IR. If you actually notice, that's not the full function, that's just a snippet of it. And yellow VM blows it up even more. Like once you get to the lower level, you might have to express things as pointers and other things, and that gives you verbosity, basically. And finally, we optimize the LLVM, and the final assembly comes out. And your compile time is doing this, right? It's transforming that source all the way to this assembly. So, well, what can we do to actually make it better, right? There's a couple avenues one can take. The first one is you can just compile faster. Make your compiler faster. Open pull requests to LLVM and make LLVM faster. But that doesn't scale. You're not going to get the super snappy compile times just by making everything fast, because compilation is computationally expensive. You have to go through a lot of data and perform operations. Like, there's a limit to how fast you can actually make a compiler. So there are other options. You can compile less. So I'll talk a little bit about further, but you can just not compile the code, execute it in a different way than just a very optimized assembly. You can compile in parallel. All of us probably have multi-core machines that whenever you're just playing in the REPL or doing something, have idle cores that could be co-opted into helping compilation. We can cache even more. We can double and triple down on our strategy of do a lot of work ahead of time to make sure that you never encounter something you haven't compiled before. Or you can make it easier to compile. So instead of making compilation faster, you do algorithmic changes that make it faster to compile still. Let's talk about going through these approaches one by one. So compiling faster. It's actually a pretty interesting topic to work on. The Julia compiler isn't any different from any piece of Julia code you've written, so optimizing it also isn't very different from optimizing most Julia code. It's hunting type instabilities, reducing allocations. It's things that most of you are probably already used to. And we can also make a couple changes. Sometimes we can change how we emit a piece of code that we know that the backend struggles with or has to work very hard to compile. So for example, I guess an interesting thing is this is a profile. It's completely uninscrutable, but this is a profile of what precompiling the documenter package looks like. And a couple of these bars, if you look, you might find some LLVM frames, some type inference frames. There's some lowering frames as well. And those are all the pieces of the compiler. And when you're optimizing the compiler, what you're really doing is you're going to one of these tall and large things and making it very slightly smaller. And with that, you can do things like, wait, we actually made it worse. Oops. Sadly, since 1.10, pre-compilation time has actually ballooned significantly. So Documenter used to take about 11 seconds to compile. This is all on the same machine. And in 1.13, it actually got all the way to 22 seconds, which is terrible. There's reasons for this, and we'll get to that in a little bit, but we've also been working to try and grab that down. So if you go to the latest branch, like in master, we're down again to 17 seconds, and if we enable the object cache, it actually goes down even further. And this is all mostly just things like going into the compiler and, hey, this function should be inline, and so add an at inline in that function. And I guess a short tangent on like why do we just not make the compiler slower? Well, a lot of the things that made the compilation slower were also things that were needed for important features. Like, hey, I want to be able to redefine a struct or a constant. That requires the compiler to do a lot more work because it now has to keep track of all the constants you use in your code or all the structs. Or, hey, I want to have a higher performance and more flexible memory type. That means that a lot of assumptions that the compiler could just bake in have now become real code. So that just scales back poorly. And also just new code paths that haven't been beaten down enough to the point where they're very quick. So what other options do we have? So we can cache more. We can make sure that your precompiled tools block actually does keep all the functions you put there. That requires us making your code more invalidation resistant, which is a kind of tricky topic. I think there's 1 or 2 talks that go on what does invalidation resistance mean and how do I avoid type piracy. If I recall, I think Cody has a talk on this. There's other things like being able to precompile code that doesn't have the standard Julia semantics. So, hey, I want to precompile my GPU kernels, or I want to precompile my enzyme code. Like all of those codes do not compile with the same Julia semantics, so they do not participate in our caching the same way. And we want to be able to make it so you can have precompilation of enzyme and have your reverse pass or whatever be very quick to compile or just load from memory. The object cache, I think, deserves a little special slide. It was added by Sam a couple months ago. Its idea is a large part of the compile time is when Julia has done all of its things, it gives the code to LLVM to compile. And that's a part of the code that we don't control too much. If LLVM's slow, we can complain to the LLVM devs and sometimes even go fix something, but we can't do that much. So the idea is you make a key out of your unoptimized LLVM IR, and when you compile it the first time, you go and you put it in a database, and then the next time you compile that same piece of code, you can, instead of compiling it, just go on the database and get the final assembly ready. So this is a kind of convoluted example that just compiles the same function 200 times, but if you have a warm cache, on my machine, it went from 2 seconds to half a second. And on, for example, Documenter's precompile time, not even execution time, the precompilation of Documenter actually gets shaved down by about 4 seconds from the 15 to like 12 just by enabling this cache. So it does do more than one would expect. It has some issues, like Julia's code emission is very session dependent, so that can cause some struggles. And the one that I'm more interested in nowadays is to compile less. So if compiling is slow, why compile at all? And the idea here is to bring something that's like Julia, while being a JIT compiled language, doesn't do much with that. But most JIT compiled languages like Java, JavaScript, .NET have fancy JITs that trace your execution and only compile what's actually needed. If you're only executing the piece of code once, might as well just interpret it. So that's what tiering does. It's the work I've been doing for the last couple months, which is to, when you first encounter a piece of code, just interpret it. It also does some fancy things. It will, instead of it interprets, and if detects it's hot, it actually wakes up a thread to compile it. So it does do the compilation in parallel a little bit. And this avoids a lot of the inference and LLVM latency, which, like, we heard a bunch of things about laziness. Inference is very much not lazy. If you compile one function, every single function that gets called from it has to be run through the compiler. So yeah. And for example, here are some assortment of packages where with inference on versus inference off, the first thing you do in data frames, this doesn't count loading time, so you still have the using time. But after you actually load it, data frames is 21 times faster because it's likely you're actually only doing one thing with it. And if you do it multiple times, it will just get compiled. Some packages don't benefit that much, like Cairo, Maki. I was surprised it wasn't doing that much, but the reason is it just is a very well precompiled package. If you have all that code laying around, there's no reason to interpret. And I'll skip over this a little bit, but it's just about the challenges about tiering. We don't have any work about just waking up threads to do compilation, so that's a challenge for me or anyone that's interested in getting into this. It's something we don't do, and we could. And on the community, complain more. Give open issues on base. It's much like just saying, hey, it's slow is fine, but it doesn't help us fix the problem. So make an issue with, hey, my package is slow to compile, or run this base.precompile trace thing, which if you assign this to a file, will show how long each function in your precompilation took to compile. And if you see one of them that's like, hey, this is a tiny function, it took a second to compile, it's probably something weird going on that should be fixed. And just a tidbit, LLMs are particularly good at this. This isn't a very complex task, so you can like, hey, insert your favorite robot here. Can you take a look at my package's precompilation and let it have some fun for an hour? It probably will come back with some interesting things, and either changes to your code that you can make, or like, hey, you should probably open an issue. This is taking too long. And there are some future more open-ended ideas. We can potentially interpret overtyped code. So our interpreter isn't particularly fast, but we could interpret overtyped code. And I think Tim Holy had some experiments where it's over 100 times faster than our normal interpreter, which means you gain some leeway on what you can interpret and what you can compile. Also, change to a non-LLVM backend. People have mentioned crane lift. You can potentially compile to WASM and still run on your normal machine just to have use V8 or another fancy JavaScript compiler. And tooling that inspects your code and says, hey, you should probably add a no specialize here, or you have a 400 long tuple that will cause issues in the backend and warn you instead of just letting you suffer very bad compilation types without knowing. Yeah, we're, I think, a little bit strapped on time due to technical issues. So, any questions? I didn't know if there's a microphone anywhere. Okay. Yeah, so the question was, in an HPC system, sometimes you have, each node it has a large amount of like memory, like RAM available to it, but the file system isn't particularly fast, especially if you're having to access the parallel file system instead of like a Scratch or something. Could the Julia compiler do something to exploit that? I think the answer is maybe. I think there's a couple things we can do. One is make it easier to deploy on each node. Your already precompiled depot, I think, I'm not super familiar. I know some of the HPC people have told me you can like have Scratch local depots and things of that sort, so that each node, when you're doing like a large run, doesn't slam the parallel file system just to find all your compiled code. So there's maybe some things. I'm not sure the compiler can do much there. Maybe the runtime can do a little bit, and it might need some special handling just for like, hey, look at maybe a RAM disk, for example, is an interesting option where you can just, hey, put all your caches in a RAM disk in Scratch and super fast. So yeah. Any other questions? You.
Yeah, hi. Thanks for the talk. So optimization can have two sides, right? You can optimize for speed and you can also optimize for memory consumption. And what I noticed during your talk is that basically all optimization technique, they sacrifice for memory. And that might be actually very crucial for embedded systems or for systems like Raspberry Pi, for example, that I work with. And I was just curious, what is your take on that? Because it's actually quite painful to pre-compile on Raspberry Pi. And there is no native cross-compilation. It's like super hard to do, actually. So are there any techniques that would allow to pre-compile on a different hardware architecture, or it's like just super hard to do for Julia in general?
So cross-compilation in general is kind of tricky. We've used the trick specifically for the Raspberry Pi case. Oh, sorry, the question was like, hey, I want to run Julia on a small machine. Is there a way I can avoid having a gigantic precompile time by doing something? And for the Raspberry Pi in particular, especially on the newer ones that are just like an ARM v8 core, we've had good success in the past on just grabbing a big ARM machine, either like a VM and an Apple Silicon laptop or some actual ARM server, and compiling the code there and like making everything ready in that thing and just moving into the Raspberry Pi, where the execution actually works just fine. It's just actually compiling that's quite slow. But cross-compilation in general is something we plan to work in the future, but it's not available today. Stefan.
If the tiered JIT becomes a standard thing, do we need to go around either making optional or deleting a bunch of precompile code? Because, you know, like the Cairo Mackie example, you know, we're doing a lot of work in advance and it takes a long time to precompile. Do we want to stop doing that because now we don't need to?
Yeah, one of the tests I've been doing with this is actually just disabling package images overall. And that turns out to have surprisingly good performance for some packages. So you may decide, and I don't know if exactly we have the features to do that, but you may decide that, hey, don't compile anything from my package at all. I trust that tiering is enough for the user to get good performance. And then you have no precompilation thing. So you get very snappy instantiation and whatnot. So it is an avenue that gets opened if we have and whenever we finish this work.
Yeah, I just wanted to mention, as the person putting a lot of the precompiled statements into Cairo Mackie, it's really hard to guess what functions in Mackie people are going to use. I mean, obviously everybody's using lines and scatter, but there are so many things, very diverse stuff. So either we make everything slow or we make the precompilation file huge. And I think we erred on the side of making it huge when this stuff became available, because we wanted to reduce the pain of basically loading Mackie once you have it installed. But now that we have the package images, actually, it's still problematic, because for many workflows, you need temporary envs, right? Like you build this project, you build that project, you want to add Mackie to it, but it happens to pre-compile every time because one tiny dep will be different, and then the whole stack kind of collapses the whole. So yeah, like I'm really excited about this engineered stuff because I always think like the top level stuff in Maki is not really performance sensitive. It's really all the low level rendering. So yeah, it's not really a question. I would just want to mention that I will definitely delete all the precompiled stuff if you, if this tiered stuff works out. So yeah, thanks for working on it.
Yep, cool, thanks.
Hello. Thanks for the nice talk. I just wanted to ask, when you are working with like tiered code, is there a design pattern that would allow you to say guarantee compilation? Like I trust myself enough to say that this function or this pattern over here should be compiled. Do not tier it, please.
Yeah, so there's a couple of things around this. So one, there's a lot of tests and packages and in Julia base itself that actually break because of this. Because if you go and say, hey, I want to make sure that my code doesn't allocate, if you interpret it, it will allocate by definition. So a lot of small changes can be done. So for that, there's a force compile macro that already exists today in Julia that's needed for some of these tests. So we could maybe extend it or tell users like, hey, if you really want to compile, you can just put the force compile macro in, and that forces compilation. Like the tiering has some challenges around it, like on-stack replacement, didn't talk about it, but it's a needed thing if you don't want to be stuck in the interpreter forever, and that can happen if you don't have some fancy things. But yeah.
We still have 5 more minutes for questions, but can I ask the next speakers maybe to start setting up?
Yeah.
And then I have a question.
Over here.
Thank you very much for the insights. I just have a question, maybe a bit naive one, but you said in the beginning that often it's a lot of new features that make the compile slower. And to be honest, from my side, for example, I could totally live with not being able to redefine constants if this makes compile faster. So my question is, on the one hand, how is this actually considered in the future that basically compile time doesn't blow up even further with new features? And could there maybe also be certain flags, for example, that constants are just constants in this case?
So I think there's two. One is like, we shouldn't have let him get this bad. Sorry. But it's kind of tricky to like split the world where like, hey, disable binding partitions, which is the feature that allows one to replace constants. It's very pervasive in the Julia runtime, so it's not just something one can flip a switch and not have it, right? And I think introducing these kinds of flags starts a path you maybe don't want to follow, where you're like, hey, I have this very different version of Julia than what everyone's using. Because it has, like, you're not doing things for no reason, but through, like, good intentions, you're now in a situation where you have a poorly supported version of Julia. And I worry that we should just be wary and make sure that we don't regress, like that there isn't much more that we can do outside of, if you're merging a new feature, benchmark it extensively so that we don't regress and in fact we improve. So yeah, sorry for the not very satisfying answer.
I have one really quick question here. So is there an actual roadmap that you have for this feature, for increasing the performance on compile, for introducing parallel compiled? Is there like a legit feature roadmap to ensure that we don't degrade? I mean, I use this extensively, and our compile time is already in many minutes, and we can have a 30-minute event that everybody hates sitting around on. And so I don't want to leave 1.10 now after seeing this.
Yes.
But I want the benefits of 1.12 and above. But my user base will go crazy if I say, oh, I'm sorry, it's another 30 to 50% on the compile time when everybody's already burning 30 minutes at a time out of their life.
So my goal is to land the tiering stuff, at least to some extent, hopefully in the 1.14 timeline. So 1.13 should release like in the next few weeks at best. So it's not getting there, of course. So I want the tiering work to be in 1.14. The object cache already is in 1.14, and that gives you some good speed ups. And that's the thing I'm working on. So that's the thing I can promise is like my plan is for 1.14 tiering will be there. The next steps are the next steps, and there's always small compilation time improvements that aren't necessarily part of the roadmap. It's like the make the compiler faster thing, which isn't usually large things. It's like, hey, I made it 2% faster, and you do that 50 times, and then it's actually pretty fast eventually. So yeah. Okay, thanks everyone, and
Ready for the next?
Enjoy JuliaCon.
So, good morning, everyone. I'm Tyrone Krieger from CodeGlass, and together with Yuri from ASML, we will show you a new layer we're adding to the runtime and to the compiler that allows you to spy into what it is doing. And that is, oh, you're not, okay. So, why is that important? Because Julia does a lot for you. Like if you, at the previous talk about Optimizer, your code really is very different that you write than what's being run. And in that, there can be mistakes or performance issues or things that you can optimize if you know they're going on. So this allows you to directly see the runtime behavior that happens because of your code, and I'll bring it back to one place, one way of getting this data. So where do we do this? It is at the very end of the pipeline, so just before it hits LLVM. And we do it here because then you'd have no impact on the other steps. So all optimizations, everything already happened, and all data is available, which allows us to see really what occurred with your code and maybe not what you expected. And I will go into a few details, a few examples, and Yuri will show you some more advanced samples. We also mark special events during the runtime to being able to inspect garbage collection, dynamic dispatch behavior, and many more things. So I will also be sometimes saying CodeGlass. What's CodeGlass in this story is, well, if you take Julia and the instrumentation layer, CodeGlass is a way to interpret that data coming from this instrumentation layer in real time and given to the user. So I will start off with a simple example. If you look at the code, it's very simple. It's just A, printing A, calling B, printing B, calling C. Very simple, but there is already a lot going on here. So if we look at the middle, that's what the runtime reports. And we see all kinds of data, including time and other measurements, but we also see A does 3 prints, and B and C aren't in there. And that's because of inlining. Perhaps a lot of people already know this, and it makes the effective code like this. You can also prevent this behavior with using add no inline. Then, if we add it to the code, you will again see from the runtime it reports, oh, it prints calls B, prints calls C. So, but you also see it is slower than the inline version because function calls are expensive. So, to end this, so inlining is very good, but it might also be a two-edged sword. You shouldn't add inline now everything. Let Julia handle it, but there are gaps in it. Like also the previous talker, Gabriel, said, sometimes you need to add that at inline, and you want to know if your function actually was inlined or not. And this instrumentation layer allows you to inspect that, and if it actually happened. And also, add or no inline is very useful for debugging purposes. If you, for example, have stack trace, if you no inline that, you again get your function names, and it's very much easier to follow. So still looking at the same code, the ABC code, you also see runtime behavior. Because I noticed that almost 1 in 8 times, this code was allocating, but the other times wasn't. So 7 out of 8 times, it didn't allocate anything, but 1 in 8, it did allocate memory. And with this instrumentation layer, we can go very deep. We can just click through it and dig into this data, and in the end, found it 5 layers deep in a function called it table rehash static data. So this instrumentation layer is not only for your code, but you are able to look into main and base, but also packages. You don't, it doesn't rely on your source code. Because we are at the late stage, we also have all the object and argument type data, which we can show to the user and see, okay, this was what the compiler inferred as types, but also allow us to see where it failed. Because on line 3 it says returns any. Well, so with the instrumentation layer again, we can inspect, hey, what happened there? So if we just solely look at the code, it's very simple. Just gets the date and compares it. If I read this, it should be returning a Boolean, right? You don't think twice about this. So let's inspect it with the instrumentation layer. And then we see a lot of things is going on. So we see that now returns a date type, but this function call returns an any. So during the compilation, it searched for a function that could compare a datetime and an any, which it couldn't find. So it introduced a dynamic dispatch. And then we see in the runtime, we see on the first call, it calls into the compiler to find the correct function, and then calls the compare on datetime. It also introduced allocations that are not visible in my code, but happened because Julia made your code work. So using this data, how can you fix this? How can you help Julia do what you expected it to do? Well, we can add a simple hint. So I call it a type gate, but what we do here, so this is the old code. The only thing we change is we assert that, hey, it returns a datetime. And this does, in the runtime, checks on that type, and now it knows how to run this code without the dynamic dispatch, without having those allocations, with just adding datetime. So, very easy if you have this data available to you. Also, comparison, again, could be inlined. So you will save another function call. In the end, what I want to say with this is type inferring, while it is very strong and very good, it has limits. It has thresholds, and if you reach them, you don't know that it starts failing. And then any's cascades through your code. And how to fix them is not always obvious. It's not straightforward. For example, the same issue we could fix by adding at inline. Also solve the dynamic dispatch and the allocations. So this instrumentation layer has a lot of ways to help you solve and find issues in your code. And now we will go to some real-world examples by Yuri. Thank you.
Yes, so I have a couple of examples that we actually stumbled upon, and well, we diluted the code here, so you will see that this is very artificial example, but it shows what we were dealing with, and I will tell you how we went through it and what we learned from this, right? So let's have a look. This is a very simple example, right? We basically have a one function which prepares the job and does the job. Prepare the job, create some list of IDs, whatever it needs, it's not really, and the do the job basically goes through it, do some computations. The emphasis is that computations is much heavier there, so this is just artificial example. So let's have a look. We had an issue with this code, and we didn't know how to proceed with this, with the instrumentation that we had, so we went to the code glass. OK, let's have a look. We run the code glass on the work function. What can we see here? Well, we see that do the job takes 32 milliseconds. This is our expectations. This is where people spend a lot of time profiling, that it actually takes 32 milliseconds. We're very happy with this. And prepare job also looks very nice. It takes 2 milliseconds, very reasonable. We're super happy with this. In 40 milliseconds, we can be done? No, it takes 203. Oh, how does it happen? We start looking into it. And the nice thing that code glass spies not only into the execution, but also in the garbage collection. This is like really what it can do for you. And you see, oh, we have a garbage collection event. Well expected, because it was in the code. We just disable garbage collection around our code, and we force one incremental garbage collection in the end. But it takes 179 milliseconds. Small deviation. It's not on a real system. It doesn't take 179 milliseconds because that's where the code glass have some overhead on tracking everything which happens. So this number is realistic, but it's blown up by the code glass. But we actually had an issue with taking it more time than we expected, and it was noticeable. Why so? Well, we open the garbage collection, and we see that during this event, this is the data types which were collected. This is where they came from, and this is how many. And at that time, we looked at this and like, oh, we're actually doing a lot of string operations, and apparently those string operations produce not only strings, but also intermediate results. So we actually have thousands and thousands of intermediate objects that have to be collected. That, of course, explains why garbage collection takes a lot of time, because you can see that our mathematics basically allocate a couple of temporary objects for the whole cycle. Doesn't really matter. That's why it's so fast. But this prepare thingy, which took 2 milliseconds, have a huge tax on the garbage collection, which we solve, of course, but the point is that you need to have this insight to know what you exactly want to solve. And during the system development, we were not really looking into this holistic picture with garbage collection, etc. So people focus on execution time. Execution time of prepare is good. Execution time of calculate is good. We put it in machine. We're not happy with the result. We actually fixed the problem, and we put it in the machine. We're happy with the result. It's well in budget, and we run it for a very long time, and then we see this spike. Oh, this spike, by the way, this is in seconds, so the spike is really high. It's over 500 milliseconds. Oh, that's very long. We noticed that it's somehow connected to the fact that we actually allocate some long-lived memory. We were very curious, where is it coming from and how we can deal with it. I show you another example. Again, it's an artificial example, but if you look at this, well, we have a short garbage collection. This time, we still control garbage collection. So you enable GC, you do the GC incremental, you disable GC, and of course we disable GC in the beginning of our operation and we re-enable it in the end. But we also do some garbage collections inside, and yeah, we just allocate something. We just allocate something and store it for future. Let's open the code glass and see how the code glass will see it. Oh, very nice. We have garbage collection events here. That's expected. But we look at the times of these events, and oh, this takes hundreds of milliseconds. This takes 50 and 150, and like, what's going on? That's always incremental. This is what's in our code. Why this jumps up and down? And why it actually takes so much time? Because we see that the final one takes 1 millisecond. This is what we expect. Well, we don't really allocate much. Why is it stuck in so long? Let's have a look. And again, CodeGlass allows you to open what happens inside of garbage collection. So you see all kind of interesting objects, etc. And this is for demonstration because you can actually see that the first invocation, which was like a little bit extra long, you see some compilation happens here. These objects are not really our domain thingy. This is internals of Julia compiler. But you can also see that. So you can catch that, oh, some compilation happened there, but we're okay with that. Let's look deeper. Second invocation. 2 objects deallocated. It's not really a significant amount of memory. What's going on? Why is it taking 50 milliseconds? That's the moment where we start looking even deeper. And garbage collection in Julia have its own internal counters, which are accessible through the API. And this is how many different counters you get. They are long-lived. They typically incremental counters. For example, here you see forced full sweep. Well, you start with 0. Our environment forced 1, so this got incremented, and the next instance it got incremented. And this is GC invocation 1, and this is GC invocation 2. And you look at the times, they all match up. This is what CodeGlass reports to you. This is also this information that Julia aware of. The interesting part here is this element and this element. The bottom one says auto full collection is enabled. Oh, OK, something is enabled. Very nice. And here we see next full sweep. And it says to 1. And the second one is set to 0. Let's go back to this overview. And let's focus on the scope type, because that was an insight. We actually asked CodeGlass to add this information so we can monitor what happens. And indeed, you see that the first garbage collection was incremental. But the second one, we requested incremental, and it's a full one. And you remember that on the previous slide, this force full was set to 1. What actually happens inside of Julia, it has heuristics, which decide that, oh, you are not collecting memory for a very long time. It's probably something wrong in your code. You're probably leaking memory, so let's do the full collection next time. And they were just forcing us to the full one. And that's why it takes a lot of time. But the also interesting insight is realization that after the full one, and as I said, like in our infrastructure, the first full one is not even shown here because we don't record this part of this. But there was a full one here. And then you see that next incremental after the full can actually take a lot of time. This is actually normal. We discovered this for what we do. This is actually normal behavior. You kind of have very slow incremental after full, and then you have, and if it's incremental after incremental, that's where it's fast. This is what we're looking for. OK, now we know what happens. Can we control this? We actually could not control this. So we were testing in Julia 1.12. So we connected with Julia Hub, and they said, like, well, we've discovered this behavior, and there's no way to control this. Can we control this? And they were nicely offered us API to control this. This is the API. This is how you can call this. It's not really on the public API at this moment, as far as I know. And it was introduced in 1.12.6, which allows you to disable this heuristic. We said that we would rather disable this heuristic, and we will take care that we don't leak memory by our own. So this is what we want. And when we're testing this with 1.12.6 and we enable this heuristic, this is the numbers that you will get. Again, reminder that this milliseconds is also because of the overhead of CodeGlass. We accept this. This is an investigation tool. This is not production environment. It's actually sub-millisecond in a real system. But you can see a significant difference because we don't do full collections anymore. So that was a very interesting insight for us, which we were really struggling to do this without CodeGlass, I have to say, because this kind of internals, what happens there, there's no other tool that can show you. So this is very good. And I'm giving the stage back to Tyrone to finish this.
Thank you. So what are, you already told a little bit, what are the limitations of this system? And of course, yes, there is some overhead. But the value it creates is more than the overhead, and indeed, it is an investigation tool. You shouldn't run this on production, except if you have a problem on production, it's maybe still worth it. And it currently uses a custom Julia runtime, because we add those new layers into the runtime and to add compilation. but we are fully committed to give this back to the community, to Julia, to upstream this. But we have also been told, well, that might take over 2 years. Don't expect it too soon, but we are fully committed to upstream this, so that you can also make your own tools on top of this instrumentation layer. Also, it is not fully finalized yet, because we can add a lot more stuff to it. So, for example, what we want to do is help with the invalidation of functions and the compile time, because we have a lot of access to all the data. So we can do a lot more stuff with it. Also, we are looking into making a debugger, which is also, can you utilize this system? The Visual Studio Code integration, and this data, if we add heuristics, we can also use it to automatically detect issues in your code. Give you simple list of, hey, you should probably fix this. And of course, we want to add easy ways that you can share this data to your favorite robot, like Gabriel called it, which will just make it easier. And that is what I had. So any other questions to either me or Yuri? Okay. Oh, all the way in the back. I don't know if we can get a microphone over there. I think I heard you, but feel free to restate your question.
Is there some kind of tutorial or getting started pages for doing this in Julia?
Yes, we have a full documentation on our website. It still is a bit shallow on the how-tos and the tutorials. It's something we are working on. And it's also something we like to get from you guys. So with feedback, we can create better tutorials, better views, better insights into the data, because you are all probably doing a lot of special stuff in Julia, and everyone works different. So we would like to specialize all those workflows into the application and make tutorials on top of that. Does that answer your question? Okay. Any other questions?
I also still have a question. Do you have an idea of, or can you give us an idea of what are the hardest parts of the upstreaming things you want to add?
Well, it is over 1,200 lines of code. That's going to take a long time to get reviewed and changed. There is also, you either may, we really want to do this in a good way that it isn't creating a maintenance issue for the other collaborators, because you make changes in very deep into the compiler steps, which if not done correctly, will introduce overhead during normal operations. And you can do that good, but it's also a lot of work to make sure that those kinds of issues don't happen. Okay. Yes.
Yeah, thanks for the great talk. I'm sorry if I missed this and it was covered, but can this also be used, like, for example, if I'm calling another library from Julia, like let's say some horrific C++ library, or maybe some MLIR code? Can CodeGlass also help me figure out, like, am I calling this in a particularly stupid way? Like, can it effectively talk to both sides of that, or is it for now mostly Julia only?
For now, what you would see if you call into C, for example, you see the C call function and don't see what's inside of it. So it's like a black box. We have other languages in the work, including C#, for example, and we are fully working into a system, if we support the other language, that you just can click through it. So, and C++ is high on the list on, for example, to get supported. So yeah, in the end, yes. Okay.
Maybe one last question in a similar vein. do you have any support for the GPU part of Julia?
Not fully yet. But it's also high on the list. We know it's very important. We also need to work with the package maintainers because we had to enlist those packages because they freaked out of our instrumentation. Hey, what's this code class stuff? And just say, we can't compile this. So, but yes, we will. Any other questions? Or to Yuri? Okay.
Okay, great. Thank you very much.
Thank you for your time. I will restate it. So there's now a 15-minute break with cake and drinks, probably in the Mensa. Mensa and Mushel. So enjoy.
Thank you. Excuse me, does anyone have a thumb drive available for technical issues reasons? Thank you.
One of these has OpenSUSE on it, and one of them should be formatted for storage, but you can try both of them.
Thanks.
Give it a shot.
Can I give this to you? Yes.
With USB-C?
I have an adapter. Give me a second.
Please.
Can I give this to you?
Yes.
I'm ready. Hello, everyone. My name is Jan Sardmanis, and today I'm presenting you App Bundler. It's a project which enables you to bundle your Julia applications into self-contained installers. About me, I have a physics PhD, which I got about 5 years ago, and since then I have been transitioning into cryptography and e-voting space. And today I will present a conference paper at e-vote.id conference. App Bundler started by a need by my want. I wanted to build a prototype for e-voting system. And that led me to a challenge. How can I actually deploy user-facing GUI applications in Julia? And that's how App Bundler started as a side project. But as I got NLNet funding, it became the main thing last year and will continue to be the main thing also the next year as well. The ultimate solution for deploying applications, we can imagine that we have some installation script on the web page, which has a funny name, Trust Me. And we can pass pipe into the shell script. So that would be easy for developers. It would be kind of easy for users. But there is a caveat. And so why do we actually want installers? So the one thing is we want a user-friendly experience. We want to do these things graphically. We want to download installers and then run them. We want a clean installation experience so that users don't need to trust us in the script, that we haven't left some mess behind. Then we want a native system integration, icons, shortcuts, file associations. And then there is emerging requirements that the applications need to be run in some sandboxed environment for security reasons. It's much in the spirit like we run web pages, which are very restricted environments, but not as safe, of course, as we have more permissions or access to more capabilities of the systems we run. And so, but why is installers are so hard? So for one thing, it's platform-specific tooling, vendor-specific SDKs, packaging utilities, signing tools. Then there is a platform-specific behavior, installation, launching, runtime, how is the runtime is, whether it's sandboxed or not sandboxed. Application dependencies, what's available on the system, what is actually being bundled, what is actually shared, and then we have signing and distribution and the signing things, like signing, notarization, or approval from external parties. So an app bundler, in a nutshell, solves a bunch of these problems. So if you have a Julia project for application, which exposes a main entry point, then it's ready for being bundled with the app bundler project. The app bundler takes the project, as you can bundle it with PKG images, with sys images, with Julia C, as you wish, and it builds it in a way so they can be relocated. And then these bundled archives are then piped into the packaging utilities, depending on what's your target. For Windows, it's MSIX. For macOS, DMG. And for Linux, it's now currently Snap, but the Flatpak and Deb and RPMs are going to be added in the future. So how does it work? Here, let's consider a demo. We have a demo for counting words. So we have application main script, and we expose the main, and it reads the argument, and then it prints a number of words in the file. So how can we, now it's, how it's compiled, that kind of thing, is let's say, we are actually in the example. A bundler comes with many examples, and let's run this example for command line application bundling on Windows. So while the command runs, let's check out the project we are bundling. So you see it's quite plain. We have local preferences file, and there is manifest and project file, and the source is simple. That's the thing I showed you. And we are compiling, and the preference file is simple. We say that we don't want windowed file. We use Julia C with trimming option enabled for compilation. And that's it, what we are performing. And now it's the bundling time. Compilation is finished. And so we are about to get a bundle. So it's, yeah, it's signed, and it's available in the build directory. Now we can, so since I'm self-signing the archive, I need to add the certificate, so I will do it with a script. And to launch, the launch application, so now we have the installer. And we can install our command line application. And now we have in our terminal a command line application, command app, which was compiled with Julia, and it counts for 15 minutes already. OK. So, what a bundler provides is relocatable application bundles with PKG images, sys images, which you can combine, actually, deciding what is the boundary between sys image and what's the boundary with package images. You can compile with Julia C, native package formats, as you saw. Reproducible, a bundler uses reproducible packaging toolchain with binary builder, compiling them with binary builder. So no platform-specific tooling needs to be maintained. And we have sensible defaults, so all kind of options, depending on what way you want to compile your application, is going to be launched properly. So the beyond main, Julia also, this bundler is going to be also used to bundle full Julia distributions. That's a Jumbo Julia project I'm going to present on Friday. It's also possible to build other build systems, which has their own build processes. Like it will be attractive for Go, for Rust, which does offer cross-compilation support. So now let's look into the how a bundler differs from usual approaches. So consider MSIX packaging format. Usually we use Microsoft tooling. It's make AppX and sign tool to get our installers. But the problem is not that it is not open source, but the problem is not that I cannot include it in my redistribute with the app bundler itself. So instead, app bundler uses open sources, redistributed tooling, which are cross-compiled with a binary builder. It's compiled for macOS, Windows, all Unix platforms. So you can choose wherever you want to build your MSIX archive. And what is in the staging directory of MSIX is there is entry point specification, some capabilities in AppX manifest. There is a resources prefile, which is fixes ugly rendering. Issues, there is our application icons. One can also configure installer. And then there is application launcher. One thing to mention is that app bundler changes the Windows GUI subsystem after the compilation. So this leaves a kind of unintended side effects that when you close the GUI application, which is prepared with app bundler, it leaves a zombie console process. Also, sandboxing is not explored currently as the application requires UCRT runtime, which is not available for Julia. So how it works? Installs the application, which we already saw. OK, so we saw it. And Apple tooling, so for Apple, we have DMGs. It has a much larger pipeline. So we start with a staging directory, my app. Then we code sign it. Then we use HDI util to make a DMG. And then we again sign DMGs. And then we need to get a signature from Apple. For that, that's usually one use notary tool. And then once you get a signature back from Apple, you want to staple into the DMG. So that's usually the pipeline. App bundler has used open source tooling, error sign to sign the application. Then we use Horizo to make ISO image. And the ISO image then we pass to a DMG command, which creates a DMG, and then we error sign, and then we can do the notarization with error sign as well. So what's inside the app? So we have application launcher and icons and DS stores that controls installer experience. And one caveat which needs to be mentioned is that the application launcher must be binary because it contains a signature, and in signature it also contains entitlements which sets up the sandboxing environment, how the application is going to be run. So how a bundler solves this is a launcher is cross-compiled with a binary builder, and it's just placed in, which reference the main file, a main launcher in contents libraries main, and then you can do anything. So the installation experience is simple. Last copying applications, then we find the application, and then we can start it. And that's it. Snaps is also an interesting format. It comes from Canonical. It comes with a Snapcraft tooling. What it does is it's also open source. Also, it's open source, but it wants to do compilation for you, and it's kind of annoying thing. AppBundler does use make squash fs command, which is cross-compiled with binary building. So it's that simple. The snap contains configuration options, and installation is through the terminal window. It's from the terminal because snaps doesn't contain staple signatures inside them, so there is this kind of thing, unless you want to distribute with a snap store. So how do we saw that all these packaging formats, how a diverse configuration files, and how can we actually configure some kind of inconsistable, maintainable way how we want our applications to run. So AppBundler came up with this project structure that we can have a local preferences where you put in some high-level metadata, how the application will compile, and etc. And then we have a very robust templating system beneath. And sometimes templates are not sufficient for your needs. And in that cases, for instance, you want to configure your sandbox, how your application runs in the sandbox, you take a template and place it in meta directory. And the meta directory mirrors one of the recipes directory, and it takes precedence over them. So that's how the configuration is done properly. One of the things which is a challenge sometimes is avoiding hard-coded paths in your Julia application project, which often happens when you use a dir macro. For that cases, one should use a pkg directory function referencing the module, the package module. And this works well with package images, 6 images, but Julia C, it doesn't work so well because it doesn't bundle the source files and pkg files. And for these situations, it's AppBundler come up with the idea of initializing asset index, asset index, which initializes base pkg origins at the runtime. And this works very well. Then we can actually don't want to usually bundle all assets. We want to bundle some of them. So we provide the ability to bundle assets selectively. And the assets themselves can be specified under each package. So if you have each package module, when it, for example, references JavaScript file or CSS file, HTML file, usually those files, or QML file for your QML application, then you can just, under each project name, you specify the assets keyword and list all your files. And this works also very well. So what are the challenges? Thank you. So Julia doesn't cross-compile. And to resolve this challenge, I have found that the GitHub Actions script is works perfectly for Julia. as it already contains all platform runners, and we just need to press a button on the GitHub Actions interface, and all installers are built and then uploaded into the releases page. I will show about this a bit more in the Friday talk about Jumbo Julia distribution. Then we have this issue that the code signing certificates are quite expensive. The idea how to approach this problem for now is to create an installation script which only downloads the bundle and bootstraps trust into this signature of the bundle. In that way, this script can be kept fairly short and also maintainable because nothing needs to be changed in the long term. That's one way, and the future work is going to address the Flatpak support. RPM and deb targets are going to be added for Linux. Polishing work is going to be happening with icons. As we saw, there was MSI installation, for instance, has a blue background behind the icon, and that's quite annoying that it appears for some reason. Then there are quite many packages which are not needed for AppBundler. AppBundler depends on images ecosystem for only to resizing images, and images is quite an overkill for AppBundler needs. So we need to look on to how to minimize that part of dependency chain. Then there is self-hosted command line interface, which is going to be happening with DS-store dependency, Python DS-store dependency deprecated. And then when we have the self-hosted command line interface, then it becomes more attractive for generic programming language bundling. Like Rust projects could be bundled with AppBundler in the future, or Go projects. And finding out how to make this command line interface accessible to these communities is also going to be work. Thank you. You have any questions?
I think it shows up on the recording.
I'm just curious how much additional work you think it's going to be to add additional targets, like especially Linux targets like app image or Flatpak that you mentioned.
Flatpak is going to be a really difficult problem because it also uses Flatpak builder system, and to do it in an alternative way, the goal of AppBundler is not to depend on system toolings which are available, and to bundle something with I need to consider it through the lens of what can I bundle with a binary builder, and that's quite an engineering challenge. RPM and deb targets are going to be quite fairly simple because the tooling can be cross-compiled, as I have seen it's compiled on macOS, so you just need to find the work. There's a person there.
I also still have a question. Thank you for the talk. I work in a context where we do a lot of HPC style stuff, doing things on a cluster. We talked a bit about precompile times, compile times before.
Yeah.
Is this something that could be used in that context where I'm running things?
Yes. So for now, AppBundle generally focuses on making the bundles, MSIX, but you can actually stop at the second step. There is API. You can create self-contained directories, and then you just need to make a tarballs of them which to distribute. So that could help for HPC contexts.
So I also use Julia in the HPC context. So one of the common problems we face is that the installation of HPC nodes, as you scale up the nodes, can be quite manual and repetitive. So this looks like one way of generating like a clicky installation.
Yeah, so the internal parts, the middle parts, building self-contained applications, is kind of mirrors what package compiler already does. But in this context, I don't rely on package compiler. I build the system so that I can build it package images, and I can also build the sys image and decide what's the boundary is going to be between sys image and package images.
So the traditional approach is to set up like a container, and you can go into the container, and then you can say package or instantiate just to keep the container image small. Now, I wonder if in the current approach, have you like generated like multi-gigabyte images that has already got the package or instantiate, or do you generate like a minimal image for the users to pull the packages locally once they have the environment?
Can you speak louder? I didn't hear you.
So in your current approach, do you do all the packaged or instantiate, and then you end up generating like a multi-gigabyte image for the installation? Or do you just generate the bare minimum Julia environment for the users to instantiate locally?
So there are two things. So one can approach it like I take the Julia image, a Julia base image, and then there are two passes. You can remove existing package images, and then you compile freshly images for your environment. But it also often compiles the underlying base images that you had. Or you can compile, or you can add the incremental package images on top of existing Julia installation. It's like distributing Julia with a base, with a standard library extended with packages which you want to add. So the standard library directory actually contains additional entries.
Okay, if we don't have any more questions, thank you again for
Thank
this
you.
talk.
Uh, Hi, everyone. So my name is Nishant. I'm going to talk about the Julia registrator. So the agenda is we're going to talk about a little bit of the history of why registrator came about. And then we're going to go about the usage and features. And I think the usage is something many of you already know about. And then we'll talk a little bit about why you would want to run your own registrator and what you would need to do for configuration, deployment, etc. And then we'll go about talking about a little bit about the future plans. Okay, so registrator came about in 2019. That's until then we had this thing called Autobot, which we use for package registrations. And we didn't have a general registry. We had something called metadata back then, which had a different format. It didn't use the TOML files. So we had separate files for the commit SHAs, and instead of project TOMLs, we had required files, etc. And we had an AWS Lambda-based bot, which would listen to your tags on your repos, and it would register packages based on that. So when we moved to Julia 0.7 and 1.0 thereafter, it was general registry and registrator as the de facto method for registering packages. Okay, this is just some publicly available data from github.com. This is just the registrator bots activity, and it's starting from 2019, 2020, and 21. And you can see kind of a pattern there. Lots of registrations before JuliaCon. And this is for the following 4 years. And we are at JuliaCon right now. So that's 2026. And the last image. This is a graph of those contributions over the years, starting from 2016. So we had Attabot for about 4 years, and then Attabot and registrator side by side in 2019 as we were migrating, and then we had registrator. So as many of you might know, registrator has 2 modes. A lot of you might be using the comment bot, where you just comment on your commit or your pull request. There's also the web UI on juliahub.com. And the web UI lets you register on GitLab, Bitbucket, etc. And both are deployable in-house within your orgs. So this is a sample usage of Julia registrator. So you just comment asking the registrator to register the package, and you get a response. And this is just the page from Julia Hub. Of course, the Julia Hub page is modified. The one you get in the open source registrator package looks slightly different, but they're pretty much similar. So apart from registration, you have other features, like you can include release notes. You can have packages in subdirectories in the same repo. You can register branches, and you have private packages, private registries. That is if you choose to deploy in-house. And then you have GitLab and Bitbucket registrations that you can do. So this was one of the design decisions we had to take early on. Why not just use GitHub Actions? Okay. So there's various reasons. It's not an exhaustive list, but one of them was because we didn't have OIDC in 2019. GitHub Actions were quite simple back then, and we needed those for authorization. And also, you want registrations to be interactive, unlike something like Tagbot, where you just expect it to do its work. But with registrations, you want to get a response back. I mean, technically, it is currently possible to have GitHub Actions do this, although you can't completely get rid of the server service because you still need general registry operations. But yeah, that's the technical reasons behind it. Why would you run your own registrator? A lot of people do run their own registrator because they host their own registry within their companies. And some of the reasons why you might want to do that is obviously you have private packages, private registries. You can also have dependent registries. So you can have your registry depend on packages on the general registry. And you might also be on Bitbucket, GitLab, or some other Git service. So those are the reasons. So I don't think I have time to go through all the details, but I just put up some of what the configuration would look like if you would run your own registrator. And what you would want to do, or what you would have to do on GitHub. You'd need a bot account. If you're running the web UI, you need an OAuth app registered. If you're running just a comment bot, you can have the GitHub app. Permissions, you need to set permissions for it to be able to access your commit comments, etc. And in the case of the OAuth app, the permissions come from the repo through OAuth scopes. Yeah, so at Julia Hub, we just use containers, Docker containers, Kubernetes, etc. What's included in the repo is a make file from which you can send these commands, what you want to start or stop. So just some notes on debugging. Obviously, there's log files. Slack alerts proved to be really useful during the early days because there were lots of edge cases which we couldn't take care of, but knowing what your users, the errors your users are going through is really important. So that's something we did. And there's, of course, other pieces in that make registrator possible, like registry tools, registry CI, general registry auto-merge, tagbot, Gitforge, GitHub, jail. So thank you to all the contributors who worked on all these packages. So it was a huge team effort. So thank you to everyone. So there are many plans. There are many open pull requests on registrator.jl and related packages. But the immediate plan is, of course, we're trying to move CommentBot out of Julia Hub and into Julia Lang. So we are looking for volunteers who would be interested. If you know Terraform, that would be good. So you can reach out to me if you're interested. For Registrator itself, I think most of you know the PKG registration channel on Slack. There's also Discourse and registry docs. Registrator.jl docs is a good place to start. So if you need any help, you can drop your messages there. Right. That's it. We went through the history of Registrator. We talked about some design decisions as well as features. Then if you want to deploy your own registrator, configuration, etc., then we went through the future plans. So thank you.
Thank you for the great talk. I was wondering, you were asking for volunteers. Maybe you could tell me a bit about like what are the tools you're using to set all of these things up? Is this mostly Julia, or are there other languages involved, other tooling that you should know?
Yeah, most of it is in Julia. Yes. So registrator.jl is a Julia package. Apart from that, we have ways to deploy it. So that's we have Kubernetes, Docker files, that kind of stuff. But yeah, mostly the code is all in Julia, yes.
Thank you very much. This is just a side question. There are a lot of packages in the registry right now that are unmaintained, deprecated. do you have some kind of vision how we can deal with this problem? Because when the user tries to search something, it can get a package that seems to solve this problem, but it's not updated like for 2-3 years ago. So
Yeah,
how can this be addressed?
yeah, I don't. I think that's something you should bring up in the Slack on PKG registration. There's also the general registry maintainers channel, so they might be able to better help you on that.
Okay, if there's no further questions, thank you again for the great talk.
All right. Can everyone hear me? I guess so. All right. I'm here to talk today about, sorry, one moment. All right, I'll be talking today about Julia's subtyping system. To set the stage, I think it's best to clarify exactly what we're going to be tackling. First of all, I'll be picking up a bit from my talk from last year, if any of you guys saw it. At that time, I talked a lot about two kind of sides of the spectrum of the type system. On the one side, you've got really concrete things that Julia really excels at today, where you talk about, oh, I have an integer, or I have an integer, or a floating point number, but it struggles to talk about really abstract stuff, like, oh, I have no idea what type I'm holding on to here, but I know that it has a field x with some type float64 on it. Or I know that it conforms to a certain interface, so I'll have certain methods available, for example. And last year we talked quite a bit about those specific types of structural types, what it would mean to have, for example, an abstract type that talks about its fields. This year I want to talk a little bit more technical and dive into this duality itself from the subtyping perspective to see, like, where does this axis with two sides of it come from in the first place? And so we're going to dive into the subtyping algorithm, kind of see what happens, and try out a couple of crazy ideas. And to be clear, to set the stage for the problem we're actually tackling here, this is not a wholesale replacement of Julia subtyping or anything that ambitious. Today, we'll just be talking about simple types, because I want to explore some new concepts in a familiar context, but we're going to restrict ourselves so that we don't get into a problem that's too complicated that we can't reason about it anymore. Julia subtyping is famously undecidable, hard to reason about, buggy, so we're trying to avoid all that by choosing a restricted part of our problem today. So we'll handle a lot of the normal types that you see in your packages: data types with parameters, tuples, abstract types, abstract vectors with upper bounds. All of that is okay. It's really just two things that we'll be forbidding for the type system today. One is that we will not allow you to have type parameters that are far away from their where. In this case, this one is bad because it's 2 deep instead of 1 deep. Like the case of the abstract vector above is equivalent to just having a where immediately outside the type. But if you go 2 types out, for complicated type reasons, that makes reasoning about this substantially more complicated. So we say that vector t with the where all the way on the outside is not allowed today for the purposes of this talk. And then the other thing we're not going to allow is essentially all of the diagonal rule and multiple appearances of a variable correlating with each other. You can use that for useful things. It's very important to, if you want to like define diagonal elements for a multiplication operator or things like this. So this is an important part of the Julia type system, but it gets complicated fast, so we're going to leave this out too. And the rest that we'll be talking about is really what's left of subtyping after that. Why is that worth talking about? Well, there's still a lot of open bugs in Julia all throughout the compiler and subtyping system that have to do with how complex the system is today. And what I really want to explore today is if we make this minor trade-off here, maybe not as a practical proposal, but as a thought exercise, if we give this up, what do we get in exchange, and what can we do with our subtyping algorithm instead? And then we're hoping as well on the way that we'll maybe get a little bit of extra performance out of this thing. Julia's subtyping algorithm notoriously has some very, very slow paths. And we try pretty hard to keep users on the fast paths because things like, pretty innocent seeming things like a couple of large unions in different parts of a tuple can end up exploding geometrically or exponentially, or even more than that if you're very unlucky. And then we'll see if we can also get a couple of extra cool features as we explore this stuff too. So the main idea today is actually that we're going to introduce, here I'm calling it 2 operators, but you'll see in a second it's actually just a single operator that we're adding to the type system. I'm calling these types intersect and not. And that probably sounds pretty confusing if you've never thought about this kind of concept before. It certainly was to me. But I'll try to give you a rough idea for how these behave. The general intuition is that you're going to want to think about these in terms of sets. Similar to how like a union between an int and a float is either an integer or a float and kind of takes the objects in the first type and combines it with the objects in the second type. An intersection is going to do the opposite. It's going to take everything in common between the 2 types. And a negation is going to take everything outside of the type. So negation is probably the trickiest part here, so I wanted to specifically give some examples. Negation obviously excludes the type itself. So an int is not a subtype of not int. Not int is everything except int in the whole system. So float64, for example, well, that's not an int. So float64 is indeed a subtype of not int. And then a couple of other examples. Integer is not a subtype either because of the specific int case. And abstract string is a subtype because it has nothing to do with int, so there's no exclusion there. So in general, the way that not types work is that by default, you're a subtype of a not type unless you match the exclusion, in which case you're actually excluded from being a subtype. So you can treat it like an exception. It's any except this specific type that we named here. Now, I didn't introduce this type because I thought it would be useful to users. I introduced this type mostly because I thought it would be useful to me, and particularly because it allows us to do this kind of distribution. So what you'll see here is the first line just says intersect not int64, not float64, and then not union int64, float64. Now, that's probably a lot of type gobbledygook at that point. But what I want you to appreciate here is that if we translate this into a more logical notation, where I use the traditional negation operator for not, and I use the set intersection operator for intersect, all I'm describing here is De Morgan's laws. So the main idea here is that not is this magical thing that can transform intersections into unions and unions into intersections. And so this is also going to be the same thing that takes us from one side of our diagram earlier, where we're dealing with really concrete stuff, to the other side, where we're dealing with really abstract types. Anyway, there's more reason to do this too, which is that even the folks who have not been quite as aggressive as I have in terms of banning different parts of the type system have also run into issues even just defining the semantic meaning for Julia's types without this kind of set, these kind of set relations that they can reach to. Julia Belyakova has a thesis from 2023 where a flaw was pointed out in the thesis which was hoping to try to say, this is, like, these are the sets of values that correspond to a Julia type in a precise mathematical sense. But unfortunately, the subtyping algorithm that was given in that thesis can't be completed without intersection and negation types, because of a specific example that if you're curious about, you can search GitHub Julia Belyakova thesis, and it'll take you straight to the excerpt here, and you can read the details yourself. But the main thing I wanted to point out here is that there's some sense in which this kind of completes our theory and lets us do some powerful set-like reasoning in our subtyping system. So like the main thing it lets us do is that we can do much more exotic type equations than what we could do before. So the main way we're going to try to tackle the subtyping problem is by reasoning primarily equationally and algebraically, because once we have intersect and not, we essentially have all we need to have a Boolean algebra. So we can define our whole subtyping algorithm in terms of a Boolean algebra. So here I've written, for example, that if you want an intersection between two tuples, you need to have their two components intersect. And if we draw the diagram here, it's probably easy to kind of imagine how this works. You've got two kind of abstract boxes. They're not necessarily contiguous in any type sense, but there's in each dimension, there's a set of types corresponding to it. And both of those dimensions have to intersect for these boxes to overlap. And so that intersection is what we're talking about when we talk about tuple intersect tuple here. And then we can break it into the individual components. So in a very straightforward way, intersect just distributes straight across tuple, similar to how intersect distributes out of tuple, union intersects out of tuple in Julia today. So then that's great. We got like new equations, but where's the part where we start making progress on subtyping? The main idea here is that we can, again, kind of illustratively take the two tuples, overlapping tuple scenario. This is kind of the minimal interesting structural example for Julia. And we can start to try to write some useful equations to help us solve the subtyping problem here. It's worth asking the question, semantically, if I have this abstract sense of what the sets of objects corresponding to type A and type B are, which are the objects in those sets that I'm looking for when I'm trying to do a subtyping check? Like, what is subtyping actually telling me? And the answer is that subtyping is basically checking a subset inclusion. So I want to check that everything inside the left-hand side type is included in the right-hand side type, which is logically equivalent to me saying, I want to look for anything in my left-hand side type that is not included in my right-hand side type. And if you're paying close attention, you could probably already figure out where this is going. So this little sliver of type right here is exactly what we're interested in finding when we do subtyping. Like, this is what all of that computational effort, the super exponential algorithm, it's all to just find this little rectangle here in obviously a more mathematically complicated space than I'm simplifying the diagram down to here. But conceptually, this is it. We have two sets, and we're trying to figure out what's in one set and not in the other. And so what we can do is, we obviously can't just describe this rectangle right away, or we'd have our answer before we even started. But what we can do is we can take this right-hand side, and we can, it's not very useful for me to use it directly, but what I can do is I can negate it. I'll need a little bit more space here. But we can just go ahead and negate the whole thing, and now I've got all the space outside of that tuple, every other type, according to the definition we gave earlier. And now I can go ahead and take the intersection like I did before. And this time, I do get the piece of type that I wanted. And so this is a really interesting little trick. I just did two quick little type operations, and all of a sudden I isolated exactly the piece of types that are relevant for a subtyping check in the algorithm. And it turns out that this, and so then we just need one more step here at the end, which is that we want to check whether or not this is inhabited. Like, it's easy enough for me to write this down. Obviously, I just wrote it down, intersect type A, not type B. But this clearly implies that the question of deciding whether an arbitrary type that I've written out is actually inhabited is an interesting question in this system. It's not obvious just because I didn't write down union empty brackets, whether or not I wrote something equivalent to union empty brackets. And so that's the question here is this statement on the right-hand side, intersect tuple, not tuple, is that equivalent to union empty brackets, or bottom in Julia? So this is a really interesting trick. It worked in tuple, and it turns out actually that this trick works in general. This is one of the properties that we get out of our Boolean algebra if we have intersect and not types, is that I can always decompose the subtyping operation into the sequence of steps. I can just take a quick intersection and then intersect with the not, which is basically taking all the types in one group and subtracting them from the other group. And then I can go ahead and check whether that thing is inhabited. So it means that you might be inclined to think that, oh, this means that subtyping became easier, but probably the more accurate reading is the opposite, which is that inhabitants just became as hard as subtyping, but hopefully not any harder is the main pitch here. And so if we can decide inhabitants, we get subtyping for free, and we'll see if actually the extra relations that we got out of our types here make subtyping any easier. It's also worth mentioning that, just as a technical side note, there are already interesting union bottom types in Julia, and this is actually part of the reason behind this kind of contentious issue on the Julia issue tracker. We fixed a bug in a way on Julia 1.10 where the compiler would take an intersection and it would just, because almost every type that is uninhabited in Julia is just union bottom, except for a couple of exceptions like tuple union bottom, or more complicated towers of tuples that all end up in some bottom somewhere. The compiler would just generally not, it wouldn't crawl through your tuple, it wouldn't check whether or not you ended up in bottom eventually. And what this means is that you eventually end up in a contradiction, and it leads to an unsoundness in the compiler. So we had known seg faults that this was responsible for because the compiler, when it did an intersection, would check for just bottom and wouldn't check for tuple bottom or any more exotic scenarios. And because we don't have an inhabitants predicate in Julia, we don't have anything that says, like, look at this complicated type, tell me whether or not it actually has any inhabitants. We had to kind of give up on the type side of this and instead say, you know what? Users aren't allowed to reach for tuple bottom. Tuple bottom just doesn't exist anymore. You can't create it. You can't instantiate the type. Like, we just delete it from the system. And this made users a little bit upset because in some cases it's quite useful to create a tuple bottom and then to grow it. For example, if you're doing like a widening operation in a loop, you might have a small tuple that you start out with absolutely nothing in it, and you want to union in new types as you grow it. You just can't do that in that way in Julia now, because we don't want to allow you the possibility to create these non-unique, uninhabited types. So this goes very much in the opposite direction. It says, let's make tons of uninhabited types, and let's get really good at detecting whether or not they are uninhabited. So we go back to this spectrum here a little bit, and I want to just point out where this kind of lies on this two sides of this axis. On the one side, we have it might superficially seem like we have similar amounts on each side of this axis, but in reality, we have very different kinds of things on each side of the slide. On the left-hand side, we have like operators that take an existing type and transform it into something else. I can take a type A from you, and if I know that I'm also returning nothing, I can just union nothing into it, and all of a sudden I get a brand new type that just has nothing added in. If it had it already, it's still in there. It behaves exactly like that. And then I also have this magical union all operator that we call where in Julia that lets me take a whole collection of vectors, whereas normally I'd only be able to refer to a single one with a very specific element type. But on the other side, we really don't have any operators of that kind in Julia today. So the kind of main thing that this talk is answering is where are they? And the main answer is that these are the duals of the left-hand side operators. So when we introduced not, we also got intersection for free. And you can even get more complicated types. I'll talk about this a little bit at the end of the presentation, just as a quick note. But there are a lot of interesting exotic types from like TypeScript, for example. This is an example of a conditional type that you can decode into like a logical statement and evaluate with this kind of algebra. Anyway, so quickly to go through the type equations. I don't think I'll spend too much time here, but it's worth mentioning that like we covered the intuitive case already, where two tuples are overlapping. So it's just like the intersection of two boxes. That's pretty straightforward. But there's also the case where you have one that's positive and one that's negative. I gave you not. There's nothing stopping you from putting a not around a tuple. In fact, that's exactly what we said we were going to do back here when we said that this is how we were going to define our subtyping. So if you give me a tuple and you want to check whether it's a subtype of another tuple, I need to write an equation just like this second one on the screen. And so the main way that this gets solved is that instead of checking that you are that you intersect in both components, you want to check that you have an exception in either one component or the other, basically. So this is very similar to the operation we just did, except that I'm breaking it down into the separate pieces of the tuple now. So you can see here, for example, the first piece of this OR, the tau 0 and the sigma 0, correspond to the left-hand side piece here. And then the tau 1 and the sigma 1 correspond to the right-hand side. So you can see we've kind of like completely collapsed one dimension and only consider looking for an exception in the other one. And in this case, our exception is in the right-hand side. So we find it here on the right. And this is a very useful trick, the fact that I can turn this like abstract complementary space for negative tuple, because there's no innate rule for how do I evaluate what the space inside not tuple is. But if I can decompose it into these elements, then I can evaluate that. And then the subtyping system knows how to handle this question of like, oh, well, it might be this or it might be that. So conjunction is all handled in subtyping already. The fact that we can decompose into these conjunctive cases is really what gives us the power here. And I won't go into the details here, but this is also the kind of equations you get from vector, which is essentially checking that your upper bounds and lower bounds are on top of each other, so that you're basically, if one vector is missing a type or missing an object that's in another, if one of its bounds exceeds the corresponding bound in the other type, as you might expect. It gets a little bit more interesting because in general you can kind of take multiple vectors and add them together, or subtract multiple vectors from one, but we won't worry about that too much today. It's just to say that there is kind of a more interesting algebra here, and that as long as we stick to our restricted type system, like our restricted simple types that we talked about earlier, all of this kind of just works the way you would hope. And you can just do this translation from the left-hand side to the right-hand side, and then keep descending in your subtyping algorithm. So then the way that things actually break down is that we end up with a ton of conjunctive constraints. What I mean by conjunctive is that it's basically made of structural conditions and made of Boolean and conditions. So all we consider is really simple to evaluate stuff like, can you be a float and an int? No, that's obviously bottom. So then I can just move on. I know my search needs to go find something else. Can you be an integer and not specifically an int 8? Absolutely, that's not a contradiction. So then keep going with your search. So that's an example of some of the constraints you get out here. I'm going to kind of breeze through here in the sake of time. But basically, one of the advantages you can get here is the not operator not only lets me do this kind of transformation with equations, but it also lets me tell my subtyping algorithm when it starts, like, it lets me tell why I failed in a specific avenue. So I go down one branch of my search, and I know that it didn't go well. I can tell the solver, oh, here's a specific part of the problem that you must solve if you want to make progress. And so then the solver can make a more intelligent back jump to a different decision rather than just kind of arbitrarily trying all the decisions available to it. So then you get this conflict-directed search out of it. And that gives us two probably significant advantages versus the existing subtyping algorithm in Julia today, which is that the subtyping algorithm in Julia today is kind of forced to do this thing where it cuts the left-hand side type up into the smallest possible pieces it can. And it does that because it knows that it's possible that the boundary of your right-hand side type lines up with one of these lines that drew on the screen, and it just has no idea which of the lines it lines up with. And so it has to take the smallest possible unit, and it visits every single possible element on this grid. That's not 100% true, because there are fast paths that allow this to reason a little bit more intelligently in Julia, which is why the fast paths are much faster. But the slow paths generally do that. They're kind of forced to just go through every single pixel, if you want to say, in your whole type, which is why adding a ton of unions in multiple tuples can cause subtyping queries that take tens of seconds or even minutes in some like really exotic cases. Okay, great. And so in general, that kind of searches O, F, and D, but the nice thing about the intersection and not types is that they allow us to kind of pick up these partitions dynamically. I just use my one type to cut my other in half, and then I can proceed from there. And then I just wanted to share some results in terms of this. This is a small algorithm that I did implement. I do want to be really clear. The simple restriction is doing a lot of heavy lifting here. It is dramatically easier than what Julia has implemented in its subtyping system. It's part of the big trade-off of taking that restriction we talked about at the beginning. But this does allow us to scale much better. So here's an example of like a mildly pathological example, or moderately perhaps, for Julia, where Julia like quickly starts to scale up into the hundreds of milliseconds or seconds, and we safely stay down in the millisecond range. I imagine it can probably be improved beyond that. I actually haven't optimized this algorithm much, which is also why Julia's C implemented algorithm does beat me on the lower end as well. So It's not a pure win, but I do think the scaling advantage is kind of demonstrated here. And the idea is, of course, just to kind of demonstrate an architecture. Anyway, I did want to mention whether or not this can be generalized. I think the answer is essentially yes, but the theory gets immediately complicated as soon as you lift the restriction I talked about at the beginning. The interaction I alluded to earlier, where you can kind of share conflict information back and forth between your constraint system that knows about what types are and your solver that has no idea about types other than that it's searching for lots of different possibilities. That's a very familiar kind of architecture that comes from the S&T world too, for example. Unfortunately, we're in a theory that's much harder than SAT, which is probably not a good sign. We're almost certainly need a quantified Boolean formula solver, which means that instead of being just NP complete, because that would be too easy, we are like this. Even just this little fragment of our solver is probably p-space complete, which is not comfortable anyway. But that said, I do think from an architectural standpoint, in terms of computing the right result, I think that this kind of hybrid approach where you have an advanced Boolean solver working together with a theory that's aware of how your types work is a compelling architecture that would kind of extend what I've done here to something potentially much more advanced, both in terms of how it searches through this space and in terms of being able to lift this restriction at the beginning so that, who knows, maybe it could actually replace Julia's subtyping algorithm one day. Let's see. Let's skip this. Oh, I did want to mention on the undecidability standpoint, on the undecidability front as well. Undecidability is not here with the restriction, but it immediately comes back once you lift the restriction we talked about at the beginning. So there really is a lot hinging on that simple types question. And I think today helps or the proposal today helps with simplifying the algorithm, but it doesn't help bound that space that opens up once you make your types as complicated as they are in Julia today. Anyway, I think that about concludes it. There's lots of potential nice features in other languages that we could have if we had this kind of thing, but sadly the non-simple types do make our life difficult here. But I do think there's something compelling about this a Boolean algebra approach to subtyping. And also it's worth mentioning that on the topic of simplicity, the implementation here is something like 600 lines of Julia versus the 7,000 lines of subtype.c. So that's an advantage as well. Anyway, that's the talk. Thank you. Any questions?
So in this last slide, you mentioned several things that are possible in other languages. My question would be, what makes subtyping harder to solve in Julia? Like, why are these things possible in OCaml or TypeScript and like a research problem in Julia?
I think it's a difficult question to answer succinctly. I think the basic answer comes down to the fact that you have to make a very informed trade-off between exactly which type of complicated you allow. Most of the static languages that do this successfully, they generally don't opt in for exactly some of the stuff that we do. For example, they won't have union all types in the way that we do, but they'll have other types instead. It's pretty easy to end up in undecidability when you add fancy type features, whether or not they're specifically the ones that we chose. I think that the basic takeaway is that once you allow for type variables that can appear in multiple places in your type and interact in any interesting way, it almost immediately becomes extremely complicated. I don't know of any language that's an exception to that. Many languages become immediately undecidable for that reason.
Yeah, just like specifically wanted to say that Haskell and most of those other languages are also undecidable and have basically all of the same problems. It's a little bit different sometimes if you have a compiler.
Yeah, I think the main advantage they have is that any limitations for their type system don't hit you unexpectedly at runtime.
Hello.
So my question is more about traits. So if this enables multiple abstract inheritance, this solves a lot of problems. But at the same time, it has the problem that when you have multiple abstract inheritance, you cannot extend the supertypes of some external type. Imagine that I create a new package where I create my new trait, and I want to extend that to foreign types. That's not doable. But traits like in languages like Rust, this is doable. So I don't know if this would apply or not. On what other alternative would we have?
Yeah, I don't know if I've thought enough about that question in detail to give you an excellent answer. One of my caveat slides that I had to speed through here is essentially that there are still design questions to figure out, even if we were to just, like, the thing I didn't get to mention here is that you can declare your struct foo and then subtypes abstract vector, for example. But intersection gives you a nice way to naturally declare extra supertypes. So if you want to both be a subtype of abstract vector and also be an IO object, that's totally fine. And that comes kind of automatically out of the type system here, just by virtue of having an intersection type. That said, I think there are still semantic questions, like, does dispatch still behave well in some practical sense once you introduce those kind of intersections? And then maybe there are some others that the runtime has to worry about as well.
I have a final question myself, but can the next speaker maybe already start setting up? I was wondering if you could comment on if this can be eventually bubble up to more of a user space where we can use this for dispatch, or we can use this to express certain things about code that then the compiler might be able to take advantage of, or is there any specific use cases like that you could envision, or?
Yeah, I can definitely, I think there's a lot of theory still to get through before we're ready for that. Like we don't seem to be in a position where we're ready to take the restriction I made on the first slide, right? And so until we figure out that problem, I don't know if we're quite ready to take them on, but if we were, then I think there's lots of types. Conditional types from TypeScript are an example. Structural types, like being able to say, oh, I have a struct with some field X and a type float64. If you want to be able to subtype that, it's much easier to implement in this kind of structure versus subtype.c, which I kind of worry would double in size if we added those kind of features. So
all right.
That's it. We can call it there. Thank you, folks.
Does anybody have a device for changing slides remotely with them? Do you think you could plug this in for me? No, nobody. Not a single person. Wow. That's bad. Oh, look, what's this? All right, no. Oh, you have. Excellent. Thank you. I had it this morning, but then it's vanished. So make sure you get it back. Oh, yeah. Does it? Does it have a little thing? Ah, very good. Thank you. Come on. August. Yep. Okay. Great. 12:32. Are we allowed to start? Yeah, good. Okay. Great. Got the time. That's very good. So this is, is something showing on the screen? Yes, good. I'm Simon Peyton-Jones. My day job is I work for Epic Games, not doing, using Haskell, but not designing Haskell in my day job now. So instead, we're designing a programming language called Verse. And the purpose of this talk in the next 28 minutes is to tell you a little bit about Verse. This does not work. Drat. That's bad. Oh, you have to turn it on the side. The side. Oh. Ah. Oh, it works. Look at that. Thank you. OK. So Verse is an implementation of Tim Sweeney's vision about the metaverse. Now, Tim Sweeney has been talking about the metaverse for way longer than Meta has. So he's actually been on this for a couple of decades. He is the founder and chief executive and largest shareholder of Epic Games. And his idea is to build a programming language in which you can program behaviors in pervasive, persistent 3D simulations of the world. So this is all sort of starting with the Unreal Engine, which Tim implemented himself, by the way, the first version. That was his creative input in the begin with. But his plan for the metaverse is this sort of very open system. So no walled garden, no corporate overlord, and lots of pervasive open standards. So Tim is primarily a computer science, sort of nerdy type, not a business type. So his values are all in the right place. I like this a lot. So whether this will come to pass, we'll see. But he's very passionate about it. So then, well, it was working. But now it's not. Come on. OK, so I have to be very close. OK, so Tim wants us to design a new programming language to program behaviors in this thing. Do we objectively need a new programming language? I don't really think so, right? We could use Lua or Python or even Haskell or Julia, maybe. But Tim, quite separately to Epic, has been thinking a lot about programming languages and programming language design. And he has a very unusual mind. He's very technically intuitive, and he thinks about programming languages in quite an unusual way. So that's what he plans to do anyway. And my job is to reverse engineer the design for Verse that Tim already has in his head, to sort of reverse engineer it out of his head. So we've actually got two projects going in parallel. One is so-called Shipverse. This is the language that you can use today, right? And Epic is busy moving from Fortnite as a game that you play to Fortnite as a platform that you can program your own games in. And so Verse is the programming language in which you write behaviors and so forth for your game in what's called UEFN, the Unreal Engine for Fortnite sort of platform. OK. So the shipping language is a fairly conventional object-oriented style language with subtyping and structs and classes and so forth. It's meant to be upwards compatible with the language that Tim has in mind, but you can already use it today. So in some sense, Verse is already out there. You can, there's a couple of links here, and you can use it. Now then, MaxVerse is the language of Tim's brain, right? And that's the language that I'm trying to figure out exactly what it is. That's my day job. And it has turned out to be a fairly substantial research project because Tim's vision of this language is very far from from conventional programming languages. So in fact, it's turned out to be not just a routine application of programming language designers, tools, and systems. No, it's pushed us into quite a new space. So here's Tim with a hat on. He has all these thoughts, and our job, as our little research team job, is this, right? We're trying to sort of suck out of Tim's brain the essence of what's really going on, and to try to write a tangible, concrete specification for what Verse is. But of course, like any plate of spaghetti, you soon end up with a lot of it on your lap. So Verse is this MaxVerse thing is quite a complex but very interesting design. What I'm hoping to do in the next 25 minutes is to give you some kind of visceral sense of what Verse, the programming language, might actually look like. OK, so here is sort of, like a solar system view of the language design space. If you are an imperative programmer, you probably think that C and C++ and, Fortran and Perl and Python and so forth are all relatively close, sort of all relatively distant from each other. But if you zoom out a bit, right, and you're a functional programmer, you say, no, you guys are all just earthbound languages, and we have functional programming languages out on some other planet in the solar system. Very different. But if we zoom out a little bit further, verse is sort of somewhere out in a neighboring galaxy. It's occupying a quite unusual point in the design space, as you'll see, I hope, in a few minutes. Okay, so that's big picture. Now, what roughly then is, from a high-level point of view, what is verse? Well, it's a declarative language. What do I mean by declarative? A variable name like x stands for a value rather than standing for a mutable cell that contains values. See the difference? Right, so in Haskell, f of x equals blah, blah, blah. X denotes a value. You can't mutate x, right? Of course, each call of the function might instantiate x to be a different value, but that's just a different instantiation of the function. So in declarative languages, variables denote values. In imperative languages, typically variables denote cells. Verse is declarative in that sense. It unifies expressions, patterns, and types. I'm going to talk quite a bit about that. And it has a rather unusual static type system. So it is statically typed, but in a very unusual way, as I think. It's lenient, but not strict, meaning there is an order of evaluation, but it's not strictly left to right order evaluation. And it has a kind of effect system rather than I showed you monads this morning for separating out I/O. Verse doesn't use that. Instead, it has an effect system for distinguishing computations that can do side effects or input-output or even choice from ones that cannot. Okay, so it's time to become a bit specific. I'm going to show you quite a lot of code to try to keep you anchored concrete. So at first, verse looks pretty conventional. Here's a function definition and some calls. The function calls are with square brackets. You can write as well, of course it has lambdas, so that function definition for F1 could also be written using this function open round parens, curly braces body, or with a double arrow. They're just lambdas. So first unusual thing, unusual compared to most languages, is that choice is part of the fabric of verse programs. So fail is a computation that just fails. 5 returns 5. 5 choice 6 returns 5 and then 6. It's as if iterators are built in a fundamental way. 5 choice fail returns 5 and then, well, nothing, so it just returns 5. Fail choice 5 just returns 5. 4.8 returns the choices 4, then 5, then 6, then 7, then 8. The same as the computation at the bottom. And as we'll see shortly, this choice thing is not commutative. 4 choice 5 does not behave identically to 5 choice 4. Then verse adopts the same idea that some old languages like Icon and Snowball adopted, which is that once you have this idea of choice and failure, it's quite cool to make conditionals work over choices and failure rather than having a Boolean type. So the conditional says, if something, and if the something fails, failing isn't bad. It doesn't indicate a runtime error. Fail just means I didn't return any results, right? So it's a perfectly fine thing to do in working programs. Indeed. So if E, then something else, something else. If E fails, we're going to do the else part. And if E succeeds at all, once or more than once, we'll do the then part. Okay? That's how conditionals work. So it follows that greater than has to be a function that takes 2 values, and if one is bigger than the other, it succeeds actually returning the left-hand argument. And if it fails, if x is not bigger than the right-hand argument, it just fails. Okay? No Boolean type. Make sense? Look intelligent? Yeah? No Boolean type. Right. So 0 less than x less than 20 makes sense in verse. It parenthesizes to the right, it's right associative, because then the x less than 20, if that succeeds, it returns x, which we can then compare with 0. So it means exactly what mathematicians mean. It's quite cool. I think this is sort of cute and useful, but not terribly important. But nevertheless, it's quite nice that notation that mathematicians use, like 0 less than x less than 20, does actually work in verse. Okay. Now, sequencing. Verse has sequencing, left to right sequencing, that behaves, if you've ever used the language with list comprehensions or language integrated query in C++, sorry, C#, or comprehensions in Python or other languages, then this is very much what sequencing does. So here, this example, X is bound to the choice of 5 or 1, semicolon, means and then, Y is bound to the choice 1 or 4, and then return X plus 1, X plus Y. So here, think of this as a nested loop. We bind X to 5 and then do everything that follows. And then we bind X to 4 and do everything that follows. It's just a nested loop. At any moment, X is bound to one value. It is not bound to some kind of choice of values. X is bound to just one value at a time. Okay? It is very conventional if you've ever used comprehensions. But you can also have failure involved as well. So this second example says, well, let's iterate over X and Y and then check X bigger than 2. If X is not bigger than 2, it just fails. And failure means return no values. So for any iterations in which X is not bigger than 2, we won't return anything at all. So that was another convenient reason that if thing, no Booleans, has been very convenient here too. Here there's another one with an equality rather than greater than. You can relate two elements. So far, so good? Right. So these are just pretty simple, just nested loops. And this already gives us a chance to do some, cute but useful things, like if you say, if something choice something, which I've done in this first example, X bigger than V, choice X less than 0, well, only if, in a choice, only if both fail, then the choice fails. So this if, really, the choice really does behave like an OR. If either of the things on either side of the choice succeed, we'll get into the then branch, right? So in this way, choice is behaving a bit like the OR of a Boolean, but it's just over choices. And similarly, semicolon behaves like AND, right? Because in semicolon, if either fails, the whole thing fails. Does that make sense? Cute, but not the only reason things were built like this. So let's talk about, so we talked about choice and Booleans, and so choice is one big thing. Tuples, the next big thing. Tuples and arrays are the same thing. They're just synonymous in verse. And you can build them by just taking, using round parentheses for literal arrays and square brackets for indexing. Okay, so then to create larger arrays, we can use this for loop thing. What does for do? It's a construct that does one thing. It takes a choice and turns it into an array. So if I say 4 of 5 choice 89, that will return the pair 5, comma 89. Okay, so 4 takes a bunch of choices and turns it into, and sort of reifies them. As if choices feel a bit like control structure stuff, right? 4 turns that choice into a data structure, a single array. In Prolog has a similar thing called bag of, that sort of takes all the choices and builds them into a data structure. But here it's very fundamental to verse, and it's the reason that choice is not commutative, incidentally, because you'd have to flip them around. Because, yes, let's see. Any of these interesting? So, oh, that's right. So for X is 1, so if I make X to be the choice between 1 and 10, but then I filter for just even X's, then I have a bunch of choices in which X is just 2, 4, 8, and so forth. And then the 4 turns that into an array. Okay? So far, so good? Yep. All right. Let's see what else about tuples that we can, and of course we can index arrays, so we can use the same for loop to build new arrays for old ones. But I'm out of time. I do want to stress, though, the duality between tuples and choice. So for goes from choices to a tuple or array, and there's an operator called colon that I won't have time to spend very much time on that goes from arrays back to choices. So there's you can really just go in both directions. It's quite a nice duality. This is not just, colon is not built in for this purpose. It has all sorts of uses. Okay. Next piece, I want to talk about types and expressions. I said types are expressions. Verse is statically typed, and yet types are expressions. What do I mean by that? A type in verse is a function, a value-level function. You can write, user-defined function, that the function takes an argument and returns a result, but it may fail. If it fails, that means that the argument wasn't in that type. Does it make sense? Right? So the int type is a function that takes any old value, and if it's applied to a string, it fails. Remember, failing is not bad. That's not a typo, it just fails. So I could say if int applied to the string wombat, and I just get into the else branch. There's nothing wrong with that. So int is like a dynamic type test that says, but if it does see an int, it just returns it. So it's the identity function on integers, and it fails on non-integers. Okay? So where are we? So you can see that what really happens is that a function applies its argument type, the type of its argument, to its actual argument. So I've written in yellow a sort of informal desugaring. We'll see a little bit more later. So this function, lambda x colon int IOE, that really looks like an ordinary lambda that takes an input I, applies int to it, and then binds the result to x and continues with e. Does that make sense? So, so type checking, or type, is like, this is a runtime thing. You apply the type notionally at runtime. And these things that I put type in quotes, because the things that we use as types don't necessarily even need to be identity functions. The absolute value function is a perfectly good function to use in this type-like context. Then it's like a sort of view, was we apply, if we got this lambda x colon abs dot blah, what was blah? E, yes, here. Then we're going to apply abs, the absolute value function, to the input. It might fail, but if it succeeds, it'll probably take the absolute value of it. So it's not necessarily a partial identity function. Now, what else can you do? Well, users can define their own types dead easily, right? So here's nat. Nat takes an int, and then the body is x bigger than or equal to 0. This is a user-written function. And if x is not bigger than or equal to 0, well, it just fails. That's fine, right? Means that this type is not this value is not a nat. So it's very easy to write user-defined types. Here's a type that says 1 or 2, that says, it just says, it succeeds only when its argument is 1 or 2. That's a very small type. It only has the values 1 and 2 in it. Here's a, types can be sort of dependent in a way. So here's a type of pairs, so gr pair takes two integer values, and checks whether one is bigger than the other. So the only values in this type are the pairs in which the first element is bigger than the second. So types, remember, denote sets of values. That's all, right. Okay, and then types can be polymorphic too. So we can swap, this function swap takes t, a value, an argument, as a type. And then it gives, then x and y had better be of that type t. So it will take the function, it will apply t to x and y. And here's a swap applied to int and 3.7. So let's see, I'm going to skip about functors. The thing I want you to get hold of is that these types are really just ordinary user-defined functions. And yet we're going to do some form of static verification. The type checker, which we call the verifier, is meant to say that if the program verifies, then certain bad things cannot happen at runtime. And we'll still guarantee that. But all of this, and many of these type tests, therefore, don't need to be actually executed. But notionally, that's what the language does. A bit like Julia, actually, that we were discussing before, that a lot of time that in Julia, you could imagine it being done by an interpreter in which there's no compilation of time. You just do lots of runtime tests. Same with verse. OK. Now, the last big thing I'm going to tell you about in verse is that expressions and patterns are also the same thing. We're used to functions, well, certainly functional programmers are used to functions in which functions are defined by pattern matching. So you say f of pattern 1 equals right-hand side 1. F of pattern 2 equals right-hand side 2. So there's a notion of, and patterns and expressions are not the same thing. But in verse, they are the same thing. So the function form is function, that is lambda, expression. So the first expression is like the pattern, and the second expression is like the body of the function. So I'm not going to have time to explain this in one fell swoop to you, but it has a pervasive effect on the language. So let's see. Let me give you one little example. So one way to think of it is that this lambda, this thing that's spelt function E1, E2, you could think of as being an ordinary lambda, the one that you know and love, that takes an input I, somehow matches I against E1. That's this twiddly arrow thing, and then proceeds with E2. And then to understand what this means, we have to do a bit of explanation of what this I arrow thing might be. So here is an example at the bottom, function x colon int x plus 1. That means take an input I, match it against x colon int. How do I match it against x colon int? I'm just going to show you the output. If you run that matching process, you get this x colon equals int of I. That's all, right? So I'm not going to have time to explain really how matching works, except that I want to get as far as this, which is to say that the patterns, remember that first argument of function is a pattern, the thing that is matched against. You can put functions in the pattern. That's rather wild. You can imagine you might put tuples there and other pattern-like things, but putting functions there is pretty wild. And in fact, this particular one, which says function colon int colon nat, that, in a completely unmodified this is the very same function. Those two function keywords are the same ones, right? But the second one behaves like a type. Behaves like a type. Okay, I've got to wrap up. So, wanted to give you a tiny sense of what's unusual and cool about this. Types are expressions. Patterns are expressions. A verifier does a kind of conservative analysis to check that certain things can't go wrong at runtime. There's a whole lot more I haven't told you about in that it's really a functional logic language, not just a functional language. So there are things that look a bit like logical variables and unification that goes on. There's a whole effect system. There's a whole overloading system that you'll love because it's a little bit something of the flavor of Julia's overloading. There's stuff about classes and structs and transactional memory, on and on. And we're busy, writing why is this gone like this? I don't know why. Sorry about the formatting. We're writing a formal language specification and trying to distill out a tiny calculus that we can communicate to other people that contains the essence of the language. Writing papers, building prototypes. And if you want to know any more about this, I gave a series of 4, 60-minute lectures at the Oregon Programming Languages Summer School, and here's a link that you can find more. Okay, any questions? Yep.
Thanks. So you have a very ambitious target for adoption of this language. How do you think about communicating these sorts of language ideas to a very, very wide audience, like a unprecedentedly wide audience?
Yeah, that's an excellent question. I think it's beyond my expertise, really. At the moment, I'm at the stage of trying to figure out, I've got to figure out what is this language at all and how can we describe it formally. Now, Tim is very convinced that once we figure it out, it'll be easier to communicate and everyone will understand it. And I'm agnostic about that. I just don't know, because in sum total, there is something quite big and ambitious going on. So it may be that what we do is we discover a lot of interesting ideas and end up distilling them in different ways. So I don't know. But Tim is totally, this is the language of, it's the language of mathematics, it's the language in which everybody's going to want to write programs, they're just going to get with the program. And you've got to give it to him. He has not just passion, but also expertise. But I don't quite know how to work out. Go.
But actually maybe connected to this question,
yeah.
Thanks for the talk. But I think typical language design is focused, or has been focused on designing a language for humans, mostly to reason about.
Yeah.
But now we actually live in a world that a lot of code is being auto-generated, right?
Yeah.
And I was curious where Verse stands there. Maybe for this large audience, it would be way easier to actually not to code, but to just prompt or explain their ideas, which will be generated into Verse. But I was just curious, how do you see the language design in this new era? Maybe Verse is
okay, man, that's a big open-ended question, because for a start, LLMs have only 6 months ago, they suddenly started generating code that was actually, so like 6 months, that's all, right? We have as yet no clue, even about relatively simple questions like, does a statically typed language give them more leverage or more friction? Who knows? We're still working, and now, so that's one big unknown that we know nothing about. Another big unknown is, what is Verse and how easy will it be to learn? And then there'll be, how will LLMs and Verse, so the answer is, I have no clue of the answer to your question. Right, because you're varying 6 different things at once, all of which are large-scale unknowns in my view. Yeah, Ray, sorry.
So I might not have realized that the answer to this question was in the presentation. I might have missed it, but
I know that there's some degree of logic programming involved in the language, right?
Yes.
And I'm curious how that implementation works in the back end, because a lot of logic languages have a solver or something that is doing something in the runtime that is pretty complicated and specific to logic programming.
Right. So yes, verse is a functional logic language, but in fact, as it turns out, the functional logic, the actual sort of unification and running algorithms backwards doesn't play a very important role in the most fundamental aspects of the language. So I think the net will be that in most programs, most of the time, the evaluation order and everything will be predictable enough that the implementation in the back end ends up not having to do any unification or logic variables. But if it does, then it'll just be create a logical variable and do some unification, not a complicated solver. So what we will not do is you can write a verse program that says exists x, x equals x times x. Now, there are solutions to that, namely 0 and 1. We are not going to find them, right? So we're not going to do constraint logic programming at all. At most, we'll do Prolog-style unification. And most of the time, we'll expect not to need to do that at all.
What is
yeah.
yeah. Sorry, it's weird to hear you. What is it about video games that necessitates this?
Oh, like I said at the beginning, nothing about video games necessitate this, I believe, right? I think we could use a more conventional language for video games. But like I say, Tim just believes, it's like when I tried to convey to you this morning, when John and I first learned about functional programming and lazy evaluation, we think, this is just the way that God intended programs to be written, right? It wasn't this is going to be more useful. It's obviously the right thing. And it's that level of technical commitment and passion that's in Tim's head at the moment. So, and so if it's the right way to write programs, it'll be good for games too.
I love it that they pay you for that.
I love it. I think it's completely stunning to be working for a games company designing involved in a really quite substantial research project, a programming language design project. It's amazing. Yeah.
Yeah, a quick question. The way you handle the failure, don't you feel that you can make the debugging much harder?
Oh, what's debugging like? Oh, I have no clue. Yes. So, I mean, when you change it, what's debugging Prolog like? I have no practical experience of doing that, or Icon or Snowball.
Yeah, it's very, very difficult.
Okay, so we're going to have fun. So there's going to be lots of material for lots of research. It's like, I'm coming here this year, instead of going to ICFP, which I've been to every International Conference on Functional Programming, which I've been to every year for 30 years. But I'm coming here this year for a change, but also because in programming language space, all the low-hanging fruit has been gathered. But verse and this territory that Tim's mapped out is like full of low-hanging fruit, like debuggers for even simple debuggers. Yeah, go.
So it sounds like a lot of the interesting ideas in this are coming from Tim's mind.
Yeah.
What is the process like talking to him and sort of getting this out of him? And I mean, there's quite a list of programming language people.
So it's very unusual. I've never experienced this before. I think Tim is sort of, in a certain sense, a genius, by which I mean somebody who has wildly original, technically substantial ideas, but has difficulty explaining them. So it's as it were, he can like teleport to the galaxy and say, we have to be here. And we're sort of, running around in space. Why is Tim over there? What's he talking about? 6 months later, we say, oh, now we realize. So in practical terms, we spend 2 hours a week with him on the phone. We have a 2-hour phone call. When I say we, I mean me and Kuhn Klaas and Leonard Augustin. So actually 3 people have all been involved in Haskell programming language development for a long time, and Stephanie Warwick and Ranjit Jala a bit, so some leading functional programming type researchers. 2 hours a week with the chief executive of a billion-dollar company who likes nothing more than to talk about denotational semantics and task key growth and deep universes. It is a very unusual experience. I don't think any other substantial billion-dollar company has a CEO like that. So it's, yes. So in effect, he's like the muse to the project. He keeps us thinking, and then we're sort of fumbling around trying to figure, how can we pour the concrete to make this a reality? Yeah.
Yeah. You open with everything about games, and then where I was expecting this to go was to talk about certain things about like, Haskell has all this safety and everything, but games need things like real time and soft real time. And there's this really difficult problem of like, how do you make sure that code is safe for real time and everything? And I didn't hear things
No,
about
none of
real
that.
time. Okay, so there's nothing in that area about like.
No,
okay.
nothing about real time, certainly. There is a bit about transactions, right? So I talked about STM this morning. So in Verse and this sort of UEFN ecosystem, the idea is we're going to, because in 3D virtual reality, there are interacting characters who have to, they can't both pick up the hammer, right? So you want transactions against the shared state. So the idea is, as I understand, I'm not involved in this part of the project, the idea is there will be data center scale transactional memory. That's pretty wild, pretty exciting.
That's wild.
That is the way. I mean, can we make it work? I don't know, but Tim is nothing if not ambitious. And that's great. I love that about him and about the project. And that, I would say, it is a really good way to coordinate concurrent processes, which is what 3D simulations are.
I see there's a lot more questions, but maybe these can be discussed like during lunch, as we're going slightly over time, or just with speakers.
I'm totally at your service, guys. I'm here the rest of today and all of tomorrow, including the evening.
And then I have one more announcement. For lunch, there's an ASML presentation going on at 1:45 in the Alta Mensa that you're all invited to.
Great. Good, thanks.
Thank you for the talk.
Handheld thing that
Hello. Hello, everyone. My name is Florian. I'm the session chair for this afternoon's general session in the tent. And before we start, I just want to encourage the following speakers, maybe during the question session, to already come to the front that we can have smooth transition and stay in time. And I'm welcoming our first speaker, Avik, with lessons in deploying Julia to production services. The stage is yours. Thanks.
Let's turn it on. Okay, welcome everyone to the post-lunch session on the first day. My name is Avik Sengupta and I work for Julia Hub. And my talk today is about some of the experience that I've had over the last 10 or so years creating Julia code that is deployed in production, serving external customers, serving large number of users, both in desktop and on the web, right? So I've been a Julia developer for quite a long time now. I've worked for Julia Hub for the last 10 years, and so as part of my job, me and my team, we've created in various contexts Julia services that are run in production today. So that's what my talk is about, talking about my experiences of me and my team. So I think the first thing to discuss is what does deployment mean, right? People deploy in many different ways. You could deploy to your private cloud. You could deploy to supercomputers. You could deploy to workstations or desktop computers or laptops, right? And that's a large gamut of products, a large gamut of experiences, right? And each of these have different requirements. You can also deploy things in, your code can be different things, right? It could be batch processes that are deployed on supercomputers. It could be long-running services that are serving requests from the wide internet. It could be desktop UIs. It could be libraries that are used commercially or in the open source. So there's a huge variety of things that you need. Also, there is also a huge variety of needs in terms of who you're deploying to. So you could be deploying internal services within your company. You could be deploying to the wide internet. And again, all of these things have very different needs, very different requirements. And so I will start sort of giving you a wide overview of all the different areas that you can approach and some tips and tricks to how to approach these situations. A lot of the things that I will talk about today, there are other detailed talks on those strategies within this JuliaCon. Some have already happened, some will happen today, some will happen over the course of the next 2 days. And I will hopefully point you to those talks as and when they are relevant. So what I'm talking about today mostly is going to be an overview with pointers to the details of various strategies that I can talk about, right? So if I were to summarize this presentation, as I said, there are multiple different routes and mechanisms that code is deployed. I have sort of a unifying idea that I'll go through for the rest of this talk, which is that, to me, deployment means running code on machines that you don't own, right? And that, as I said before, comes in various forms, but the common assumption is that this is code that you're running where your code hasn't run while you were testing it, right? And so the problem that we are trying to solve, in summary, is that any code has implicit assumptions on the environment on which it runs, right? And so they have assumptions on the operating system, the instruction set, the libraries, the dependent set, configuration files, all of that. And so for the rest of my talk, I'm essentially talking about how to abstract and mitigate these differences into something that can be a common set of tools and technologies for deployment, right? So the simplest way of deploying Julia code is, send a file to somebody. Write a .jl file, email it to your colleague, and I'm sure many of you have done that over the last few years, right? And that's the most simple thing. You don't have to worry about anything. Obviously, the downsides are for the person receiving it, they need to have Julia installed. They need to also have all the packages installed. And you need to tell them, this needs marquee version such and such or whatever else, right? And that's the problem, right? If it works for you, if you're working in a team where everybody has the same install set, fine, that's the easiest thing, and maybe you shouldn't do anything more. So that's sort of the baseline, right, of what we are, of what deploying means, right? That's the minimal viable product in some ways. A little more sophisticated that we always recommend you to do is, instead of sending a file, you send a project, right? You send a project that contains your source files, and it contains a project and manifest, right? And here where we come to the first set of tips that I want to talk about, which is that the recommendation is that for a library, you only have a project toml checked in, but for an application, you have the project and the manifest checked in, right? And the manifest is essentially the project toml expanded at a point in time, at a point of the registry that will ensure that all your users have the exact same versions of dependencies, of your dependencies and the dependencies of those dependencies. And so, that's the best you can do as far as freezing Julia dependencies, right? The user needs to have this correct version of Julia installed. So, if you have created this project and manifest with Julia version 112 and your user has 113, then, things will break in strange ways, right? There are a couple of things that are very new that help with that problem. One is that in Julia 113, you can store project and manifest files inside a source file, right? So if you don't have a project, you can just have a single source file, have the project and manifest inside. That's work that I think Christopher did a few months ago, and that's coming up. It is not in 1.13. Okay, I stand corrected. There's a PR for it. Hopefully, it'll be in there soon. The other thing is Julia. Again, this is work in progress, I believe, in Julia, where you can have Julia itself read a project and pick up the correct version of Julia to run. So you start Julia up. You start Julia via Julia, and you sort of give it a project file, and it'll run the correct version. And that helps with having the correct version of Julia with your with the people who are running your code, right? Right. So that's the simplest things you can do, and that sort of works. But I always recommend that if you're working in a group, you're working on a slightly larger project, always use a private registry, right? So whether you're doing development or you're deploying, it always helps to have a private registry. And in Julia, a private registry is actually a very simple thing. It's a Git repository that you can manage like all other Git repositories. There is a package called localregistry.jl that sort of helps you do that. But you can do it manually with PRs. That's, registries are basically simple toml files that are reasonably easy to manage. But you can use local registry to manage it yourself, a slightly more sophisticated way, and that helps a lot, right? So always have a registry. If you're working, more than 2 people, more than 2 projects, have a registry, and that helps immensely both for development and deployment, right? If you're running things on an HPC cluster, a few things to remember is that you typically should you should set your depot to a shared file system. You shouldn't have, you're not pre-compiling your code on every node. That's important. So, have a shared depot. Shared file systems are usually slower than the node file system, so you need to, plan for that. You should consider running with this thing called compiled model equals strict, which will ensure that if there is no precompiled file, then that code will basically break. So you're not, by mistake, compiling code on thousands of nodes. That can take minutes and aggregated hundreds of CPU hours, and that's terrible. If you have heterogeneous nodes on your CPU cluster, set a CPU target for your compilation and for running Julia. And finally, the last line of my slide probably has 10 talks on it, which is figuring out the correct MPI config, which I don't know how to do, but hopefully you know how to do if you're working on a cluster. But that's among the most difficult things that you would do when running Julia code on on large SPC clusters or supercomputers, right? Right. Moving on to a completely different strategy, which is when you're running on servers or on the cloud today, you would typically run Julia within a container, within a Docker container of some sort, right? Whether within Kubernetes or on a Docker Swarm or whatever, right? If you're using a Docker image, first thing to realize is there are public Julia Docker images. You should always build on top of that. So depending on what version of Julia you're using, you start with a public Docker image that's on Docker Hub. You should instantiate a manifest during build time. Don't leave it to runtime. So when you're building the Docker container, instantiate the manifest, precompile using pkg.precompile. Define CPU targets, again, when you're precompiling, because the machine that you're building it on may not be the machine you're running it on. So you need to be aware of that. What is the set of possible machines you would run this container on? And you should then, set the CPU targets. The default Julia CPU targets are actually quite conservative, so they work in most cases. And that's what the last line says. That's the default set of CPUs that Julia compiles to. But you may want to change that depending on what you plan to run on versus what you are compiling on, right? Those become different. If you're running on containers, remember that you're sometimes running on what Julia sees as a machine, which is slightly different from the size of the machine that the container is running on, right? So you have a node CPU and then a pod CPU. So your node might have 64 CPUs while you're running your Docker container on 4 CPUs, right? And so Julia has only 4 CPUs accessible and only a part of the memory accessible. And so sometimes that causes issues. So our recommendation is always a couple of things. One is to set a heap size hint. So you can do that now. Christopher will correct me about which version it is. I forget. But it should be around since 1.12, I think. So that ensures that if you're running a Docker container with a size limit of 4G on a node with 64G of RAM, Julia knows the correct RAM size to work with, right? Similarly, you should set threads explicitly if you're running on a Docker container, because Julia might see the number of CPUs in the node and not the number of CPUs on your container and get the wrong sizing. OpenBlast in particular has issues around that. If it sees the wrong number of CPUs, it'll give you the wrong thread count and take a lot more memory. Finally, always limit the number of precompiled tasks on Docker. Again, the number of precompiled tasks that Julia runs is based on the number of CPUs that it sees. And when you're running Docker, that might not be what the number that Julia sees. And so always explicitly set the number of precompiled tasks, right? So for production services, where you're running long-running services, you're mostly running Docker, and sort of remembering to do these things always, helps you when things go wrong in production, right? A quick aside on precompile tools, most of you probably know this already, but always have a precompile workflow that precompiles the code at build time, right? So when you're running your Docker container, ensure you have a precompile workflow. Precompile tools helps you create that precompile workflow, and that'll ensure that when your service starts up, things are fast and you're not waiting for pre-compiling, right? I want to talk about system images for the next 5-6 minutes. A system image is basically a serialized snapshot of a Julia session, right? And it contains a lot more things than the standard precompiled files contain, right? And that helps Julia load much quicker. And a sysimage is not a very strange thing because Julia always comes with a system image containing base and standard libraries, right? But what you want to do for your workflow is to create your own custom system image. Custom system images basically solve the compile time latency. So for example, modeling toolkit famously takes 5-6 minutes to compile. Or when you first add it or when you first use it, it takes a long time to compile. And then even when it has the precompiled cache, the second time you load Julia, it still has to load some of that cache, and that it still takes, in this case, 3 seconds, right? But if you use package compiler, which is the tool, Christopher's tool that helps you create sysimages, custom sysimages, using package compiler, creating a sysimage for modeling toolkit, for example, loads it in almost no time, right? So you get even faster than cached loads. It should be instantaneous. It's not always instantaneous because of, depending on what else is happening, but it's much, much faster than not having a sysimage. So create a custom sysimage, and there are various strategies on doing things on top of sysimages, and I'll talk about that in a second. But to summarize, custom sysimages significantly reduce compile time latency. It needs a C compiler on the build machine. You need to use the same version of Julia to load it, so that's the downside. Artifacts, right? So DLLs that are part of your package need to be downloaded separately. The sysimage only contains Julia code and its dependencies. It doesn't contain any native dependencies, right? You also have to build for every OS. There is no cross-compile facility yet, and it takes a long time to create, and the results are pretty big, right? So you are easily creating gigabyte-sized files, although in the last 3-4 months it has significantly improved, but it's still a big file, right? So a package compiler also has a facility to create an application, and this, it takes the sysimage and all the native dependencies. So as I said before, with just a sysimage, you have to download the artifacts. The package compiler can build an app image that can, bundle all the artifacts together for you. And taking this idea a little further, you had a talk in the morning about App Bundler that uses some of these ideas, but also then adds the ability to create installers, so MSIXs or package bundles in Mac, and that's that's helpful if that's what you want to do. Also, after this, there's a talk about creating custom Julia distributions, where you create a Julia executable that instead of using the standard sysimage, will use your custom sysimage, right? So you could create a Julia distribution with Pluto included, for example, if you wanted to. And that's the talk just after mine. One thing to remember on sysimages is that any package that you put in a sysimage has to be relocatable, in the sense that the file system that the package sees is not your standard package file system, right? Because it's compiled into a big file. So you have to worry about what that means. And most packages in the Julia ecosystem are now relocatable. But if you're writing a package, you have to worry about when somebody takes your package and compiles it to a sysimage, does it work? So that's something to worry about for package authors, right? Going one step beyond, this is new in the Julia ecosystem over the last year or so, is Julia C. I won't talk much about it because there is one Julia C talk later today. I'm sure there are other talks about that. It creates standalone binaries. that can be small, and the key innovation is trimming, right? And Gabriel will, I think, have a talk this evening about that. So, Julia C depends on libjulia, but I won't, how to use Julia C. Let's skip that. Let's now talk about considerations for long-running services, right? If you're creating a web application using http.jl or Genie or something like that, what should you do? One is that, package latency in Julia, you have to worry about it, compile latency. A few ways to handle it is, have a very good precompile workload that compiles your web application, when you're creating your container, for example. The second is warm-up requests, right? So when you start it, you have a client that then, hits that service with request and precompiles it before your customers hit your service with requests, right? As of today, I would not recommend running Julia services on the open internet because not many people have done that, and there's some amount of unknown risk. But also, if you're running a web service, you absolutely should pay attention to package vulnerabilities. And again, there are a couple of talks tomorrow, I think, Friday, where Matt and some of my other colleagues will talk about, how vulnerability detection and analysis works within the Julia ecosystem, right? Lastly, considerations on cloud-native usage. A lot of you are running things on AWS or Azure. You should look at the AWS and Azure packages that provide interfaces, hooks into these platforms. You should also probably consider running it in Kubernetes if you have large-scale services. And there's a package called kubejl that basically wraps all of Kubernetes services into a Julia package, right? And so one thing to remember on AWS and Azure is that memory is a bigger cost on public services than CPU. And Julia processors generally tend to take larger memory access than sort of Go services, for example, or native C services. So that's something to consider, right? How do you size your containers? You should consider Julia's memory cost. One thing to mention here also is that the memory cost of Julia for precompiling is much larger than runtime. So, again, try not to precompile on an AWS machine, and try not to precompile while your service is running, right? So you can size your machines much smaller if you don't precompile on your runtime machines. That'll save you a lot of money, right? So I think that's about to the end of time. We have a few minutes for questions. So yeah, tell us your stories. If you've had any experiences around this, any questions, happy to answer now.
Thanks.
Yes, there are a couple of questions on that side.
Hi. I have a question about running the Julia on Kubernetes.
Yeah.
So would you say each Kubernetes represents like a worker with access to like 20, 30 virtual cores, like through the distributed GL package, or would you recommend that each Kubernetes container is just like a single worker? And what do you do with load balancing? Let's say you have a big task. What do you do then?
So that's a good question. I think the answer very much depends on your workload. So, we have a platform that the Julia platform that we allow running Julia processors on Kubernetes. And we allow the users to choose what they want, right? They're either a small set of large machines where Julia is multi-threading inside each machine, or a large set of small nodes where Julia is running single-threaded, and then you're running distributed.jl tasks across it, and that's a strategy that is better for some workloads than others, right? So I think you have to choose based on what your workload is and what, in terms of load balancing, I think most of the work that we do, we use distributed.jl for this work, and distributed.jl has its own sort of load balancing technique. There is also Dagger, I know, which has sort of separate set of distributed primitives and load balancing. But that's, I think, at the application layer mostly, right? Yes, hi.
Thanks for the talk. You mentioned earlier that the Julia process doesn't know about the actual amount of memory available. Yes. Same for CPUs. Is there some fundamental block for this? Because it's something that can...
No, I believe for memory it has been fixed recently. Again, I don't know which version, but now it gets the right memory. But it's a very sort of complex thing because you never know where it's running on and what the situation is. Is it root Docker or non-root Docker, or whether it's some other container?
Because even heap size hint is a hint.
Yes, it is a hint. Absolutely, it is a hint. But it does help. Like, our experience is that running Julia services, one of the things that our support team is pinged most is ooms. And using this reduces ooms quite a lot. Still happens sometimes, but it's not uncontrolled as much as it used to be.
Maybe just another question. Something we've been facing or having trouble with is handling of signals of Julia. So when you want to close your pod, when you want to close your service, there's no elegant way to do it right now?
Yes.
Is there some...
I don't think there's an easy answer to that. I think that's... I don't know, maybe the cancellation work will help that Keno's been doing. So that although it's not directly involved, but I think it might help. I think it's a longer conversation with the compiler team, which is somewhat beyond my skill set. But yeah, no, I don't think there's an easy answer to that right now.
Could you just maybe quickly talk about the difference between using like the AWS JL and the Kuber JL versus just using Julia Hub itself?
If you would like to use Julia Hub, you are most welcome. I think we make it much easier to run Julia services on Kubernetes. So you can just click and drag and get 100 nodes. Obviously, if you are running your own scheduler, you will need to use KuberJL if you want to interface your scheduler with some Julia code where your logic lies. You don't even need AWS.jl and KuberJL if all you're doing is you have some code that you have Dockerized, and you can use standard tools, right? KuberJS is useful as if you want Julia involvement in the scheduling process, right? And most of the time you don't. So if you just have Julia code that starts up, does some work, shuts down, you have a Docker container with it, you don't need any of this, right? Standard tooling will make it run.
Hello. How can you comment on memory usage when you're creating CC images and how you?
Sorry, I can't see you. Where?
Can you comment on memory usage?
Yes.
When creating CC images and how you resolve these issues in practice?
Sorry, can you say that again?
Memory usage.
Yes.
How many RAM you use when creating CC images with package compiler, for instance? Can you comment?
So a lot, right?
3 times the use size. 3 times the use size.
I think, yeah. So if you think your process needs 4 GB, while compiling, you should keep it 16 GB, right? 3 to 4 times it'll need while compiling. My experience is that Julia processes will run in 1 or 2 GB, but 4 GB is like the minimum for a reasonable sized Julia machine that's taking requests, right? So I would say 4 GB minimum runtime, 16 GB minimum while pre-compiling, right? If you're compiling modeling toolkit, maybe 32 GB. But I think 16 GB is okay for modeling toolkit as well. But the larger your package, more RAM you need, right? Are we out of time?
Yes, I think.
Thank you, everyone. Thanks.
Again.
And I'll hand over to Joris.
Yes, and the next talk is by Joris about building and shipping Julia distributions. Go ahead.
Hello.
Yeah. So not just Joris, also Paniotis, but he can't join just yet, but he's over here. And so today, as Avik already mentioned, we'll be talking to you about how to build and ship your own Omakase Julia distributions. So some of this might maybe even look familiar a little bit already, and that will be because about 3 years ago, at this very same conference, I think it was in Boston, Vector Spasada and I gave a talk about how we were shipping Julia packages using system images to improve performance. And at the time, we called this a mostly contained and relocatable solution to being able to ship performant packages to our users. Now, obviously, in 3 years, a lot has changed, so have our needs, and that's sort of what brings us to today's talk. So what are the primary things that has changed is that, especially over, I think, the last 3/4 of a year, what we used to ship was called Julia Sim. Since about, I think, a year or two now, we've been working on this project called Diet Studio. And Diet Studio is a project, or it turned into a product that you actually download. So where previously we were shipping things as container images, just putting them up on our platform, which worked great, I can't ship a container image to a user. Now, some other things that have changed, right, is that our users are primarily mechanical controls engineers, which, I know all of you are very well versed in Julia, but not everybody is. So they're part of our audience. And the promise that Diet Studio gives people, right, is just Julia plus SciML without sort of the learning curve that you have to go through. So the difficulties that this brings is that instead of running on our platform, this now runs on their machines, which have different operating systems, different memory usages, or different memory capabilities. So the container images that we used to ship, they were relocatable to a certain extent, but they needed additional tooling to be able to run. And we've shipped that for years, actually, that way. And so we don't want that preconditioned. We don't want to have to put that precondition on our users to be able to run these distributions that we ship to run our product. But before we go further, I think a good thing to sort of think about a little bit is like, why were we doing this again? And I think this is actually rather important. I mean, I know everybody's looked at time to first plot and things like that, but I think we have some pretty damning answers. Sorry for the phrasing. But what we see currently with our diet distribution, right, is if we just do this thing in the stock Julia, just do a simple plot, run an analysis, do a simple plot, it takes about 60 seconds. Just start Julia, load a package, run the analysis, go to a plot, it takes a minute. If you do the same thing within the custom distribution that we build, it takes about 3 seconds. That's a huge difference that a user will really notice. Now, to be fair, the container image did this as well, and that's what we built it for. But again, we can't ship that anymore. But there's another important caveat that when we're running on a user's machine, before we can even get to that 60-second start Julia and run an analysis and a plot, they actually have to sit around and wait for at least, I'm going to say at least half an hour of PKG instantiate, precompile, et cetera, et cetera, et cetera. I'm saying at least because this 30-minute mark here comes off of is a measurement on our CI machines, which have, I don't know, I think about a terabyte of memory. So it's not entirely, no. Does anybody have a terabyte of memory in their laptop? Yeah, figured. I don't. I have 16. Doesn't help. You can't build the distribution on 16 gigabytes, by the way. So yeah, the primary reason why we are doing this, I mean, the 20x is a nice number, but for us, the key benefit is that we want a product that we built on top of Julia to actually feel like a product and not the first experience of a user who installs Diet Studio going, OK, now I'll wait. OK, and with that, I'll hand it over a little bit to Paniotis.
Hello, everyone. So this morning, I'm Panagiotis, by the way. This morning, we discussed in the first talk after the keynote that compilation is slow, and we were discussing why. Like, do I need more? Do I need the new features that make everything slower? That's a valid question, I think. And there were complaints that Julia is becoming slower. Now, I will argue that Julia is not slow, right? Julia is really fast, but it's really fast at one point after that. And before that point, you have great power. And with great power comes great responsibility. And while everyone in this room should have this power, everyone outside this room doesn't need to have all this power at the beginning. So your users do not need like all the general, everything that Julia can do out of the box. So they basically want an opinion, right? So the idea is that we pin what we think users need, and we give that to them. There is an opt-out, obviously. So that traces back to a very fundamental question of what is Julia, right? It's a bit of a philosophical question, and I know that a lot of people have a lot of different opinions on what is or should be a Julia. Like, is it the language? Is it our implementation? Is it an interpreter? Is it a compiler? Is it more like GCC, or is it more like the GHC, like the Haskell compiler? Or, like, is it a REPL? What is Julia? But I think that's the wrong question to ask, even though it's on the right path. The question we need to answer at the end of the day is, what is Julia to your users? And if your users do not know what Julia is by the time they are installing your product, then it doesn't really matter like what they think of what Julia is, right? They just need to run something, right? They just need the thing to run. So yes, recent releases made the compiler, like the core compiler, better. Like it's more lean, which means less things are in, and you can do more things like trim and make small binaries, and all of these are great. But your users, at the point where they are using the product, especially for the first time, they don't really care about the lean things. So the question, yeah, and I will include this statistic from fonts. Last year, basically last April, we benchmarked the packages across Julia 1.10, 1.11, 1.12, and everything gets slower, right? And I think the reason why everything gets slower is that you start earlier at the compilation pipeline. So you have more work to do. Now, the same experience was amplified at the Dyad workshop where we got a bunch of potential users in a room, and it took 45 minutes last May to get them started. That is, install Julia, resolve the packages, and instantiate. Like, it took 45 minutes on average. Hopefully, we could talk our way out of it, but that's not a product. That is, that's not what we want. And when you ship a product, ideally, the first experience should be something quite fast. Like, not instantaneous, but, I don't know, 8 minutes is, 2 fair dice rolls. So my point is that the user should not start at the beginning that Julia allows you to. They should start right where your product ends. And that transforms the previous question of what Julia is to what your user's standard library selection should be, right? The standard library as a concept in Julia is not well defined, and we've discussed this with Christopher. Most of this work is Christopher's work, by the way. We're just showing it, and yours. But the concept of a standard library is not well defined. That's why we are exciting things out of the main systems. Like, what the standard library is not well defined, I think. But my point here, like what I want to communicate to the world, is that what your users experience as a standard library is your responsibility, right? So we made a distribution out of this, and someone could make a Mackie or a Turing or a Jump distribution, and really every company that uses Julia professionally, I think you should bump the user to the point that they just use your product. For the same reason you don't compile Ubuntu every time. And with that, I listen to yours.
All right. And so that's basically where we get to the point about, we have this word in the title of our talk, omakase, and this is where we really start bringing home that point, maybe. Or it's a very bad analogy. That could work as well. So for those that are not familiar with what it is, I mean, I've never been to one, but an omakase restaurant, right, is where you basically, as a customer, sit down at a chef's table and just go, you give me whatever you want, right? Whatever's ready, you basically get no choices. And in this particular case, you can be the chef, and your customers don't actually, or they get some choices, right? But you significantly reduce them, as we'll see later. So the point, right, is that, as Panagiotis just brought home, is Julia defers decisions on purpose, because it is very generic. It allows you to do many things. It is many different things to probably every single person in a room. But a product means, if you're building a product, you need to make decisions because you need to reduce the space. Otherwise, you end up just handing your users a toolbox. So let's cook some things. So we'll start by talking a little bit about what our ingredients are. So what do we actually ship? Right? So we ship about 14 packages that we actually care about, which are our component libraries, our first-party toolbox like Diet Model Optimizer, Diet Control Systems. Those are the part of our product offering. Right? These are the packages that we really care about. Now, 14 packages is not that much, but unfortunately, or fortunately, almost all of those depend on the SciML ecosystem, which means you bring in about 421 other packages that you have zero control over. And additionally, those bring in about 100 binary wrappers. So the point is, you don't, as a chef, you don't actually choose 421 of these things. You choose 14, and then you inherit a bunch of the rest. With the upside, or actually or probably more of a downside, is that they all need to agree on a common set of dependencies that they can work with. Otherwise, your thing is going to blow up, right? And that's a promise you effectively have to make to your users, because otherwise, they keep having to reinvent it for themselves. Now, the box is also pretty big, as Avik already alluded to. He was showing a 1.5 gigabyte system image. Do you think we can do better? Of course we can. Over 2 gigabytes. This means we've run into, again, we need to thank the core team for this as well, right? This wasn't possible until I think like 2 years ago. You couldn't definitely not go, I think until 1.11, you couldn't go over 2 gigabytes. On Windows, you still can't, but we have different solutions for that now, which I think are in 1.13. Christopher's nodding slowly. So when we were building these distributions, one of the first things that you hear when people building a system image, people go, oh, but you're pinning, right? Because anything that's in a system image, you can't replace it anymore. Like it's there, it's fixed, the Julia code's baked in, you can't swap it around. But given what we've been saying, we will argue that pinning is actually the feature, right? As I just alluded to, a large component of what we build, a large component of our product, is the SciML ecosystem. Now, not sure if I think the talk is tomorrow about Chris and his bot army of automation. SciML moves fast, like really fast. And it's also why it's good. Like it's very, very actively developed. The problem is, occasionally it breaks. And then you end up scrambling, having to re-resolve, make sure that your packages actually work. That's not a nice experience. But it does mean, because it moves fast, right, the combination of everything that works is a moving target, and it needs to hold for every single one of your users who, if they happen to run resolve at a slightly different point in time, they get a different set. So in this case, when we're building these distributions, we find that set once, and then we hand it over to our users. And that's a gift, or we consider it a gift, right? Now, that saves you a lot of time, because you're not waiting for pre-compilation, you're not having to figure out which version depends on what version and what doesn't work. They just get a combination that we've already vetted to work, that somebody else already stood behind. And in our case, I see him over there in the back, like, I think, no. Doesn't matter. So like in our case, right, like one of our colleagues, Oscar, who sits much closer to the SciML ecosystem, can keep track of what does and doesn't move and which combinations will work and won't work, where previously, when Venkatesh Prasad and I were building a lot of these, the previous system images, a lot of that came down to us, and we only noticed all the way at the end. And that was not necessarily problematic, but it was definitely frustrating. Now, as I said, I just try to sort of sell you on pinning, and I'm a huge a proponent of pinning dependencies no matter what. But of course, there's a bill, right? And we already alluded to that. Anything that's baked into a system image is a constraint that nobody downstream can relax anymore. You can add additional packages to your environment, but that's it. They're a default that nobody else can derive anymore. I'm looking at the wrong slide. So the bill there is, like, your users, they have to pay for it. Like, they can't change, if they need a different version and it's not just yet, like they see this new cool modeling toolkit feature, yeah, sorry, it's not there yet. So you'll have to wait until the next distribution, if we decide to upgrade, which we don't always do necessarily. And the larger downside, I guess, is it also costs disk image, right? Because now instead of Julia being able to spread out the different package images and deduplicate them between different installations, you get one giant blob of Julia code in a 2 GB file. So yeah, that starts eating up disk space, so you'll occasionally want to clean up your distribution. Yeah, your computer. So that basically means that this is where the trade-off comes in, right? This bill ends up being a selection criterion for when you are composing what it is that you want to do. And the tests that we primarily use for this is not necessarily, I just told you, like, modeling toolkit moves fast, so that's why we're freezing it. But the test is not necessarily velocity. It's more about maturity, right? Because if something moves very fast, for instance, you have a very new Julia package that is just completely not settled yet, you explicitly do not want to put it in a system image because you might find a bug tomorrow, right, or a big one, or add new features. That means building an entirely new distribution. Right? So just said, SIML moves fast, it goes in, we just don't update that fast, right? Sometimes if we know, like, a release is broken, or like one of the packages in that whole ecosystem doesn't quite work well, or it has a particular problem, we can keep it back. Yeah, anyway. So things that are fast-moving and mature are exactly the things that you want to bake in. And things that you don't include is sort of a maturity judgment, right? It doesn't mean it never goes in. Like, it just put it a little bit on the back burner. So yeah, those are the ingredients and what comes back to haunt you. Then talk a little bit about what happens in the kitchen, because this is a thing I have to tell people again and again and again. A system image by itself is not redistributable. It's not relocatable, right? Like Avik already mentioned something about the packages that you put into a system image need to be relocatable, right? It's where you have packages like relocatable folders for, because if you hard code a path in there, when it compiles, it actually compiles in the path that is on the build machine, which won't exist on your user's machine. But even that is still, it is still just all Julia code, so that's not enough. You don't have any shared libraries, right? There's no artifacts, there are no data files. Like, none of these things, if I hand you a system image, you'll have on your machine. Normally, you have instructions on where to get them. And these are the things that we have to bake into, right? If you just ship one of them, you don't have it. And so you have to make sure they're all combined. And in our case, right, an app, which is one of the options that you have in package compiler, is also not sufficient. You can have multiple executables or multiple entry points there. But for us, we actually want the REPL. So we do want to still be able to have Julia act like it is Julia, hence custom Julia distributions. And so a very important part for us, additionally to that, right, is that you don't just want to strip all the source image, or all the source code, which is, I believe Avik also just mentioned that, where a common theme for using system images is that you can sort of obfuscate your code so that people can't look at it, which is fine. But in our case, we ship a lot of packages where you should be allowed to read the code. But even more importantly, there are our Dyad component libraries, for instance, are Julia packages, but they also still have the Dyad code in it. And if you don't ship the Dyad code, the first thing our software will do is it will immediately crash because it can't find the assets that it needs. It can't find the model code. So it'll go like, you think, oh, I'll build a nice RLC model. Let me add the electrical components. Like, where are all my components? So we have to ship those. Otherwise, it just can't work. So our product is not complete. Yeah, so going back to those numbers I showed you earlier, like for us, our current distribution is about, all in all, it's about 3.5 gigabytes large, compresses to about 1 gigabyte. The system image is 2 gigabytes worth of that. But the other 1.36 gigabytes is all the other stuff you need for the product to actually work that a user would otherwise have to figure out how to get. And then, of course, you have to check what you built on every platform you ship to. And one of the most common things there is if you try to build on what Mac or Windows, well, you have to sign it. Otherwise, you cannot. Oh, yeah, 5 minutes. OK, I'll speed up. Otherwise, you can't even run it. So here's the good news. You can actually build one today based on the. We looked very, put up the big eyes and looked at Christopher and went, can you please build this for us? And he went like, sure, I'll put it in package compiler. Now, it's not merged, but I mean, we've been using it for a while, and it works pretty well. And on top of this, to make it a little bit easier to do, because there's still a lot of stuff you have to hook up, as of today, we also have a GitHub action you can use, which wraps this work, and it effectively becomes a 2-step process to build a. You just ship a project toml, a manifest toml, and you define your GitHub workflow, and you're off to the races. Now then, very quickly, I'll sort of speed through this and hand it over to Panagiotis. You have a distribution. Now what, right? You have built one, but as Avik was, you can ship, like you can give people files. How are we going to give them files? How does anybody get it? It's like, well, that's what we thought of this. Like, hey, Julia itself uses Julia up, so can we? And yeah, we can. Like Julia up just speaks plain HTTP GET. Just needs a couple of different files to serve up that you need to serve up. You need to serve up sort of the version of your database. You need to serve up a database of, if you've ever done like Julia up plus 112, that there's something that translates 112 into the actual distribution that gets downloaded. That mapping you have to do, and you have to provide your tarballs. And that's it. And you can actually do that serve them up quite easily. You just take 3 files, one of which is just a number. You just stick that version number in one file. The databases also there are JSON files. So they have that same version number in there. Then you define what the available versions are. Those are basically all the tarballs, all the distributions that you have available. And then you define a bunch of channels, mappings that allow your users to install it. So I have a very quick video of how that works. So you can go home and watch it work. Now, this is going to take a while, or it actually doesn't take that long. I'm going to skip over the last part, I think, because the unzipping takes too long, and I don't want to waste time on it. So this is not actually downloading. There's something else going on. Claude thinks it has to do with decompressing, but we'll see. And then once this is done, you have a Julia. So very nice. I'll let it run for a bit. But so the only thing your machine, like your customer, actually needs is, well, nothing except for Julia up, which they need anyway when they have Julia, when they need to use Julia. And you can install Julia up pretty easily. See, now it's available. And we can also just run straight up modeling toolkit straight from it. And it's really fast. Like if you try to do that with a stock Julia, it takes a lot longer to just print. So let me skip over that. I'll actually skip over a lot of this. Sorry. Like, yeah, there are some sharp edges. You'll cut yourself, but it's fine. They're not that sharp. We can work around them. So we went from something that was mostly contained to, we think at least, something that is contained, because now it brings its own depot, it brings its own Julia, which previously you had to do all sorts of magic incantations to make the container images work. They're easily relocatable, because we can just hand you a Julia up server and go, just install it. And yeah, it's that simple.
Yeah.
So yeah, I'll hand it over to Panagiotis.
Thank you.
Bring it home.
Yeah. So basically, should everyone build one distribution? My take is yes. Sorry if you disagree. But I think in every place where a user expects something to run fast, and if you want to serve that user well, you should build your own distribution. And if it only helps one person, the video that Joris just showed is the experience, with this custom distribution. So what we would like this to look, so given that everyone builds their own distribution, it would be very nice if Julia app would support, would have first-class support basically for adding servers. There are 2 knobs now that you can switch, and we do that in the Diet product. You can use it now. But basically, it would be very nice if we could do Julia app server add, and then we could basically distribute stuff. There is a discussion going on. It's pretty much frozen. This is a call for unfreezing this discussion. And I have been saying again and again that you should own what your user sees, and you should take the power back from the users. Now, I have this very weird slide that basically what I'm trying to communicate is that this is a social welfare decision, and I will close with that, right? The cost of opting out of the distribution for a power user is 0, while the cost of building, pre-compiling all the packages in something very big, give me that, it's much higher. So we should make the easy things easy, and that's the product's work, and Julia's job is to make the hard things possible. And with that, I'm
do the last thing.
Yeah, we have also this slide. We want to thank Julia Hub for this, because building the Diet product is what pushed this work through with the help of the core team and the compiler team, and that was a very fruitful collaboration, and that's what we have. Do you want to see that?
No. Speaks for itself.
Okay.
If you need 6 lessons, these are the lessons.
Perfect. Let's thank the speakers. And we still get a couple minutes for questions, so please go ahead.
This is a question I asked yours before. So basically, Diet distribution is like me shipping my own Unreal Engine for my own studio.
I'm not sure if that's accurate. It's a part of it, maybe.
Okay.
Because the distribution is just a subset of what Diet Studio is, right? The product itself is much larger. It contains a development environment. This is just the piece that powers the Julia section of it.
But to make your question a bit more generic, if someone is basing their product on Julia being available and running custom Julia functions, you probably don't want the user to precompile at all, especially if your user is not a Power Julia user. If your user is not in the room, consider making a distribution. If your users are all in this room, they probably don't need one, but you can do the math on this slide, right? It's a default selection, and I will close with this slide.
No.
No.
Okay. Just one quick question. You showed that you have to, host the static files? You have to host that on your own servers or something that it's going to fetch from? Is that kind of what you're showing? Because you're saying Julia does basic HTTP GET.
Yeah, you just basically, it's sufficient. And this is what we were showing sort of, I was using Caddy in this case. Mm-hmm. If you have those 3 files and just have a blanket folder on your drive, and you have the configuration for that server was very simple. It's just like serve these files. That's it. And so you just need the very specific paths where Julia Up looks, and you just point it to it, and then it will be able to find it. So you can effectively host it wherever you want. If you want to know more, by the way, so if I've understood correctly, there's going to be a poster at the poster session tomorrow that will dig a little bit deeper into how to run your own Julia Up server. Sorry.
I can say it. The Julia Hub platform already supports that. So
yeah, that's true.
If you want to distribute something through the Julia Hub platform, you can talk to Avik and Matt.
That's how we ship it, of course.
Yeah.
Okay, we would have time for one last quick question. Over here.
So in the distribution, you have many indirect dependencies. And how do you deal with these dependencies which lag with the compat bounds? And what can you recommend for people who will make their own distributions?
So you were asking about compat bounds, right?
Yeah.
So Well, it depends on, there's different use cases here. As also Avik said in the talk before this, as soon as you have a manifest, that's it, right? So you have to, the transitive dependencies get pinned by your manifest. Now, in some cases, that's not actually sufficient. So we do something slightly different where, because those top-level product packages that we have, they need to agree on a common set of dependencies, but they don't know upfront what those are. And we don't want to find out when we build the distribution. So we have a layer sitting before that that sort of locks down, that looks like what are all the transitive dependencies, locks those down, then publishes that, and then all the other ones have to agree that they still work. And basically at that time, if we know all the tests are passing on all the individual packages, we know they've been tested against this known good set, and then we can just go, okay, just bake them in.
Perfect, thank you. Then let's thank Joris and Panagiotis again. And we have now a 15 minutes break, and we resume at 3:45 with the next talk.
Yeah, that's Avik's fun.
Okay. It's 3:45. Our next speaker would be Cody. I haven't seen him. Perfect. Give you 15 minutes and 5 minutes. Okay.
Hi there, folks. I gave a talk similar to this. This will be introducing some new concepts, yeah. Hi there, everyone. We'll be talking a little bit about type piracy today, hopefully going a little bit further than last year. But let's see. It'll get a little bit messier and a little bit more technical, but I think it'll be a fun ride. The main, I think, first part of this talk is to go from, last year I talked a lot about invalidation freedom. And I think we kind of we took type piracy kind of for granted. We said, assuming that there is no type piracy, here are the things that cause invalidations in the system. Because I think we've all dealt with situations where famously type piracy is causing lots of invalidation and compiler thrashing, but it's maybe a little bit less obvious that there are lots of sources in the Julia ecosystem where people are doing perfectly innocent things and the compiler is invalidating out under them anyway. So that's what we talked about last year, but now I think it's time that we actually put type piracy on solid footing. Because I did put this big asterisk on it where I said, assuming no type piracy, but we don't really have a definition of what type piracy is. So it's not really possible for me to base an argument on it if we don't know what it means. So that's where we're spending today's talk. The main proposal is, I'm going to get straight to it because I actually think the proposal is oddly intuitive, which is just that we're going to say that a type is type pirating in the package foo if any of its concrete subtypes are constructible without referring to loading or using foo, essentially. And I think this is kind of the intuitive behavior that you see when you deal with a type pirated method, is that all of a sudden someone who didn't need to deal with your types at all is able to change what your types do. And so you're affecting dispatch for types that other people have already been running, and in a past execution somewhere in pre-compilation they did something different, and now you're changing that behavior. So the one direct consequence of this is that later we'll talk about some more interesting invalidation stuff, but this immediately tells us that for the very common case that you have like a concrete dispatch in Julia, forbidding type piracy guarantees that you won't invalidate. This also colors in some of what I mentioned a minute ago. Like there's this question of, oh, well, if Julia invalidates, even when you're following by the rules, why do people mostly run into issues with type piracy? The reason is because as long as you are fully monomorphized, which a lot of people have been told to do, like make your code not only type stable, but totally it's concretely typed almost everywhere. In that case, you don't suffer from these other problems that Julia has, as long as you don't dare to use an abstract type, let an abstract type get into any of your actual code types of your methods at runtime. If you do, then you'll run into other invalidations. And I think that kind of demonstrates this like bifurcation of different invalidation issues we run into, and probably why we tell people to so aggressively try to get their code to infer better. Anyway, the main proposal here is that we're going to have to, first of all, have a notion of the package graph. Julia does understand the images it loads, but we need a slightly different definition of the actual packages as a unit. These might be grouped into a system image, for example, or you might be loading multiple at once. Anyway, the main concept here is that every package you load has a root module, and we're going to be using that root module as the identity of that package. So 80 types here is basically what you would intuitively think of as your 80 types package. But the idea here is that type piracy keeps being meaningful, even if you change those boundaries and move your images around. Anyway, the idea is that as you go from the top down to the bottom and you start loading more and more things, it becomes possible basically to spell more types. Like if I have a vector and I load styled strings, now I can make a vector styled string. And I couldn't do that until I loaded styled strings because I have no way to refer to the name styled strings. And so the main thing about this definition is that it's a little bit of a cop-out, but I think in a very Julian way, in the sense that this definition is very precise. It says that there's some set of concrete types out there that first become spellable or can first be instantiated once this package is loaded, but actually checking whether or not a given abstract type falls within that set is something that we might have to approximate, because the compiler might not be able to tell you, like, oh, this complicated abstract type happens to rely on a package, AD types, but it looks like it kind of doesn't. I'll give you some examples here. So, for example, vector styled string was the one we just talked about. That one requires both base and styled strings. And the idea here is that you can just go ahead and add multiple packages if you need multiple sets of types to construct a type. And then the problem here is that one of the cases that the compiler has to reason about, where it gets a little bit approximate, is the case where you have union styled string, abstract string. Well, I wrote it down this way, but the moment that type gets created, it's going to turn into vector abstract string, because styled string is an abstract string, and so those just merge together. And so in reality, because of that like absorption behavior, this did not depend on styled strings. So there are subtleties here that I'm not going to get into today, but a correct implementation of a sound predicate that would say, what is the package type corresponding to a given type that defines its type piracy? If the compiler wants to check that, then it has to consider cases like this union. For our cases, it mostly means if you have two pieces of a union, you're going to need to either prove that one can never subsume the other, or even better, just prove to me that they're directly or non-overlapping, which is pretty common for very different kinds of types. Like union, something, and nothing is very often very conspicuously orthogonal. Anyway, then we have other cases that are a little bit more interesting here. Surprisingly enough, this is very, very close to being what I wrote on the right-hand side, where we get to have styled strings and AD types here, even though you're using the less than operator. Almost every subtype of this thing does require using those packages, except for, one quick comment here is that the key equation that we want this relationship to follow is that if we have a less than colon p, meaning one package is visible from another after getting loaded, like it has a using connection to it, then we want to make sure that if you're able to subtype something, then that implies that you must have brought in the packages for that other type to describe it. So this is the key correctness requirement for our type piracy relation if we want it to mean what we talked about on the previous slide. Anyway, there are some gremlins though, because unfortunately there is exactly one subtype of this last entry which breaks that rule, and that is when you replace styled string with bottom. And this is a perfectly valid type. This is a concrete type. You can construct this. People have reasons to construct these. Vector union, vector bottom will get created occasionally during widening when you're starting out and you haven't yet accumulated all the elements that you want to include in some unknown vector that you're kind of growing to fit your collection, for example. So we don't want to just forbid these types like we did with tuple bottom. But at the same time, I didn't need style strings to write this, so I'm not allowed to include that in my type up there. But I would really like to, because it feels almost every subtype in that is inaccessible until the moment that package gets brought in. So we literally have a single exception that's preventing you from being able to define pretty reasonable methods. And that's an unfortunate case. So there's no real good way to tell Julia that you don't actually want to define the method over that one exception. And there's another gremlin that's worth mentioning too, which is probably the other exception. This one is related to union empty brackets. The other one is related to tuple empty brackets, specifically as a degenerate case of var args. This one has a better workaround because you can just copy the t out of the var arg and put it before here. So you'd write this as foo, wow, I used foo too many times, but you'd write it as foo, and then var arg, and foo. And then you could make sure that you always have a capital F foo in there somewhere. Anyway, I think that the only two ways that we can solve this problem if we want to be able to actually have this guarantee from type piracy, which would be nice for the second half of the talk here, is that we basically have to either add a more complicated definition here, which I think is viable. I have a definition in mind, but I haven't 100% convinced myself that it's correct yet. But we can try to exclude these problematic types. So we can say if you happen to include a bottom in your type somewhere, then we call that a problematic kind of, or let's say an undesirable concrete type, one that we don't provide this guarantee about dispatch not changing. We don't provide a guarantee that the compiler can safely invoke that without it getting invalidated. So these are special types that are degenerate in the sense that we made it too easy for you to include them in your method definition. And so now we're no longer allowed to assume that their dispatch is going to be stable, at least if we want to have the guarantee that, like I said earlier, that concrete calls are not going to invalidate. The other option is that we could change vector abstract string to specifically exclude vector bottom. And there are a few different ways to do this. I'm not going to go into the weeds here. But if you're curious about it, you should talk to Kenno and me at some point during the conference. But the main idea here is to distinguish between the case that is technically strictly greater than the bottom or greater than or equal to bottom. And so in this case where you provide the bound at the location, you almost certainly want to exclude bottom. And so it might be possible for us to just switch to that behavior, perhaps. Anyway, that's really, I think, all that's required to define type piracy, other than checking the actual implementation of the predicate that I was talking about before behind this to make sure that the math is correct. But the basic thing that provides this strictness is that you can't really subtype anything in Julia until you bring in a package. Like to declare foo as a subtype of abstract foo, you need to have access to abstract foo, and so on. And that ends up being very robust, except for these couple of gremlins. So then the idea is that you get both runtime and compile time guarantees. Compile time never invalidates because the dispatches never change, and you know that behavior doesn't change for the same method call because you know that the dispatch tuples also have not changed at runtime. So there's both a well-behaved program perspective to this and a please don't invalidate me perspective. Anyway, I think that's about it for type piracy. So I want to get to my favorite part, which is part 2, which is the second half of this equation, which is how we, if we actually place an even stronger constraint and go all the way here to finishing my talk from last year, and say, let's shoot for invalidation freedom. What is the design that's required? How do we actually guarantee that Julia will just never invalidate as long as you follow some rules that I've defined for you and that I've implemented in Julia, so that if you break them in your package, it will tell you that you violated the rule. So that's our main requirement here. And the main thing that we're missing is something that I've been calling implementation piracy. And the idea here is that we have to, for things that are downstream, where you can go ahead, you can see the types that are related that you're subtyping here, but the compiler doesn't know whether to expect new types in general. And this is a big problem for methods like this. So I guess we'll start with the feature side of this, which is, by the way, I should be clear, this is just a sketch to try to explore the landscape here. I think if we were to introduce interfaces, it might couple with other things. We might choose a different design. We might try to have you define sets of methods at once. But this is supposed to be the minimal requirement for us to be able to achieve, don't invalidate me. Anyway, so the idea here is why use interfaces to tell you where new methods should be expected? Well, there's two reasons for this. One is that we need to tell the compiler somehow where methods are going to be or where they're not going to be. I'll give some specific examples about where that gets problematic now today. But then secondly, we also, once you tell the compiler, please expect new methods here, well, great. I mean, you told the compiler expect new methods, and it knows absolutely nothing about them. So the compiler can do what it degrades to. Last year we talked about like, oh, well, the compiler, if you load enough methods, will eventually just infer any and invalidate everything anyway. So why not skip there? But in theory, interfaces let you do one step better than that. And they let you say, expect future methods and require that they do this. And then the compiler can, in theory, try to hold on to, if not good code gen, at the very least good inference information. And that tends to be very important for Julia programs because otherwise, you have a tainted return type and it just funnels all the way down your call chain. I should, by the way, give a shout out to Jameson's proposal here as well. He has a fairly similar proposal that also mentions interfaces but focuses on more of a single dispatch version of this. So if you're interested in making the comparison, feel free to take a look at that too. I think there are some interesting ideas there as well that are definitely worth consideration. Anyway, I wanted to mention here, so why tie these two things together, or why is this so problematic? The main issue is that methods block dispatch, but nothing else does. And so doing something very innocent, like specifying a return type on the foo constructor here, I just wrote int out of habit. That seems pretty harmless. But the problem is now that somewhere that's calling foo had some type wide into any. And so now we're calling foo with any. And unless I have information that there's not going to be any other foo constructors created, there's no way for me to prove that that's not going to invalidate. So the compiler has reached a fork in the road. It has to either choose, I'm going to expect new methods, and I have to grab whatever type of information I can if interfaces are available, or just infer any, or I can assume that no methods are coming, and then I'm safe to go ahead and just infer through this one constructor. And now I know that I won't invalidate because someone gave me the guarantee that there won't be new methods in this area. And the similar thing happens here for like a string widening to abstract string, which is also pretty easy to imagine. And so the unfortunate part here is that it's just, when you end up in a part of the dispatch table with no other methods covering it, it's really the Wild West without a rule like this about whether or not you should expect new ones. And in both of these cases, it's like these are pretty likely to be internal methods. The compiler can, maybe 80% of the time, guess that you're not going to overload these and get good inference out of it. So that's generally what it does today. But the unfortunate thing is that whatever fraction of the time that we're wrong about that, when this doesn't end up being a private method, that's when we pay for it with invalidations. Anyway, let's see. Yes, so then what are the actual rules with this? Like, how does it all compose? The main idea is that, first of all, you can define the set of rules I'm kind of sketching out here as just one proposal, is that you can define an interface wherever you can define a normal method, and you can define a method if you own arg0. That is the key rule that helps with these previous cases. This one in particular, where you want foo to close, you own arg0 foo, and so you get to decide whether or not someone else is going to be able to extend foo as, it's not technically a generic function here, but it's effectively operating like one in arg0, and in the internal string transform case, it is a generic function. Anyway, so if you create a generic function or if you create a type, you get to decide whether or not the constructor gets overloaded, you get to decide whether or not the method gets overloaded, and if you don't specify an interface at that point, or you don't declare this to be extensible, it's never officially extensible after that point. So the person defining the arg0 type must decide that it can be extended. And then after that, you can go ahead and define either a method or an interface, whatever you want, as long as there's some covering interface that says that you're allowed to extend it. So in theory, you're looking at this package that you just using, and you see that it has some interface. You're like, OK, it's got a return type. I better implement this so I respect that return type. And you know that you have the right to implement that method, so Julia won't yell at you in this strict mode when you do that. And I want to mention as well, there's a really subtle point here about the difference between the types of rules in 2 and 3. The reason we have to go, why did we go for a single owner rule for 2, where we said, oh, there's this very specific position in the function that's different than all the other positions? The reason for that is that we need to kind of slice our dispatch table into orthogonal pieces. Otherwise, you end up in a situation like this one down at the bottom, where you have a convert method that wanted to be final. Let's say that there's some at final. No, this proposal doesn't include any final annotations, but let's say that someone dreamed one up and they wanted to be able to declare this piece of the method table final. But they didn't create convert. Convert is from some other package. It's from base in this case. And then someone else in a separate package defined convert any bar. Oh, well, that's a problem because I declared this final in a world where you can't even see me declaring it final. bar precompiles defines this completely separately from foo, and it's not until you load them both in the same environment that you discover that they disagree about how the dispatch table is supposed to be handled. And I think we really don't want to have that kind of behavior. And so that's why these rules specialize arg0, so you can just declare it right at the top before it becomes available to anyone. And then from there on out, you're just defining interfaces that specialize each other. I mean the function argument, correct. Yeah, sorry about that. Anyway, the key problem here is that you have like a coherence problem where you've got two separate packages that have their own idea about what's going on, and then you bring them together and they're like, oh, we disagreed. And that's not something we can enforce up front. Right. Okay, let's see. These are OR. These are OR rules. Yeah. So if any of these apply, you can go ahead and define your method. So yeah, in general, when you're creating something brand new, you've got automatic writes to it, and then if you're doing something in someone else's stuff, you get extended writes if they're specifically granted to you. Anyway, then I wanted to mention on the final front, weirdly enough, this does actually work with methods. So if instead of annotating this just at final as some label on general dispatch space, you actually provide a method, even if you defined the method here as like convert equals error and just made a useless method, the dispatch behavior of Julia treats this differently. It treats this as a conflict between the two methods. And so now in this case, you actually have somewhat better behavior in the sense that you didn't introduce any dispatches into bar's function space here. Wherever they overlap, there's a specificity conflict. And so Julia declares an ambiguity problem. So that almost actually helps to solve this problem. And I think the full version of this proposal that recovers as much inference information as possible allows you to effectively close over any method you define. So if you specialize, if you want it to be very, very strict, you could say that you can only define a method that specializes in another method if there's an interface that under it that you are implementing under. And if we want to be more permissive, then we don't have to do that. But the advantage of that is that if you call something that matches your method signature, then the compiler is free to go ahead and just infer through that one callee. It also has information from the interface, but now it can also go through your implementation, and it can use both pieces of information if it wants to. So that would be the maximal precision version of this, I think. But it's also the maximal annoyance version. So, and then the last kind of note I wanted to make here is that there are some technical details still to work out, one of which is, I think this is probably solvable, but there are lots of, on the topic of gremlins, this is the gremlin on the impl piracy side, which is that these two packages are loaded in parallel with each other, but the more specific than relation in Julia has some quirks to it. Generally, it works quite well, but in this case, it allows a method in one package to be declared more specific than a method in another package, which means that you're effectively stealing the dispatch from that other method. They do have a non-zero intersection, and you load package A and package B, and all of a sudden package B's dispatch is just taken, which is another violation of type piracy. So I think my recommendation here would be for us to use the package graph we defined earlier and the notion of the package type, and to try to say that if you're, sorry, I should have had a slide ready for this, but essentially if your types correspond to two different nodes here that don't reach each other, then we should not be we should not be giving them a specificity with respect to each other. And to be clear, specificity is always like this extra thing on top of subtyping. If you're a subtype of a method, then you automatically are more specific than it. The way we defined type piracy still allows that to work, but the cases that we're trying to kind of prune away here are the cases where you're not a subtype of that method, but you do intersect with it, and more specific than decided to try to decide that you deserve that dispatch, even though you probably shouldn't, given that you had no idea this package existed. You probably weren't trying to extend a method you can't even see. I think that covers the essentials. Yeah, let's conclude there and take questions. Thank you, folks.
Thanks. Perfect, on time. We got a couple minutes for questions. Let's start here.
So on this last example you're talking about is the idea that then
This one?
yes. So if I'm in package A, then I would not see the method defined in package B because I do not know about package B's existence. So there is no way I could be. I guess like subtyping tells it it's fine, but you want to add something else that's not just subtyping to make it not fine for my value to flow into a package that it doesn't know existed or something.
Yeah, it's the other. I think that's just about correct. The only thing is that it's a little bit the other way around. It's where you are specializing a method that you can't see. So the specificity relation looks at the right-hand side and says, oh, you were probably trying to specialize this method, and you couldn't even see the method. So the behavior here would be, do we award that dispatch to package A, or do we award it to package B, or do we choose that these are ambiguous and award it to neither? And I think the correct answer here is to award it to neither.
Oh, so like when in doubt, you should probably give an ambiguity error.
Right. Which is what we do very often.
Right. Like you may just get unlucky and one method be slightly more specific than the other and actually just get behavior that's not expected instead of an ambiguity error, right?
Yeah, exactly. But the idea is that that both inference and runtime benefit from the fact that you don't like if you choose to give that intersection to one person over the other, one person gets their expectations changed, essentially. It's also worth mentioning, by the way, that this is something that I think this is part of why Julia does composability does so well, is the fact that you can take a split like this, and then if you do have this ambiguity conflict between the two methods, you can just go ahead and in a package an extension between them, or in a package that uses both, you can try to resolve that, probably in an extension if you're going to obey type piracy. Anyway, I think our extensions are really key for resolving those kinds of diamonds. And it's something you can't do in Rust, which is what I think when folks complain about the specific orphan rules being strict in Rust, they're strict in specifically disallowing this kind of thing.
More questions over there?
So continuing in this way, this pattern I've seen a lot with convert, which was one of the examples. What I'm wondering is there a way out of this kind of ambiguity trap where, I mean, do we just basically tell packages you're not allowed to write methods for convert of this shape anymore? Because, I mean, I cannot just add another package which provides the disambiguation, because there could be multiple packages trying to do this. I mean, and they would be doing pipe piracy in any case.
Mm-hmm.
So what's the way out? I mean, like typical examples, CXX-wrap is causing us a lot of pain for invalidations because it tries to be nice and provide conversions. And yeah, I don't see, do you see any way out of this, or what would you propose?
Yeah, I mean, the idea here is that even if you might suffer from ambiguity errors here, you at least won't suffer from invalidations. So we're kind of halfway through to solving those two problems, I guess. Or at least that's where this proposal is trying to go. The real challenge with the trying to completely solve that problem and like predict that ambiguity errors won't happen, for example, is that it basically requires that instead of deciding how you're going to specialize in the two different children packages here, you have to dictate it from the very beginning, how you're going to choose to split up your method table. If you look at how Rust does this, for example, they require that like your owned type only appears to the left of other owned types, and that generic types appear to the right. And that's specifically so that the order that you choose to put generic things in front of non-generic things is already chosen for you. And then you can't have this kind of ambiguity conflict. But that people complain about it. So, yeah. Thank you.
Perfect. Thanks, Cordy, again. And our next talk is by Simon about lessons for teaching Julia.
Okay. Can you see all of it? Or is there an edge? Why? Okay, great. Thanks you for having me. I'm Simon Christ. I'm a research software engineer at the Leibniz University of Hanover and the digital science support space Lower Saxony at the Technical University of Braunschweig. And today I want to talk to you about what I call Julia novices, which are lessons for the Carpentries organization for teaching Julia to scientists around the world. So there are two things. I first want to introduce to you the Carpentries organization, and then afterwards I will talk to you about the existing and maybe upcoming Julia lessons. So first of all, the Carpentries. So this is a non-profit organization that organizes so-called Carpentries workshops worldwide. And the goal is to raise technical literacy of scientists to improve and enable reproducible science, in a sense, that people don't rely so much on working with spreadsheets, I guess. So what is the target audience? I think the main focus is, when you have people who are very new to programming, and then you have people who already learn programming in their studies, and then you have people who study computer science. This is the spectrum. Then the carpentry is mostly focused on people who have little to no formal education in computer science during the studies, but then afterwards are expected to use computers to conduct science. And to give them a basis that they can work off on. For that, there's the Carpentries workshop structure, which is usually 2 full days or 4 half days, and then you will have an instructor and a bunch of co-instructors and helpers. And then you work through these Carpentries lessons. So this used to be in place, but then after 2020, it also works online. And sure, in those 2 days, you can't get someone from zero to being a proficient programmer, but you can, he already has stuff installed, and he has run it once, and then he can afterwards build up on that. And I think importantly, he knows, or she knows how to do the stuff, while being led, and also know all the vocabulary that you then afterwards need to look up stuff. So this is a map from their report of where they conduct workshops. So you see this is all around the globe, almost. And so since 2012, they delivered over 4,000 workshops and trained 5,000 instructors and also a bunch of instructor trainers who trained the trainers and conducted a bunch of workshops this way. They run 4 different programs. So one is software carpentry to give basic software engineering skills like working on a command line, doing version control, learning a programming language. And then there's data carpentry, more focused on data science workflows, as well as library carpentries that's more addressing the needs for librarians. And then HPC carpentries is newest, like 1 or 2 years ago, where you can learn the basics about distributed and GPU computing. So on top of this, there's the Carpentries Incubator. So this is essentially a GitHub organization where community can start to develop lessons that are not officially like vetted and battle tested, but they can start coordinating the development of lessons. And then after time has told, they might become incorporated in the official catalog. This contains hundreds of lessons where the official, like each one has like 5 to 10 lessons. Okay, and lessons are not just for the carpentries, they are released under CC license, and you can reuse them outside of the context, and that's also how I use them. I teach a course about Julia and open source software development in the university, and it starts like with this workshop, and then there's multiple weeks where they can work on projects after they gain the basic information. So let me quickly introduce the existing Julia lessons to you. Kind of recently, this is the so-called Julia inflammation lesson there, which is kind of a direct translation of the pre-existing Python and R lessons about inflammation data and how to. So the main goal here is to get them basic programming concepts and then exercises them by visualizing the data set of like inflammation data from patients. This is like one, I had a student like make the transition, and then this is now online, and you can, or the goal is here is to cover the basic data types and programming concepts and how to read data and get the plotting. So it's very basic stuff, but it's what you might get across in like 4 to 8 hours. The longer pre-existing lesson was Julia Novice, which was targeted more at people who already wrote some code but are new to Julia. And my goal was to enable the learners then, after they took the lesson, to understand packages and the structure of Julia code enough that they can then work on open source projects and can download it to a repository, change something, and then hopefully make a contribution there. So this covers a bit more, like the type system and programming languages and packages and interfaces, and also writing tests. And this all on an example of trying to aim a trebuchet. Then there's another lesson, not by me, on efficient computing in Julia. So this targets the more advanced people who already know programming a bunch, and also in Julia, but then they want to know, like, how do I optimize stuff? How do I run distributed computing? How do I program on accelerators? And so this covers the common performance pitfalls and parallelization and GPU computing. So this also covers units and type stability and stuff like this, and there you can work it on simulating solar systems and make game of life. Last but not least, this is an empty repository, which is called Julia Data Workflow, and then there was the idea to have a lesson about data science, more introduction to data science people. And I think Kevin would be very happy if people would like to work on this and then coordinate it. So there's a discussion of how to structure this lesson, but there's not yet the actual lesson. So this is more in the conception phase, and so it's a bit unclear how that goes. So, but part of why I'm showing you all this is that I think having good lessons for the Julia language in this repositories would benefit the community by having like battle-tested teaching materials, like open educational resources that then everyone can benefit from. And all the lessons would benefit from people who pilot the courses and give feedback and try or make PRs or discuss improvements about these lessons. And also what I find that is hard to do and really benefits the courses much is I have good challenges where people can get feedback about where they stand in the learning. Okay, and that was my talk. I'm happy to hear your thoughts, and thank you for listening.
Great, thanks a lot. We have time for a couple of questions, and maybe the next speaker can get ready in the meantime. Over there.
Thanks. Just confirming, I would love for people to work on the data lesson. My question for you was, has there been any interest from the Carpentries folks in making these in-person workshops? I see you used it in your course, but have there been any implementations of the 2 or 4 day workshops, sort of real Carpentry style yet?
What do you mean? Like from the community, I know some people who at least looked at the lessons, and then there was one who actually piloted one of my lessons and then gave feedback, which was very helpful. As far as, it's not the Carpentries who decides I want to run a workshop on this lesson. It's more like organizations ask the Carpentries to run a workshop covering Python or R or another tool. So this is more, I guess, a popularity issue, but it's good to have something in the bank, I guess. And also, at least with the universities I work with, Julia is getting more and more traction. So I think this is maybe becoming more often in the future.
More questions? If not, maybe I have a quick one. So you mentioned university courses. Is this intended as like a full semester course? For example, because I'm from physics, so could you now take this and make this in a undergraduate?
No, as I said, the structure of the lessons is that you are able to teach them in 8 hours. But in my course, it's like a block course. Then people have, let's say, I give them 2 whole days for Julia, and then afterwards they have a longer period of time where they can apply what they learned in a project.
So it's like for a week or something like this?
Well, it's actually 4 weeks, but then they also have to do a presentation and stuff.
Okay. Great. If there are no more questions, let's thank you again, the speaker again.
Thank you.
And then our next talk is by Sam about how Julia is both dynamic and fast.
Just making sure we can see the slides. Okay. So my name is Sam Schweigel, and I work at Julia Hub. I'm a compiler and runtime engineer there. And I'm going to give a short presentation on some of the parts of the design of the Julia language that I find very interesting. So I'll start off with a kind of silly observation, which is that as programmers, we kind of start out, I think, believing this, which is that there are some programming languages which are just fast inherently, and then others that are slow. And then I think at some point, you'll end up updating your belief, and you'll start thinking, well, really, it's language implementations that are fast or slow, and it doesn't make a lot of sense to talk about languages themselves. And then I think an even better approach is to actually think, really, some programming languages admit fast implementations, and others make that rather challenging. And this is why I like to think about the design of Julia, is because I think Julia makes a lot of nice choices that admit a very fast implementation. And so that's kind of the theme of this talk. I'm going to talk about language design and how your language design constrains the implementation of your programming language. And then I'm going to talk about what parts of the implementation of a programming language should inform language design. And in Julia, in particular, I found this very interesting, which is how Julia makes kind of a retreat from very dynamic behavior, like some of its peers in the scientific computing space. And in exchange, we win a lot of performance, and we win being able to implement it much easier. So me, like I said, I work on the Julia compiler now. But prior to joining Julia Hub, I actually didn't really use Julia at all. I came from the more like statically typed world. So a lot of the aspects of Julia were really new to me. And I think Julia broke a lot of my preconceptions about like what a dynamic language could be in terms of performance. So yes, I like compilers. So I'll start off with, what do we want out of a technical computing language? And really, it seems like based on what people actually use, they want loads of expressive power. And in particular, they want macros, and they want multiple dispatch, which is the kind of the lesson of Julia. And they also want interactivity. So in particular, we want to have a REPL, and we want to have eval. And we also don't want to be like fighting with the compiler as we're modifying our program. So we want to be able to run sort of half-finished code that might have, maybe over here, it parses correctly, but there's some weird type errors going on, and a static language would reject it. So of course, I think that means that the perfect programming language that meets these requirements is, of course, Common Lisp. Because Common Lisp has been around for ages, and it actually satisfies all of these constraints if this is what you're looking for. And I don't actually mean to hate on Common Lisp. It's got a lot of really, really nice things going on. But it is a useful comparison because it differs from Julia in some key ways that mean that Julia can implement things in a faster way with a little bit less effort. So, of course, Common Lisp has macros. We've got multiple dispatch, so you don't really need to read this. But here I'm doing an example that I'll run with for the rest of the talk, where I'm defining this shape class, and I've got the circle and rectangle, and they have some fields, as you might expect. I'm going to define a generic function over that called intersect p. The p is just a suffix we use in the Lisp world to mean it's like a predicate. And I've got some methods there for intersecting the different shapes I have. Of course, we also have interactivity. So the asterisk is the REPL prompt in SPCL, which is one implementation of Common Lisp. We can load files. We can call our intersect p after making some instances. And of course, we have eval. So you can also eval code, and code is just a list. So this looks very Julia-like. Now let's do a little example of the performance of SPCL, because SPCL really is a high-performance Lisp implementation. And I'll just make a really long list, so 10,000 random shapes. They're circles and rectangles. And then I'm going to loop over them and just count how many intersect after I've generated them. And so we might try that out. It's like, oh, this is taking a while. And it took 3 seconds, which feels longer than it should. And the really suspicious thing is it looks like it allocated a whole bunch there. So let's find out why it did that. So here's the implementation of one of the methods on intersect p for circle-circle intersection. And you can see we really wouldn't expect it to allocate at all if we were doing this in Julia. You see we are just calling these accessors, circle x, y. We're doing some math, and then we're returning the result of a comparison. And this is my first instinct whenever, as a compiler engineer, whenever something takes like a millisecond too long, the first thing I do is hit it with a disassembler. And like Julia, SPCL has a nice like thing built into the REPL where you can just tell it to disassemble something. And here's like this giant disassembly that I'm not going to read the whole thing. And my suspicion is like whenever I see an implementation that looks like this, and it's like I feel it should be really compact, and then the result is this gigantic mess, that always kind of sets off alarm bells, like I'm suspicious. So let's look at just a few pieces of this that are maybe causing our performance problems. The first is that we notice that calls to stuff like accessors aren't inlined at all. And in fact, it kind of gets worse, which is that we can't, it seems that SBCL is not able to know the type of the return of these accessors. So even though when we created the class, we said that it contained a float, we still have to call into like the Lisp generic minus and plus implementations. And those, for historical reasons, are not actually implemented with multiple dispatch. It's kind of like a thing that just inspects the type of the arguments and does the right thing. So this is weird, because I know that SBCL has the ability to do type inference. It's able to reason about this kind of thing and use an efficient, just a machine instruction when possible. And the reason is ultimately that is this problem. So in Lisp, we have the ability to redefine functions at runtime using eval or in the REPL. And we also have the ability to create new methods on existing classes. So we could, those accessors really are methods, and we could go in and make a new method that returns something that isn't a float. And so SBCL is unable to actually know for sure that the result of calling that method is going to be a float at all. And so here's an example where we've got foo, and then bar is going to call foo once, and then we're going to eval a defun, which will make a brand new version of foo, and then we'll call it again. And we'll just see that between those two calls, it actually changed the implementation of foo. So that means if you imagine in the disassembly for bar, we can't just inline the definition of foo so easily. We'd actually have to look up what the current version of foo is, because you could imagine that eval could be buried somewhere in a call stack. And then we have to call it twice. So I do have a caveat here, which is that I am aware that there are things you can do to improve the performance of the toy example I made. And in particular, in SBCL, you can kind of write promises and say that you know what the type is of something, and you can turn the speed all the way up, and you can turn the safety down. But the problem, of course, is that we want to write kind of the obvious code and get good performance out of it right away. So I was able to improve it a little bit by messing with this kind of thing. And one further thing is there's actually even more power in the common Lisp object system that I haven't talked about. You can redefine classes to add or remove fields. And here's a method you can make a method on this generic function that tells it how to migrate from an old instance of the class to a new instance. So just to give you an idea that CLOS really is more powerful than Julia in many ways. So the question is like, how can we be very dynamic, because we want to be dynamic, but win back more performance? And so the key kind of philosophy behind the Julia programming language is that we can be a little bit less dynamic, but much faster. So what we want to do is we want to abandon the features that have the least amount of power, that we maybe don't use that often. And in exchange, we want to give the compiler information to work with so it can make smart choices. So the core one that has been in Julia for a very long time is this concept called world age that I'll discuss. And world age is necessary if you want to have eval, but you don't want the effects of eval to become visible right away. And so that's what allows the compiler to make assumptions about when I call a generic function. When you use plus in Julia, there's many methods on plus, and of course at runtime with eval you can add more methods to it. But because we say that the effects of eval don't become visible immediately, the compiler is free to optimize inside the function, assuming that it knows all of the methods on plus. So here's the same toy example with foo and bar, where inside bar I'll eval a redefinition of foo, and then I'll call it again. And you can see that the first time I call it in the REPL, I get 1, 1, so the old one was called twice. And then after that, for some reason, we seem to get 2, 2. So what's going on here? So this is the world age mechanism, and you could imagine that there's two versions of foo. There's the original one, foo 1, and there's foo 2. And every time you hit enter in the REPL, the code runs, and then the next thing that you enter will actually run in the world age that has just been created if you've defined some new thing. But within one function, it's going to be running entirely within the world that it started in. And so this is kind of, you can see we have latest world after that first definition, and then we go to the next world, and then the next. And as we progress, certain methods are visible and certain aren't. So after foo2 gets defined because of the eval, you can see that foo1 is no longer visible. And so for all future calls to bar, we're going to get 2, 2. So the reason to have something like world age is because it gives us assumptions in some particular world that the compiler can use. And the way I like to think about it is that inside this world, we can do whatever we want. We can call eval. And then that produces some new set of assumptions that are valid in a new world age. And then because we're in the REPL, we go to the latest world, and we can call bar again. But then that will get compiled with the new assumptions that we have in that world. So that has been in Julia for a very long time because it's super critical to having the performance of multiple dispatch be reasonable enough to use it all over the place. But it turns out, since 1.12, which more people should use, we've extended world age to even more things. So 1.12 extends world age from just the methods that are defined, but also to constants. And that includes struct definitions. So previously, of course, with like revise or anything, you couldn't revise something and add or replace fields on a struct because we just didn't support changing that. Now, if you make a new struct with the same name, it's as if you redefine the constant, which is the struct name, and those are actually two unrelated structs. So if you have some existing instances, we don't do anything. Those just stay as they are, and you get a brand new type that has the same name. And that's a big difference from the common Lisp object system, because in CLOS, when you redefine a class, you can actually migrate the old instances to the new class, and that comes with all kinds of performance problems like we were just discussing. So let's try the same silly example in Julia. We can define intersect p the same way, and we can make our big array of 10,000 shapes and run it, and we get a pretty reasonable improvement in performance. So we get 0.3 seconds, and it doesn't really allocate at all. And so we can see what the compiler did, and I hope you get into the habit of doing this if you're a Julia user, which is we've got these great introspection tools. So code type shows you what type inference and the optimizer did to your program, and it is exactly what we'd expect. You can see all where it gets the field, and it's just inlined everything all the way. It knows it's a float, so it calls directly to the intrinsics. And then, of course, the native code looks equally good. So you can see it just loads the offset from the struct right away and uses the machine instructions for doing floating point arithmetic. Now, this was the first, world age really is the key thing to making multiple dispatch useful. But I have one other feature that I thought was very interesting as a compiler's person that is often not thought about, even though it's as critical, which is, why do we have both these mutable structs and immutable structs in Julia? So again, not to pick on Common Lisp, but Common Lisp, in the name of simplicity, just has, in addition to the Common Lisp object system, there's a def struct thing. But the idea is that everything is kind of mutable by default. And everything has an identity. So if I construct a new instance of a struct, that is a separate thing that has to have a separate identity and a separate, if I check if they're egal, they should not be egal. And so the reason we need this is because if you have an immutable struct, the theme of this talk is that you're giving the compiler more to work with. So in particular, with immutable structs, you give the compiler, sorry, I'm gonna skip over this, even though it's interesting. So this is the final thing I wanted to say, which is that there's many reasons to be dynamic. We want the features that have the maximum power without burning the implementation. We have eval, we have immutable types, which are good, and we also have this thing called opaque closures, which I suggest you look up if you find them interesting. Yes, now we can take questions.
Thanks a lot. We got time for maybe one quick question, and the next speaker could get already ready and come to the front. Someone? And our next speaker is already ready. Maybe I have a quick question because I'm not really familiar with Lisp, which you mentioned it. But what about this interactivity? You're talking a lot about compilation and so on. Is this actually usable compared to Julia?
Sorry, could you repeat the question?
Is it very interactive, Lisp, or can you do something with it still? Because a lot of people mention it. I'm not really an expert, not a computer scientist, but is this something we can try out, or Lisp is actually not that similar to Julia in the way we can do all this interactive fancy coding and so on?
Common Lisp, what I was trying to get at is that Common Lisp has even more interactivity than Julia in some ways.
Okay.
So in Julia, if you eval things at runtime, you have to opt in to seeing the results of the eval. But in Common Lisp, it's even more interactive in the sense that things that get evaled are just immediately apparent. Yeah.
Cool, thanks. Let's thank the speaker again. Thanks. And our next talk is by Julia and Alexandre about Reland and Argos.jl.
Can you hear me? Yes, I think you can. Hello, my name is Julia Dumitru, and together with Alexander Bergel, who is around here somewhere, we worked on developing a new and powerful linter for Julia, and we are here to present you our work. So first of all, why would we care about a linter for Julia? Well, a linter is useful for enforcing coding standards across code bases and for catching errors that can be statically detected early in the development process. It is also useful for avoiding style inconsistency, and I think this is especially relevant now that agents are generating thousands of lines of code very fast. And in general, a linter serves as a guardrail for developers. All right, but why a new linter for Julia? Well, there isn't really a good option right now. The only available viable option used to be static lint, which I think now moved into Julia workspaces. And the linting part, I think, should be extracted in Julia lint. So that is still a work in progress. The entire project is in a transitional state from CST parser, from using CST parser to parse Julia code, which is an ad hoc parser, to using Julia syntax, which is the official compiler frontend. So there might be a bit of a struggle with that as well. But I think the main problem is that writing linting rules is difficult for a regular Julia developer. And the reason for that is because you need to know the internal representation of Julia code, and the regular Julia developer doesn't really know that. So what we are proposing is a fresh start that directly uses Julia syntax and makes writing rules accessible to anyone who knows a bit of Julia code. And that is relint. So relint was initially developed as an alternative to static lint, but was meant to be more expressive, easier to maintain, and lightweight and fast. And one key feature of relint is that it provides a script that makes it easy for relint to run in CI/CD so that you can integrate it with your workflow. And this is the basic infrastructure for a linter, and for writing linting rules, relint relies on Argus, which is a package that offers a domain-specific language for pattern matching and for transforming Julia syntax, and also for writing linting rules. It is highly inspired by Racket, specifically by syntax parse and presyntax. And if you don't know about this, I suggest you look into them because they are very cool. So let's look a bit into how to write linting rules in relint, specifically in Argus. Idiomatically, you would define a rule group, and then you would define your rules within that rule group. Here we are using a declarative approach for defining rules using the define ruling group macro, but you can also use a functional approach using plain Julia functions. We will see an example of that later. So we are defining a very simple rule called async, which searches for all calls to async and suggests that they be replaced with calls to spawn instead. We need to provide a description for our rule and a pattern, which is used for pattern matching on your abstract syntax tree for your source code. So we are looking for calls to async, and we don't care about the arguments of async. Right, so this is cool. We can match all the calls to async, but we cannot match qualified calls. And for that, we will need to improve upon our rule by using an OR pattern so that we can search for either calls to async or for calls to threads.async. So now we can also catch qualified calls. Let's look at a more complex example. Here below, we are defining a rule that suggests to avoid containers with abstract type parameters. And for that, our pattern says that we are looking for a container. This is just a pattern variable called container, which has somewhere among its pattern variables an abstract type. And what this abstract type here is a syntax class that we define just above. Syntax class is a syntax category that groups together syntax objects that are similar in some way that you define. In our case, we are grouping together identifiers. An identifier here is also a syntax class that is built into Argus. So you can see that you can reuse syntax classes within other syntax classes and within patterns. So we are grouping identifiers that have a name that is either one of the built-in names for abstract types, such as any or real, or that starts with abstract. Of course, this doesn't cover all abstract types that you can define, because you can just write a random name for your abstract type. But if you follow Julia style conventions, then this is close enough. This is an even more complex example. We will not go into details for this one, but just to show you that it's possible, here we are defining a rule that enforces that an unsafe function be called only from another unsafe function. And for that, we define an unsafe function called syntax class, and then we use it to define our rule, which says that we are looking for an unsafe function call that is not inside a function definition whose function signature is also an unsafe function call. Again, don't worry too much about it, just to show you that it's possible. This is the basis of defining rules, but you also want to run those rules. Relint comes with a bunch of predefined linting rules, and whenever you run Relint, those rules run and generate reports for your code. Here we are running Relint on a piece of code using runLint on text, and we can see that we have only one report generated. It's more interesting to run Relint on files, and we can do that using runLint, to which we provide a file name. And again, we see the generated reports. And runLint also can take directory names. And what it does is that it runs all the pre-registered rules on all the Julia files that you can find inside that directory. Here we are running Relint on Relint itself, and we are timing the result, and you can see that it takes about 0.6 seconds, but of course that doesn't tell you much because you're not familiar with the Relint code base. So that's why we also ran it on some popular Julia packages, such as Flux, for which it takes 1.3 seconds, Jump, 3.7 seconds, Maki, which is the entire Maki repository, so all the backends and the tests even, and that takes about 22 seconds. So it's not lightning fast, okay? There's a lot of room for improvement. Maybe CodeGlass can help telling us why we have so many allocations and so much GC time. But still, for your regular package, I think this can be fast enough. One very cool feature of Relint is that it allows you to define your own custom rules and rule groups. And you can register those into Relint. And once you do that, when you run Relint, you will automatically get the results of the rules that you customly defined without having to do anything else. So the last report that we see here is coming from the function, from the rule, sorry, the description of the rule that we just previously defined. So I think this is pretty cool. We mentioned CI/CD. Relint offers a couple of pre-commit hooks that are available for checking severe and regular violations. And it also offers a script that makes it easy to run Relint via GitHub Actions, for example, on files modified by a pull request. And the results are then posted as a comment, such as this one. So to wrap up, Relint currently offers 50 predefined rules. It is expressive and flexible, mainly thanks to the abstraction mechanism provided by syntax classes, which can be then reused in patterns. It is also customizable, allowing you to extend it with your own custom rules according to your needs. And it offers a script for simple integration with CI/CD. In the future, we plan to ship Relint as a standalone command line app, like a true linter. We hope to provide better editor integration because the current one is very rudimentary. We also hope to have more introspection power. We could do that, I hope, by integrating Argus more tightly with the Julia compiler and specifically with Julia lowering, which I believe could give us the possibility for macro-aware analysis and even cross-file analysis and other cool things like that. We would also like to allow refactoring suggestions, and we already have a good starting base for that. And of course, we should write more linting rules because, for reference, linters for other programming languages offer a few hundred rules, and we only offer 50, so there's a lot more rules that can be written. Right, so these are all things that we can do by ourselves individually, but we would really like to integrate Relint with the current Julia static analysis ecosystem, and that could mean, for example, joining forces with the Julia Lean development team and focusing our efforts towards one single reference linter for Julia that is well-maintained, that is robust and fast. And one of my goals is to provide a Julia native alternative to general static analysis tools, such as StemGrep, that are highly trusted by security professionals. I think these tools are not a very good option for Julia because they are too general and they don't really know anything about the Julia internal representation. So that they cannot provide true insight, in my opinion. To provide true insight, you need a Julia native tool. And one of my other hopes is to have Argos integrated with an existing language server, such as JetLS or languageserver.jl. The main advantage of that, I think, would be that developers could then extend the set of static analysis rules that these language servers come with their own custom ones that they can write in Julia code that resembles the codes they want to analyze. So that's it. Thank you for your attention, and we are happy to answer any questions you might have.
Thanks. Questions? Over here.
Hi. So I started working with Julia not that long ago. Coming from Python, I find it quite puzzling that there seems to be no common like coding standards like Python's PEP 8. So for example, people tend to do global imports everywhere, so it makes tracing dependencies a nightmare because you need to use LLMs to say, is this a redefined function or is that a built-in operator or is that coming from a package? For this to work properly, surely you need to have a committee that decides what are acceptable Julia practices and then you implement the guidelines. Is that like ongoing?
I don't know. I'm not aware of any effort like that. So yeah, sure, to have a global set of rules, then yes, you would need a committee to agree on those rules. But you can also have your own, each company or organization that uses Julia can have their own internal rules, and I think that's what generally happens for Julia right now.
More questions? If not, let's thank Julia again. Perfect.
Thank you.
And we are coming to our last talk about Julia C from Gabriel, Jeff, and Cody. I don't know who is giving it. Jeff.
All right, I guess are we going to pass? Oh, do we all have mics? Oh,
Gabriel's getting a mic right now.
Great. Usually you give up after that much time trying to get the laptop to work, but we actually pushed through and made it work. Wow. Okay, so hi everyone. This is Gabriel and Cody and me, Jeff. We work at JuliaHub, and over the past couple of years, one of our big focuses has been on one of the most common Julia user requests, which is building binaries for deployment, especially if they can be small binaries. That's particularly what people would want. So I'm going to give an update on the latest functionality we have for that and show a bit of how it works. So we have this package juliac.jl that's sort of the thing you use for this. So what is JuliaC? So that it doesn't have anything to do with the C programming language, so the name might be a bit confusing, but it's basically just the same naming scheme as like GCC, Java C, et cetera, which means Julia compiler. And it's supposed to evoke that it's a similar kind of interface to compiling code. So it started off as a script in the main Julia repo, and now it's gotten it's snowballed, so it's been moved out into a separate package, which is it's one of the new package apps. So you can go into package mode and type app add JuliaC, and then you will have it. And so it's basically a command line interface that exposes some of the functionality of packagecompiler.jl. So there's a lot of overlap with packagecompiler.jl, actually, because for a long time, you have been able to build binary output artifacts using just package compiler. So there's a lot of overlap. It's not a whole lot that's new. But then it also provides an interface for this new Julia-trim option. And so which is the ability to build the so-called trimmed binaries, where we remove everything that you're not going to need. And so that's a feature of the core Julia compiler. But it turns out that it's a little bit primitive. If you just run Julia with --trim yourself, it will just do the bare minimum thing to it will just run the trimming algorithm and then kind of nothing else. But it turns out to get it to work well, you kind of need some more hand-holding and support code. So this package provides that. So yeah, why do we have this? It's basically because many users are used to using a command line interface like this to do their compilation. Yeah, --trim is a little bit bare bones by itself and needs a little bit of help. And also, just building binary artifacts is a bit complicated. You have to deal with system linkers. You might have to do some object file manipulation. There's just a bunch of other steps you kind of have to chain together. So turns out you need some glue code to sort of put the whole thing together. And it's enough that I didn't want to burden the standard Julia compiler with it. So the standard Julia compiler can just worry about spitting out a .o and then let someone else kind of figure out everything else. So sometimes people talk about it as if it's like, oh, Julia has a static compiler now. It's a static compiler for Julia, but that's not really accurate because Julia is already a static compiler for Julia. It's not. We already have the ability to statically compile things. This does not really change that in one way or the other. It's just kind of a convenient workflow. So why don't we compile something right now, just as a fun example? So Ian Butterworth has this really nice processmonitor.jl package. And he now has a JuliaC compiled executable version of it. So we can just build it. So I've got process monitor here, and he provides a build script, which calls JuliaC. And so I'm just going to run the build script. And you'll see it really just takes a couple of seconds. And now I have it spit out this JTOP executable, which is about 4.7, 4.8 megabytes. We can see it is a ELF executable. And if I run it, right away, I get this nice little process monitor. It's very pretty. And so it just comes right up. Another good example is Jacob Quinn's. He did a whole workshop on writing binary compiled HTTP services. So he did that. So he's been a major user of this as well. So he's also been doing a lot of that. So there are more and more examples of this kind of in the wild. So there was a talk on this topic. There was a talk on this topic last year at JuliaCon, and I had this checklist of to-do things. So anytime I have that, I like to check in on the checklist and see how many of these we can cross off. So this was last year, and then this is, as far as I can tell, this is this year. So we've checked off a few more things. Task support is in yellow because Jacob has already implemented it, but we have not merged it yet. But so that hopefully maybe we'll do that on Saturday. I'm hoping. And there's a couple more things to do. But also we actually have done a lot more features that are not even on this list. So we have a whole bunch of new features. Yeah, I don't know why they didn't even make it to this list, but they're quite cool features. So we have this bundling thing, which will automatically bundle the external native dependencies you need. And now it will also be able to go through all of your C calls in your program and remove any native dependencies that you don't actually use. So now the trimming is kind of extended to native libraries as well. And we have this privatized thing, which basically will put a private copy of the Julia runtime with your output artifact. So it can actually use its own Julia, and then you can load it in another process alongside other Julias, or even in Julia itself. And you can call it as if it were just a normal C library, and you don't even have to know that it's using the Julia runtime. So that's kind of neat. And we can also we can do export ABI and Julia lib wrapping, which Tim Holy has been working on to automatically generate header files. And we've also been working on being able to link things statically. So because a lot of people want to get, no, seriously, I just want a single executable with everything in it. Don't give me any .sos, nothing like that. They want complete static linking. So we have some features for that now as well. And yeah, do you want to,
Gabriel?
So I guess talking about bundle specifically a little bit, bundle is probably the least interesting of the features, but it's also probably one of the more important ones. It is basically wrapping some of the package compiler infrastructure that turns out to be very important when you're building an executable or a shared library. Hey, I depend on BLAS or depend on libffftw or insert whatever artifact dependency you have. It's nice if you just pass an option, say, hey, make me a little bundle. It just follows the Unix style of like lib, bin, and et cetera, where you just put everything in the right place. It does the RPath, so the executable knows where to look for the libraries, and it does all that work for you just so that, well, you don't have to do it yourself. So if you say, hey, I built this little library that runs a linear solve and depends on BLAS, BLAS is going to be there whenever you end up executing either your shared library or your executable. Currently, it doesn't do the scan of all the C calls. So if you have a dependency, like, hey, for some reason, you pulled in FFTW and didn't use it because you used, I don't know, dsp.jl, which may have an FFT call somewhere, it gets added without any use. And one of our goals is in the near future for you to be able to inspect the generated native code of your package and say, hey, you actually didn't use any of the FFTW code, so you can probably just throw it away. And same for BLAS, same for GMP, and all the dependencies that Julia currently carries. That will require still some infrastructure in both base and Julia C for it to roll out. So we hope to land most of it in 1.14. And yeah.
I thought you would cover it.
Okay, I can do privatize as well. So privatize is this normal linking, especially on Linux, is basically a flat namespace. So if you have, for example, the same library there twice, Linux will very helpfully not let you load 2 copies of it without going through some hoops, which causes, for example, if you try to load a shared library that's using Julia inside of Julia, things go very wrong very quickly because one of them will disagree with the other, and yeah. So turns out we have to jump through a couple hoops to make sure that this works. We rename all the libraries and associated SO names, and we use some OS-specific features. So on Linux, we have to use GNU's symbol versioning scheme. On Windows, we have to do we have to embed an XML manifest together with your binary. And on Mac, we don't have to do much because the Apple people did a good job with their dynamic loader. But with Privatize, you can now load Julia on Julia, and do Like there's some caveats with signal handlers and other things that doesn't matter right now, but in most cases you can just have a SO that's built in Julia and load it. So quick, we thought about doing a live demo, but it wasn't particularly interesting. So this is what it might look like. You compile a libm-like function that's written in Julia, and you can just call it from Julia as if it were a C library and never know that it was written in Julia. Okay.
Great, yeah. How's our time? Great, thank you. Export ABI relates to what Gabriel was talking, or actually, sorry, this relates to the lib wrapping that we mentioned that Tim Oley's working on. So there are two different ways. One is a little bit more mature right now, but relies heavily on the C ABI. That's Julia lib wrapping. You can ask Trim to basically take a look at all of your exported C callables, all of your exported symbols from your package, and then to export type information about them, so that you can either pipe this to whatever interface generator that you want. Maybe it'll generate a wrapper package as a bridge from your language of choice, whether that's R, Python, something else. It's entirely up to you. I think this has only been developed for Python so far, if I understand correctly. And then you can also use this directly and consume it directly in the dynamic language as well, if you want to, for example, set up effectively a table of function pointers and C types for you to use to perform your calls in Python. And then the other way of doing things, which is hopefully up and coming here in 1.14, is that there's also some amount of support for us to cooperate with runtimes a little bit more directly. So in this example, for example, this convert function is actually calling into the Python C API and asking it to convert from a NumPy array into a Julia array by just copying its data buffer and then taking ownership of it. And then we do an SVD on that using Julia's native functionality. And then because Python keeps track of reference counting, we still have to include that in the native API here a little bit. So you have to mark that you are done with the data before you go ahead and transform it back and return it to Python. But this allows you to, we'll talk in a second about how we get to the rest of this picture, but the idea is essentially that you'll have a single .dll or a single .so, and Python really supports you putting that in the appropriate directory, and then you open up Python and you type import the name of that DLL, and all of a sudden your methods are all there, and you can type dir and ask for the help on each of these, and it feels more like interacting with native Python versus what Julia lib wrapping can do, which is highly customizable, but feels a lot more like interacting with C directly. And then the other half of the story is going to be on the static linking side of the support. So this is another one of the things on the list that is implemented and not yet merged, but will definitely be in there for 1.14. The idea here is that Julia, the way it does C calls, has been problematic for Trim for a long time. Technically, C call has always been defined purely dynamically. And in the 1.13 timeframe, we decided to tweak that definition in a way that was almost invisible to users. We decided that it was going to be dynamic, but only the very last bit of the part where we look up the global in your module to identify your library was going to be dynamic. And that's enough for Trim to get the information it needs to be able to say, oh, you actually have a C call to libblaz trampoline, or to openblaz, or to libmpfr, so for example. And so this allows us to also hook into CodeGen and basically disable a ton of the fancy PLT functionality that Julia uses for its custom C calls. There's a cache built in to the first time you hit a C call dynamically, load that library at runtime. We don't want that behavior. In this case, we want the native linker to run. So whether you're linking statically, like we're showing on the slide here, or you're linking dynamically, you're still linking natively in the sense that you've got a DT needed entry in your binary, and the loader is what's responsible for loading that library when your lib foo gets loaded. So we're kind of handing all that responsibility over to the native linker when that happens. And all we have to do that is rip out our PLT functionality, and we allow you to tell JuliaC specifically, I want to natively link this library and not all of these other libraries that you might be responsible for. And you can ask it to be either statically linked, in which case it will contact Yggdrasil and try to download a static variant of your library if one exists. And be warned, almost none exist right now because these are brand new variants. So far, static libraries in Yggdrasil have only ever been file products, and For this to work, there'll need to be proper static library products. But that's the idea, is that it will go ahead and download the JLL for you, get the appropriate product, and link that directly. And for most libraries that don't diverge between their static and their dynamic library significantly, that should be primarily a drop-in replacement. There are some caveats where if you have manual DL opens and things like this, you can run into problems with static linking. But those caveats aside, the idea is that you can just turn this on. And for BLAS, for example, that's exactly how it works. There are almost no changes required to linear algebra to be able to just statically link open BLAS here. So that's what we're showing here, is that the actual BLAS symbols are showing up in the library. It should be mentioned, by the way, that there are significant changes in open BLAS that I don't know if we've decided how we want to try to upstream these or fork it or carry these as a patch or what, but they make a big difference for trim. The problem with open BLAS right now is that it has a mega dispatch function that holds function pointers to a huge table that you can think of having rows of the architectures and columns of all the different operations you might do in BLAS. And that whole table is pulled in all together. There's no way to trim out any of that the way that BLAS is written today. So we have a change that we're sitting on to make this happen, where you can break that up by operation. So it still groups all of your architectures together. You can see that here on the right with Cooper Lake, Bulldozer, Core 2, et cetera. These are different specialized kernels for different processors. But we at least get the advantage of trimming about 90% of the library here, I think 26 megs in this case, because we don't have to include many operations that you don't need for whatever C call specifically you compiled in. And this is actually just relying on the trim support built into your linker, GC sections, but it requires these patches to open BLAS for it to actually work the way you'd like it to. And then also we need to still, to get all the way to this single library story, the last piece of this puzzle is still going to be getting libjulia and its variants themselves available for static linking. So that's still work to be done. I'm hoping we get that in the 1.14 timeframe.
That's almost done, right?
It still has, we've had several experiments that have demonstrated working.
Yeah.
But I don't know if we've got PRs ready to merge yet.
Yeah, so it's like half done.
It's at least half done. For whatever that counts for. I don't know, Gabriel, do you want to take it?
Yeah, I guess quick thing that's maybe interesting to very few people, but like Julia C, while the expected use of it is as a CLI app, it does have a programmatic interface that it, for example, uses for its own tests, because doing a bunch of shell interpolation to actually execute the CLI is kind of tedious. It also has, at least at Julia Hub, one consumer that just uses the programmatic API, because if you're wrapping Julia C, because hey, I have one function in my package that builds a binary with something, you probably don't want to shell out to Julia C. You want to build your invocation using your program, and it has a kind of interesting idea where you have an image recipe, a link recipe, and a bundle recipe. One is like you get a .o, which is like basically your Julia invocation. You have your link recipe, which tells, hey, link this thing with either a C-shim or some other libraries, and the bundle recipe, which is all the, hey, give me all my artifacts. And if you're writing tests for Julia C, if it works, or if you just want to wrap Julia C, it might be interesting to use the programmatic API over the CLI.
Great, I got you. Do we want to talk about it? Okay. Great, and then I think we can talk about future work that we're excited about here that might land in the 1.14 timeframe, might easily fall out. We'll just have to wait to see. But Jeff already mentioned that task support is on the way. Apparently large portions of it are done, maybe all we need. And then there's also there's quite a few loose threads in the runtime to close up for multi-threading support. Gabriel kind of hinted at this earlier when he mentioned signals, for example. Signals are important not only when users want to interact with them, but the Julia runtime uses them internally. And so it needs to make sure it uses them in a way where, no matter how many Julias I throw into your process space, they all understand how to appropriately distribute the signals between them. So this is another thing that I think I'm pretty confident we're going to land in 1.14, which means that then it'll be experimental for a little while, but at the very least, it's now possible for you to turn on multi-threaded support at that point and to start to see what issues you run into. Another piece of exciting work that I won't talk a lot about here, might come up during the State of Julia later this week, But we're also working on a low latency GC that for folks who are interested in Julia C, partly because it gives you a more responsive application, or because you care about, I don't know, real-time interactivity or those kinds of things, then this GC could potentially be useful for you. Particularly if you have a large heap, the idea here is that your pause time can be much, much lower if you're running in a multi-threaded environment. But we'll talk more about that at another time. But it's an exciting project that's in the works, and it's already showing some promising numbers. And then, Gable, do you want to talk about the non-standard semantics?
Yeah, we're working on code that's compiled with non-standard Julia semantics. Think your AD tools that perform transformations over code. Think about GPU code. GPUs have other issues because we can probably bundle all the GPU code, but what do you do about the driver or like the vendor libraries? That's still a question. You can just, there are solutions to that, like, hey, the system should have those libraries around. If not, then why you're running GPU code?
I think it's worth mentioning that right now we don't have any way to run GPU code from trim, and we're hoping that this would theoretically enable that. Yeah.
And also, there's a couple things we kind of want to make the development of trim or trimmed work nice in a much nicer way. There'll be the talk on JetLS. Is it?
I think Shuhei is giving a talk on ZLS, and I think we also have a talk from Emma on Julia lowering.
Yeah.
Yeah, but yeah, trimming, part and parcel of trimming is compile time error messages. So you're sort of opting into static compiler type of stuff with this. So you will get error messages, and so of course people want them to be as user-friendly as possible. So that's a constant battle.
Exactly. Yeah, I think so. We're hoping for a revamp of those. I don't know how it's going to land, given that Julia lowering is the first requisite in this. But as soon as that is available and ready to go in Julia, I think we're very excited to do a revamp of the errors in trim so that they can stop being just a waterfall of stacked traces. Great. Okay. And the last thing we wanted to mention is that we are aware that cross compilation is an attractive target for folks. It's going to be a long road, partly because it's very challenging for Julia semantics. The way that we define the packages work allows you to execute a lot of code on the host, arbitrary code, during pre-compilation. And if you're particularly feeling ambitious, then your types on your host may not even match your target, which is really, really hard to do. But we're hoping to be able to at least support this in the case that your types align between your host and target, at least, for example, the size of int, whether it's int64 or int32. And then Jeff has been working on a proposal that's open, that is open for comments, and I think probably still has a little ways to go before we exactly know where we want it to land. But it's starting to discuss the idea of how can we define functionality for both the host and the target so that you can do this kind of cross-compilation, when it requires both functionalities to be present. And then I think it's probably too early to say too much, but there's been a lot of WebAssembly chatter going around, and there's a good chance that this is kind of a nice cross-compilation target just because it's not quite as far a leap as pure hardware might be. And it allows us to I think, work out a number of semantic issues early with WebAssembly before we worry about full cross-architecture support. Is there anything else we want to say there?
No, I think that does it. Yeah.
Great. Okay. Thank you.
Perfect. We got some time for questions.
So privatize, in principle, solves one of the Julia lib wrapping problems, which is you can only have one in your Python session right now.
Correct.
Is there a longer-term solution where you have an independent lib that everything links to for the Julia runtime, or is that a bad idea?
No, I would like to do that. Yeah, I'd like to be able to have separately compiled libraries with a shared Julia runtime, but we haven't done that yet. But yeah, it's on the roadmap.
Cool.
Yeah, I think there are two interesting solutions there. One is if you can manage to statically link your entire binary, then these dynamic linker interposition problems just melt away. And then the other one would be, if we can get the runtime. Yeah, absolutely, that's correct. And not only that, but the Julia processes may not cooperate excellently. They might, you're running 2 GCs, for example, so that may not be peak performance.
Yeah, but the Julia runtime is actually only about a couple megabytes, so it's actually not terrible.
Yeah.
So one of the problems with Julia C is, in my experience, that you never quite know what packages will be compatible with it. And some require quite extensive modifications to get them to trim.
Correct.
So my question is, sort of where do you see the ecosystem going? Should there be maybe an indication in the project.toml that tells you whether it is trimmable, or how do you make that development process easier?
Yeah, that's a difficult question. I mean, there definitely will be cases where a package is just not going to become trimmable, like because it's just it's too dynamic. The design of it doesn't lend itself to it. That will happen. So in those cases, people might end up creating alternative, more statically typable variants of those packages for people who want trimming. In other cases, it'll probably be possible to modify packages, keep them mostly in place, but make them more trimmable. So it's gonna be a mix of both.
Yeah, one big challenge there is that even some of the flagship examples for us are cases where some subset of the package is trim compatible enough to be useful, but not the entire package. I think Modeling Toolkit is a great example of this, where we support lots of differential solvers, but not necessarily every single one. And certainly not with every configuration.
So I wanted to ask about, just going back to the last question about, you're saying some packages don't lend themselves to being trimmable. Is it possible when designing a library just to say, this one I expect to be statically compilable, right? I just want to declare it like that. And please tell me if you can't statically specialize everything. Because I imagine that it's probably only, I don't know, what do you think? 1%, 5% that are the, I intentionally am being very dynamic, and maybe quite a few more that are kind of accidentally more dynamic. And if the programmer had been told right up front, you're straying into untrimmable territory, they might have just said, that was a mistake, I'll fix it.
Yes, I mean, the ideal situation would be able to say, tell me if my package supports trimming or not, and I want to fix it until it does. That would be the ideal situation. It's possible sometimes, in some limited cases. Unfortunately, we can't do it in general because we don't have any way to prove, for example, that a package would be trimmable for all possible instantiations of all the type variables. We don't have the capability to do that because if you could do something with an argument that by taking an argument of an arbitrary type, it brings in arbitrary behavior into your code, and which might not be trimmable. So we can't really guarantee that for all t, your code will be trimmable. So that is probably that would be quite difficult. But for more limited cases, we could probably do something like that. Like if you have a package where every function has all concrete argument types, then we could do it. As one example. Sure, you can do it in various ways through your tests, which is how, like for example, people test whether their code is inferable and things like that in their test suites. So you can add tests for that as well. But but there's still a fundamental problem that you don't know if it will be trimmable, for all possible uses of your package.
Yeah, this is a case where I think we suffer a bit for being a traditionally very monomorphizing language. So until we know exactly how it's going to monomorphize, we don't tend to know very much about your code.
Yeah. Oh, there's a delay on it. I wanted to ask, is it feasible maybe in the future that packages compile part of their functionality into binary shards, sort of, so that they fully pull all the dependency code into, sorry, it's really hard with the delay. So that basically you completely bake all the other Julia code into it, so that not with like a package image where it is not possible to load it anymore if any of the dependencies are different, but basically Maki version whatever can compile all its functionality for some shard and then load that in no matter what the dependencies are actually at load time.
Yeah, so could you use it to basically compile something to a binary that freezes everything? And yes, you can use it for that. Right now, it just makes it very inconvenient to use because you pretty much have to interact with it through C-call, as if it were a C library. But if we have the full separate compilation support, then that would be fixed. And if you have Julia library that lends itself to it, you could separately compile it and still hopefully have some more convenient interface. But that's the thing we don't have yet.
Yeah, if you're looking for a tag word, it would be separate compilation.
Okay, I think we're out of time, so let's thank Jeff, Cody, and Gabriel again. Let's thank all the speakers of this session again. I think there's now a 15 minutes break, and then there will be the black hole talk.
Picture.
Oh,
photo.
sorry.
Yeah,
There's
photo
the
is
picture
now.
now.
Yeah,
Actually,
yeah.
where's the picture?
Yeah, photo is now. Yeah.
Ah, so we have to go back basically for the picture. Yes. So. But that might be tough in 15 minutes.
Good evening, everyone, or good afternoon. Please take your seat and let's get ready for the afternoon keynote of the day. Please take your seat and take a deep breath and recover. At least this is air-conned. All right, thank you very much again for coming to the keynote session. Today is my great pleasure to introduce Dr. Paul Tida from the Black Hole Initiative, Harvard University. Paul earned his PhD from the University of Waterloo and the Perimeter Institute in Canada in 2021, and started his postdoc at the Harvard and Smithsonian. I'm a big admirer of Paul's work. I love Bayesian inference. I love HPC. And I can always get excited by the astrophysics stuff. And Paul has been a leader of Julia community, especially in the EHT Julia as a leader, and has been involved in many community events. Without further ado, the stage is yours, Paul.
All right, yeah, thank you. Okay, yeah, so I'm a research associate at the Black Hole Initiative. I call myself a computational astronomer, which means I'm bad at computation and I'm a bad astronomer, but I try to do both to the best of my ability to take pictures of black holes and do a bunch of stuff. So this talk will be a little bit different from, I think, the one this morning. I'm gonna try to have as much energy, but I guess we'll dive right in. So just to bring everyone up to speed, I wanted to start with the simplest thing. What is a black hole? This is more debated than you would think it is, but the basic definition that you always hear in popular science is basically correct, which is that a black hole is a region of space and time where there is so much matter in it that nothing, not even light, can escape. And one of the reasons that black holes have been so popular, I think, in physics, is that they kind of lay bare all of the problems that we have in modern physics. So at the center of a black hole, there's something called a singularity, which is basically where our concept of space and time breaks down, or equivalently, the gravitational force becomes infinite. And this is just a signal that our theories of the universe are breaking. Now, that said, a singularity is not really observable, so I'm not going to talk about it anymore in this talk, and I'm instead going to talk about things that are at least more in principle observable. So specifically, the thing that most people are aware of is every black hole has something called an event horizon. And this is the region in space and time where it's the boundary where light can escape and can't. So light right at the event horizon will take an infinite amount of time to escape to infinity, and stuff inside will never escape. And what this means astrophysically or to a human is that whenever you look at a black hole and you can see down to the horizon, you should expect to see something that, like what you see in this image here, where you have a bunch of material, it looks all distorted and warped. This is actually due to the extreme nature of space-time around these objects. But at the very center, there's this very dark thing, and that is the event horizon. So why do scientists love black holes? Well, it's really kind of paradoxically that they're really, really simple. So the word that some people might have heard is that black holes don't have hair. And what this means is, to put this in perspective, is I'm showing my cats here. Their names are Nikki and Nala. And to describe my cats, I need a ton of information. Things like their color, their size, their height, their weight, their personality, their favorite food. They let me know what their favorite food is quite a bit. And their favorite human, which is me, not my partner. It's me. She can't defend it, so they love me most. On the other hand, black holes effectively have two parameters. There's a third called charge, but we're going to ignore that because it's not important for astrophysics. And these two parameters are the mass, or the size of the black hole, how big it is, and then the other one is its spin, or how fast it's rotating, or what its angular momentum is. And what I mean by this is that if I have two black holes and they have the same mass and the same spin, they're completely indistinguishable. I can't tell anything different about their history, what fell into them, how they formed, or whatever. All of that is gone, and this is, if you're into physics and popular science, this is kind of like at the root of the information paradox, where you lose all track of information that fell into a black hole. And so, but what this means is that while they're all paradoxical, mathematically I can describe them in what I would consider pretty simple equations. You can write it down on a single piece of paper, which means it's simple. And this means that you can do a lot of really interesting analysis with them, and you can do a lot of interesting physics. On top of that, black holes actually have a longer history than you might have thought. They were first hypothesized in 1780 to 1800 by two physicists. I'm going to call them physicists because I'm a physicist. Jean Michel and Pierre-Simon Laplace, where they had basically a thought experiment of if I stuck enough matter into a small enough region such that the escape velocity was higher than the speed of light, you would just see this dark, compact object. They called them dark stars. It wasn't until 1917, with Einstein's theory of gravity, that the modern conception of what a black hole kind of started to arise. And this is almost immediately after Einstein published his theory of general relativity. Carl Schwarzschild wrote down the first solution, exact analytic solution, which is, if you've ever seen the Einstein equations, is a bit of a beast. It's a monster of a PDE. And he just pulled it out, and this solution was actually the black hole solution. But there was a lot of debate for a long time about whether this notion of an event horizon was even physical, even appeared in nature. And I think it was really 1930 and 1940 when Chandrasekhar first demonstrated that things like black holes might be common, and then Oppenheimer showed in the full generality of, and yes, it's that Oppenheimer. This is before he did the A-bomb. This is what he did when he was a physicist. He did this kind of stuff. Oppenheimer showed that in full general relativity, these kind of black hole objects should form, but it wasn't until, I would say, 1960 that Roger Penrose showed that they're just natural in general relativity, that if, regardless of a setup, if you have enough matter in a small enough space, it will form a black hole eventually. And I think this really launched the kind of astrophysics or interesting, more what I would call practical aspects of black holes, where astronomers started to really dig into what these things would look like. Specifically, Jim Bardeen and Jean-Pierre Luminet started calculating what the optical appearance of a black hole would be. And this is actually what Jean-Pierre Luminet in 1973 predicted an image of a black hole would look. In terms of observations, there were a bunch of theories in the 70s and 80s about we think black holes may live at the center of every galaxy. They would explain a lot of weird observations with things called quasars. But I think the most direct evidence in the 90s and 2000s were by two groups, one in Germany and one in the United States, where they watched the orbits of stars around the center of our galaxy known as Sagittarius A star. And that's what's shown in this GIF in the bottom right. And what they found was all of these stars seemed to be orbiting this really dark object. And when they calculated what the mass of this object was from these stars, they found it was over 4 million times the mass of our sun. And basically, the only thing they could come up with without going extremely into exotic physics was it's got to be a supermassive black hole. But, you know, we're astronomers, and seeing is believing, and I don't believe anything unless I can see it with my eyes. So in 2017, a collaboration, which I'm a part of, called the Event Horizon Telescope, pointed a number of radio telescopes at the center of the planet, all at some specific galaxy called Messier 87. This is actually a fun galaxy that's been observed for over a century. And you'll see in the zoom in right here, this little strip of light. That little strip of light is a jet emitted from the central black hole and was seen back in 1918. Apparently there was a discussion whether it was aliens or not at the time. But now we know it's actually a jet from a black hole. And after zooming in for decades and decades, in 2019, the Event Horizon Telescope published the first ever image of a black hole. And this black hole is since become known as M87 star. The star denotes it's the black hole. M87 is the galaxy. It's Messier 87. And a couple years later, we released our second ever image of the black hole Sagittarius A star. This is that black hole at the center of our galaxy. And I think it's a nice little final piece to the decades and decades that we spent looking at the center of our galaxy. One thing that's really interesting, at least to me, you may not think this, but I think it is that these images are remarkably similar. They both show this weird fire donut with some ring-like structure and then some central depression. And the reason why this can be somewhat surprising is these black holes are actually 1,000 times different in size. So M87 is 6.5 billion times the mass of our sun, roughly, and Sagittarius A star is around 4 million times. And so even though these things have a massive scale difference, they look extremely similar. And the reason for this is really because Einstein's theories tend to make very precise predictions, and what we think we're looking at is effectively plasma around this black hole, which is sometimes called an accretion disk, that's emitting light. This light emits to us, and it ends up looking like a fuzzy ring where this dark center is that event horizon I was talking about. However, Gravity is really cool in these scenarios. And you get something called strong lensing, where the strength of gravity is so strong that light can do multiple orbits around the black hole, and what ends up happening is that entire image, that first fluffy ring, gets concentrated into this tiny ring-like structure that's sometimes called a photon ring. And light can orbit more and more and more times, and the more times it orbits, the thinner and the more demagnified this gets. And so basically, we expect every image of the technical term optically thin emission, but I'll drop the technicalities now, is we expect it to look something like this, where we have a fluffy ring, this thin ring on top of it that's called the photon ring, and then at the center, this dark feature, which is the event horizon, or more correctly, an apparent horizon of the black hole. Now, we didn't take something that looked like that. We took something that looked like this, a fuzzy donut, and this is because we're just limited by the resolution. So you might ask, how hard is it to take a picture of a black hole? And at first blush, it actually doesn't sound that hard, because the black hole that we took a picture of in M87 is actually the size of our entire solar system. So in the center here, you can see the distance between the sun and Pluto, and it's just this tiny little part in the middle of this depression. Voyager 1 is just coming out of the depression. So imagine our entire solar system replaced with a black hole. That's huge. So you might think it's actually pretty easy to take a picture of something that big. The problem is that it's 50 million light years away. And so to put this in analogy, it's about 10 to the minus 8 degrees. That doesn't mean a lot. But what this effectively is imagine you're sitting on Earth. There's a soccer game being played on the moon. The amount of resolution we need to take a picture of this black hole is the same as if I was able to track the soccer ball while sitting on Earth. So insane amounts of resolution. My other favorite kind of analogy for this is hold your thumb at arm's length. The angular resolution we require is enough to resolve the individual atoms in your thumb. So absolutely insane amounts of resolution. And effectively, to make this possible, you need a telescope the size of the Earth. I can't build a telescope the size of the Earth for engineering problems, and probably political things taking up the entire sky, while it might be fun for me as an astronomer, would probably piss everyone else off, so I'm not going to do that. So instead, what we rely on is something called very long baseline interferometry. And what this is we put telescopes across the planet. These are a bunch of radio dishes, and then we link them up in a way that we can turn the entire Earth into an effective aperture. And what's shown here is actually the Event Horizon Telescope circa 2022. And you can see we have telescopes across the planet, a couple in Hawaii, a couple in Arizona, one in Mexico, 2 in Chile, 1 in France, 1 in Spain, 1 in the South Pole, and my personal favorite, 1 in Greenland. It's my favorite because I've been there twice. It's pretty fun. It's up in the northern US Air Base there, and it's a pretty fun time. Now, at the core, though, and the reason that I'm excited to give this talk at Julia is really that VLBI and the EHT is really a computational telescope. And you'll see what I mean in a second, but basically everything we do relies on computation. So the first thing is that we have to get all of these telescopes to point at the same object. And then because they're across the planet, we all have to effectively download it to disk. And our data rates are extremely high, 64 gigabits a second, and we're going up to 128 gigabits a second. So this means over a single night of observation, we'll produce a petabyte of data, and multiple petabytes per observation. The data, we can't store the full thing, so we do 2-bit quantization onto special high-speed hard drives. And then, kid you not, the hard drives are so big and so heavy that we can't e-transfer it. We literally physically FedEx the data to a central location. And fun story, we've lost hard drives in the past. Just like FedEx loses your packages, FedEx lost our package one time, and we had a hard drive just disappear. We found it a couple years later. It showed up on eBay, apparently, and someone knew what it was because they saw it, and it's very distinct. I don't think they knew what they had. So after we get there to the central location, we load them into a specialized supercomputer called a correlator. These used to be FPGAs. Nowadays, they're a bunch of CPUs linked together quite quickly. And what we do is, this is where we literally form what I would call the Event Horizon Telescope. So what we do is we grab pairs of telescopes and we do cross-correlation between them. So we do an FFT of the signal, cross-multiply, and an inverse FFT. And the whole point is, these signals that go to each telescope are weakly correlated, and we want to dig out this, this correlation. So what comes out of that is these very weak correlated signals, but it's effectively still basically noise. We're dominated by really annoying things like the instrument. So things like cables will introduce weird noise. You can literally see sometimes in the data where someone kicks a cable because the data becomes unstable and we have to either throw it out or figure out what happened. Lots of stories about the kind of nightmares we have to deal with there. But the whole point of this is in this calibration stage is we isolate these signals that come from instrumental and atmospheric effects and we remove it. And this requires us to effectively do high throughput computing where we're cycling through to tens and hundreds of terabytes as fast as we can, because if we don't do this, we can't actually image anything. At this point, we basically have cleaned up data where we can average more aggressively to build more signal, but we still don't have anything. We have some weird correlated signals, and then we have to try to reconstruct an image out of it. And specifically, what we have to do is infer an image from actually the Fourier transform. So each pair of telescope doesn't take an image. And I kind of lied, it's not really a telescope. What we do is every pair of telescopes measures this correlation between the electric field, and then you can show mathematically that this correlation is just equal to the Fourier a single sample in the Fourier transform of the image. And so every pair of telescopes samples one point in the Fourier domain. And so if you have more telescopes, you get more samples, but you need a ton of telescopes to effectively fill the Earth. And so instead we rely on something called aperture synthesis, where the rotation of the Earth smears out these tracks so we can get more Fourier coverage. And then the name of the game with imaging is inferring what the image is from this extremely sparse Fourier sample. So this is why I would consider the EHT a computational telescope. Recording requires computation. Shipping, okay, not. But EHT recording does, correlation does, calibration does, and imaging does. And if computation isn't used or isn't efficient in any parts of these, we can't make an image of a black hole. So in some sense, software computation is just as important to this as the actual telescopes itself. So the rest of this talk, I'm going to skip the correlation because that's something else, and I'm going to focus more on calibration and imaging because this is where Julia's had its biggest impact. So one of the questions I'm asked is, people know what a Fourier transform is, people know what an FFT is. So the first question people will ask is, hey, you have all these Fourier samples, just throw an inverse FFT on it. And if you do that, it turns out that it just doesn't work. The image looks like absolute crap, it's filled with artifacts, and if you just do the naive thing of doing this, you would need to basically cover the entire Earth with radio telescopes to reconstruct your image. And unfortunately, we can't do that. I don't have infinite money. If I did have infinite money, I might do that, but I don't. So instead, what we have to do is we have to apply inference, or we have to infer what the image is. And the problem with this is that if you have, this is the actual Fourier coverage, or where we sampled in the Fourier domain for the original black hole image, there is no single image that will fit this. There's infinitely many images that will do this. If you're interested in optimization or inverse problems, you would call this ill-posed. If you're a statistician, like I pretend to be sometimes, you would call this likelihood non-identifiable. And so to actually make this problem tractable or finite, we have to end up putting in physics or heuristics to try to solve the image. And how this was traditionally done before the EHT came along was through a kind of heuristic iterative procedure where you would take an initial guess for an image, you would try to correct for residual instrument and calibration effects. Given that guess of an image, then you would update the image. You might go back to, after that updated image, try to correct it again. You might update again. You might do this, blah, blah, blah. And if this sounds wishy-washy, it's because it is. The whole procedure was wishy-washy. And it's because there was a whole bunch of hyperparameters in this that were kind of led to experts. And so you had people on the planet who had done this a lot, who were called clean's the algorithm, artists, where they were just better at imaging. I don't know why. I'm not like that. I'm actually a really bad clean imager. But the really weird thing about this is that two different people would get slightly different images because they pick slightly different parameters. A same person might produce a different image from day to day because they woke up on the other side of the bed, or they didn't get a good night's sleep, or yada, yada, yada. And so what ended up happening is you'd get a single image, and then people would fight for years to decide what was real in the image and what was fake. And so in general, radio astronomy was filled with doubt. This is an example of an image of actually M87, but at a lower frequency, and this is that big jet that I showed earlier, that little streak. And this is a pretty typical image you would see in radio astronomy, where that bright region is where the black hole exists, and you have all these weird features in the image, and people would fight over, is that real or is that real? And I point that little arrow at that little extension in the bottom because there were debates for years and years about whether that was real or fake, because that had something to do with how plasma behaved around the black holes, and so people would just fight for this. And you might ask, okay, this is kind of silly, why would you ever do it like this? Well, the reason is computation. So all of these methods and this whole field was founded in the 70s and 80s, and when basically you had a computer with a megabyte of RAM. So here's a quote from one of the founders of the field, kind of doing a retrospective, and basically they said everyone in radio astronomy had this kind of computer. It had about a megabyte of RAM, and so we wanted to actually analyze the data we took, so we did the best we could with the computation we had at the time. And just because of momentum, these algorithms have stuck through for generations, and even today, they're used for some of the biggest instruments in the world, partially because they're really cheap. But we have modern hardware these days, we have modern languages, so we should be able to do better. And for a long time, the field has known that there are these things called Bayesian methods, where instead of producing a single image, scientifically, a lot of the time, and this is true in astronomy, we want to classify the uncertainty in the measurement we make, because this is how we can claim a discovery. And without an uncertainty, it's vibes. And we try to stick away from vibes as much as we can, although vibes are fun. So the problem with this kind of Bayesian approach is that it is expensive. So in 2017, when I started my PhD at Perimeter, I was working with my supervisor, Avery Broderick, and we tried to develop, myself and several other people, a Bayesian code that would try to do this. It was written in C++ because C++ is fast, they tell us, and it required us to evaluate the forward model millions of times, and we would try to do gradients, although we couldn't for various reasons. And the end result was that it took us about a week with 1,000 cores using one of Canada's clusters, and we had to fit an extremely reduced version of the problem. And on top of that, it became kind of annoying because, I'm an astronomer, I'm not a software engineer, so dealing with C++ all day is rather annoying. So we ended up writing a second version of the code in Python, whose entire job was to just inspect the fits, because it was too slow to be in Python, but we still wanted the interactivity of it. And even beyond that, in C++, we ignored algorithms that we should have been using because there was no package manager, and I was the one in charge of linking everything together. And after you link 5 packages together, you give up because you never want to do it again. So we ended up just dropping a bunch of stuff. And so this is basically a story of, I would consider, astronomy in general, where astronomers really need 3 things in software: performance, interactivity. And I say interactivity because astronomers are visual people. They want to play with the data, they want to load it, they want to look at images. Like honestly, what do astronomers do? We take pictures of the sky and try to figure out what's going on, but we're basically photographers. So asking a photographer to not do photography is pretty weird. So interactivity is pretty important. And then on top of that, we need community. We don't want to write every package ourselves, so we rely on people in the community to write packages like NumPy or SciPy or whatever you're going to use. And I would actually say the bottom 2 are so important in astronomy that people will often disregard performance because they would rather just, I think the great quote from this morning was, get stuff done. They just want to get stuff done. And sometimes the human hours of writing a big C++ code, or Rust these days, because I'm told that's what the kids are into, rather than, they would just rather use something simple. So performance is often an afterthought, much to our danger as I think we move into the future. So what ended up happening was, given this need for performance and wanting to have interactivity in a community, I was left alone because it was COVID, and my supervisor learned a dangerous lesson never to leave me alone, because I went aside and said, I'm going to try to redo everything in Julia. I'd used Julia in the past, and I think I can make it a heck of a lot faster than or at least easier to use than what we had with Themis. And I was getting really frustrated because I was in in the middle of trying to do analysis for the first image of Sagittarius star, and the workflow was a nightmare. So I kicked off, spent a couple days writing up a prototype, and I found that with some minimal effort, I was able to actually get this Julia code to be almost 2 times faster than the C++ code when just evaluating the likelihood or doing the forward pass, and 20 times faster when doing this on a single core on the reverse pass. And this isn't, I want to say, this isn't because Julia is faster than C++. I'm not a fool. That's obviously not true. But I'm also an astronomer, and it was much easier for me because of Julia's interactivity, load up a function, figure out, okay, this is slow, why is this slow? Do code LLVM or code whatever to figure out what was actually getting computed and figure out how to speed it up. And so just a silly PhD student in astronomy could end up beating some C++ code that he had also written, but I think what I learned is I'm a better Julia coder than I am a C++ coder, which is definitely true as I've moved on. And so what's exciting about this is that we could then apply this to the imaging problem, and something that took us a week with 1,000 cores on an extremely reduced problem, we were able to lower it to 30 minutes with 1 core, and I was able to up the parameter complexity pretty aggressively. So instead of fitting an extremely reduced version of the problem, I was able to fit the whole problem, and I was able to move from an HPC cluster to my laptop just because I wasn't having to deal with C++. I could make C++ faster now. Maybe Claude could help a bit with that, but hey, I was a grad student and Claude didn't exist at the time, so things happen. Because of this, Julia and this piece of software, Comrade, has become a key piece of the software stack for the EHT. It's basically been in every one of the major EHT publications. So it was all over the place in the first images of Sagittarius A star. It was used in the follow-up image of M87 that was released in 2024. And a few months ago, as part of a project that I led, it was used extensively. Basically, almost every plot in the paper was made using Julia, and a lot of the analysis was done using Julia. And it explored the evolution of M87 across 3 observations, and we also tracked the evolution of the magnetic field. Magnets are cool. Magnetic fields are really cool, so this spent a long time and ended up pushing us in some pretty interesting theoretical places. If you want to see it, read the papers. I think the thing I'm more proud of, though, is it's made uncertainty-aware radio imaging possible. So this image that I showed earlier on the left, we were able to, exact same data, just using this updated algorithm, we're able to make an enhanced version of the right. It's enhanced because I'm doing things Bayesian inference, and I really care about data fit, so it just tends to improve resolution. And then on top of that, I was able to do statistical significance testing on that little feature in the bottom and show that on a single epoch of observation, it's true. At this point, people had already decided that that counterjet was real, but it was still really nice to demonstrate, at least in a statistically rigorous way, that we can show that with a very small amount of data. I think more generally, this is a project that's been led by one of my coworkers, Jong-Ho Park. He's used this Julia software to analyze multiple black holes at lower frequencies. Each one of these is a distinct black hole. What you're looking at is every black hole tends to produce these jets, or not every, but a lot of black holes produce these jets, and these jets interact with the environment, get twisted around, do these crazy structures, and that's what you're seeing here. So each one of these is actually pointed at us, but what you're seeing is weird projection effects and relativistic effects. And the little ticks you're seeing are tracers for the magnetic field because these are highly magnetized plasmas. I just think they look cool. I am like making pretty pictures, so pretty pictures are fun. And so this is, you make pretty pictures and then we can do science directly on them because we have uncertainty estimates. And you may ask, how is this possible? Well, I mentioned a lot of it is Julia. I could just do interactive stuff. But there's another thing. I was able to work a lot with a couple people who were really close friends at this point, Valentin and Billy Moses. And we used an enzyme, and the enzyme was really I would call it the thing that made everything go burr. It produced efficient AD of scalar code, which was really important. I like writing for loops because my C++ background, and I didn't want to have to stop writing for loops, so enzyme was able to just eat up those for loops. On top of that, it had Julia's extensible package system was critical. This would not have happened without all of the work that all of you do. So I used a ton of packages that I didn't have to write myself, and thanks to package.jl, I didn't have to worry about linking with C++. And of course, interactivity. Mach-E is my favorite plotting library. We use it all the time. And I think in general, what this is that better software can enable better science. That's my major takeaway from doing all of this, and is why I'm really happy to be here at JuliaCon. And moving into the future, the big thing that we want to do is, it's nice making pretty pictures, but at my core, I'm a physicist, and what I really want to model is the system of interest itself. So here is an example of a fluid simulation of a black hole produced by a collaborator, Cora Prather, and this is basically a fluid with magnetic fields on top of it that are orbiting or falling in or accreting into the central black hole. And what we really want to get after is not a picture, but this. We want to be able to model this system, figure out where all the interesting dynamics are, and then model the black hole directly, because there's really important questions about the nature of these objects. The problem with all of this is that it's really hard to go from an image to what's happening at the source. You can learn a lot from an image. The paper, the original EHT publication talked about this, but what we really want to do is take an image and kind of go backwards and figure out what happened actually at the black hole. The problem with this is that it's a bit of a computational nightmare. It's effectively a radiative transfer inverse problem, if people do radiative transfer inverse problems, where we have an emission model of a hot plasma around the black hole. We have to map that to the sky. This is basically an ODE. It's general relativistic ray tracing. So it's ray tracing, but instead of light bouncing off things, there's nothing to bounce off. We just move along the curvature of space-time. Once you get that, you get an image, and then the whole point is that we have to go from that. We have to go from what we infer with the image, or really what the EHT measures, this Fourier transform of the image, and we try to learn what these bulk emission models and the physical map is. This is an extremely hard inverse problem for the specific reason that it's really hard to do a gradient back through it efficiently. It has a bunch of special functions. We had to write custom elliptic functions. My student, Dominic Chang, who's a literal hero and quite a bit better at this than me, figured out a way to do this. And what we found was that by doing this properly, by doing a bulk emission model, this forward map, plugging it into enzyme and churning the crank of Bayesian inference, we're able to dramatically improve the resolution of the first image of the black hole. This is a paper that was submitted to Nature recently and is currently under revision and should be out very soon. But while it's really nice to make a crisper-looking image, the best part about this is that we were actually able to estimate what the three-dimensional geometry of the emitting region around the black hole is. So these are actual draws from a posterior, where what you're seeing is a projection of what we think the emission is doing around the black hole, or different samples from the posterior, and what the resulting image looks like. So while the EHT isn't able to fully constrain where we think the emission is, it is able to give us a nature of where we think things are. And in the future, as the array improves, and as I'll talk about shortly, as we put something in space, we expect this to improve pretty dramatically. And I think the thing that personally I'm proud of, because I'm moving into a faculty position next year, so I'm mostly excited about students these days, is this whole Julia pipeline has been easy enough for students to use. I remember when I got involved in this and I was using C++, it was a bit of a slog, so much so that I ended up being the only PhD student in a group of, I think, 5 that actually had the ability to edit the code. So maybe that's because my code was bad, but who knows? But either way, at the CFA, we've had a whole bunch of students walk through who have used this kind of Julia ecosystem to do their own research, and I just wanted to point out a few here. On top of that, I think the thing that's really exciting, and why I think Julia as a community should be excited about the radio interferometry opportunity, is that data volumes are going to explode extremely soon. So there's more than these, but these are the ones that kind of came to my head. There's three big upgrades and telescopes being built right now. The first one is the ALMA wide sensitivity upgrade. It's going to come online in the early 2030s, and it's going to do effectively 3 gigabytes a second of raw visibility data. This is significantly higher than what the EHT does. SKA in the mid-2030s is going to do 200 gigabytes a second of raw visibility data, and NGVLA in the late 2030s is going to do 300 gigabytes a second of raw visibility data. And we need to turn this around fast, otherwise you're just going to lose track of all of this data, and it's going to be a bit of a nightmare. So one of the things that's been going on in the Julia Astro community is there's this package being developed by James C. McGarry and Paul Barrett called AURUS, or Astronomical Utilities for Radio Interferometry and Simulation, and using a really a really quick, a quick and dirty Julia prototype with the assistance of some AI tools, we were able to turn something that takes in standard VLBI tool sets, a tool called CASA that took about 2 hours. We're able to turn it into something like 90 seconds on a single CPU and less than a minute on multiple CPUs. You know, scaling could be improved here, but in general, what this is that Julia, with a small amount of work, is able to a lot of the time beat these old tools just due to the ease of which it's programming and not having to deal with a lot of baggage. And so I wanted to end this talk with going back to black hole imaging, because that's what I do. And specifically, there was something that happened when we released the first image. I remember as I was sitting in the lobby, and the first question we got from NSF person was, "It's blurry. Did you try to apply Photoshop to sharpen it?" And every person in the room was like, "Oh my God, you don't understand. We spent 2 years trying to do this, and it's so hard. We're not going to throw it into Photoshop." But you know, a part of me understood where they were coming from. It looks like a fire donut. So we want to like make it. You want to see the sprinkles on the donut. So you want to see it kind of sharpen up. And so we can't do this from Earth. We've basically maxed out the size of the Earth. And so what we need to do is something called, we have to put a telescope in space. And I'm the chief data scientist for the Black Hole Explorer. It's a mission that's targeting to launch in 2031, so 5 years, which is scary. And we're actually going to be submitting to the NASA Small Explorers program, actually in the end of the month. So I am here with the support of the PI, but also getting lots of emails from the PI to help write proposal stuff. But the really cool thing is this is going to increase the resolution by the telescope by something like 3 to 5 times, depending on how you do these calculations. And the whole point of it is we want to see that narrow, thin ring around the black hole, because this will let us really learn about the nature of space-time around the black hole and have a better understanding of the emission properties itself and really put Einstein's theories to the test. And so, for instance, with BECS, here's an example simulation. Here's what we would expect to see from the EHT, basically a fire donut that's wobbling around. And with this Comrade Julia package and doing a simulated observation with BECS, we're able to see a much higher resolution image. And in the future, it will look better than this even. But a much higher resolution where we actually are starting to be able to see that thin ring. And after the entire lifetime of the experiment, we expect to take an image that looks like this, where we're no longer going to be seeing this fire donut. We're actually going to be able to see the substructure of the black hole image itself and do the highest resolution images ever in astronomy. And so the problem with this is that we're going to have to scale. So if we say the original image had something like 10 effective degrees of freedom, in the near future, we're going to have to, and for BECS, we're going to have to effectively make black hole images in color. So we're going to do multiple frequencies. So basically, every frequency is a different color. This increases the number of parameters we're going to have to fit by this, and including other effects, 10x, and then the amount of data by 3. We're also going to want to then make movies of this, which means we're going to increase this by a further amount. And then we're going to want to do this in extremely high resolution for BECS. And so we're going to increase the total amount of parameters by 750 times and the data volume conservatively by 100x. And due to NASA and limitations, this has to be finished. We have to go from raw data to an image in less than 1 day. This usually takes us weeks in the EHT. But this is a requirement because NASA wants open science and really strongly prefers open science, and for us to be competitive, we have to get the data out ASAP. And this means that we have to scale up our programming and our computation quite a bit. And so, because I'm the chief data scientist and I'm the one in charge of the pipeline, and because the PI and other people, so the PI, Michael Johnson, and the lead one of the lead project scientists, Peter Gallison, or science director, Peter Gallison, we're working with the Harvard Data Science Initiative and AWS to combine Julia plus Reactant to be able to scale to the levels that we're going to be required for us to meet this NASA goal. And specifically, we've chosen Reactant to do this because I also don't know where we're going to be entirely running this stuff. It's probably going to be some amount of GPUs, but thanks to AI, I don't know how many GPU hours we can get, so there's a chance we'll be running on other accelerators. And the beauty about Reactant is that it's good enough and it's really fast, but it's good enough that we can write the code once and then deploy it on arbitrary backends and hopefully scale up to BECS. And when I say hopefully, I mean we definitely will be able to, because we've basically already shown it. this is a preliminary pipeline result from a couple of months' work with Billy and myself, where we took the original, and a bunch of students, of Billy's students who are, they've done a lot of really great work. And so what this is I didn't have Beck's data because telescope hasn't launched. So what we did was we took another data set from a telescope called ALMA. We looked at a data set that is basically, this is called HL Tau. It's a protoplanetary disk. This is literally, you're watching the formation of the solar system. The gaps in the rings are planets being formed. And the really fun part about this is this model is about 1,000 times more complex. The data volume is about 1,000 times more than what the EHT originally had. And in terms of runtime, thanks to reactant, it's only about 5 times slower than the current the original black hole image that would run in like 30 minutes to an hour. And we're still able to do uncertainty quantification. So I think we have a big check mark here, and there will be a paper in the next few months talking about the Beck's pipeline and how Julia is going to form the basis of it. And so, in summary, why we chose Julia, I think the original thing was they were greedy. I was greedy too. So I wanted performance, and native Julia is fast enough. Native Julia plus reactant is fast enough to meet Beck's needs, and I don't have to dive into a bunch of C++ code. As I've learned, I'm not a very good C++ programmer. I think a lot of this is built upon the GPU compiler ecosystem and reactant and enzyme, and it's made our lives a lot bit easier, and I'm really excited to see those projects continue to grow. I know reactant's grown a lot since we first started using it. On top of that, the interactivity has been critical. I wouldn't be able to use Julia if it wasn't interactive. My students would be like, I'm not doing this. Don't make me use like something like Fortran or C++. So they really enjoy being able to just open up a REPL or open up a notebook like Pluto or Jupyter and just use it. And I am excited about the improvements to compile time. I think the tiered JIT that Gabe talked about sounds great. It would be really nice to have things be a little snappier for the students, especially when they are wanting to pull up a research report and I'm waiting 10 minutes for their whole thing to pre-compile. It would be nice if that didn't happen. And then finally, I think the big reason that's not talked about enough is all of you. This wouldn't have been possible without the community. And Julia's extensibility is great, but it's only extensible if there's enough people using it to develop packages that I can use. And this is really, I don't think that black hole image or any of this would have been possible with all of you. I use all of your packages, whether you know it or not. So I'm really grateful to all of you, and I'm really hopeful that we'll continue to see the community grow in the coming years. All right, thank you.
Thank you very much. It's truly amazing to see the usage of Julia in actually truly groundbreaking works. So we have time for a few quick questions, and they have to be really quick.
Thanks for a very cool talk. So you mentioned that the scale of data is so large that you have to use FedEx to basically collect that. But you also mentioned that you're planning to put new telescopes into the space. And the amount of data is also going to 100x. So how do you actually plan to get this data back to Earth? The FedEx isn't really going there for you.
All right, I can't give too many details because it's considered competition sensitive, but there is specific laser downlink technologies that we're looking into that we think will do it. But that is a fantastic question because we were really worried about it, and we're having to do certain tricks to actually make it possible, and we can't put hard drives on the spacecraft because it makes it too heavy. So you have to basically downlink. It's actually a really fun problem.
Hi.
Hey.
So you mentioned at the beginning black holes are really rather simple things.
Yeah.
Right? Once you know their size. So why are you putting all this work into imaging them? I mean, you know how big it is. Well, you know what's going to happen around.
So it's really hard to figure out how big it is. Even figuring out how big it is what we infer effectively is the size of the material around it, which you can use as a proxy to figure out how big it is. The other major thing that we want to measure is the spin. And I might get into some trouble here, but I would argue there hasn't been a convincing measurement of spin ever in astronomy for one of these supermassive black holes, because it's really hard to disentangle the effects of spinning space-time from astrophysical effects around it. And then finally, on top of that, beyond the black hole, the material around the black hole itself is extremely tenuous plasma that we have a very, very poor understanding of, that has big implications for how accretion works, how jets launch in the system. These jets impact the evolution of the universe. So understanding all of this stuff is actually really, really important. So astrophysically, it's really interesting. You know, whether that's interesting to you is a different question. I can't answer.
I'm wondering if you considered using the moon as a base, and when will that happen?
That is a great question. The moon has been considered as a base. So there's two things we have to be worried about, and I think eventually there will be probably something built on the moon. The problem is the farther you go out into, the farther you separate two telescopes, the farther out into the Fourier domain you're going. So that means the signal you're going after gets smaller and smaller and smaller. And what this means is you have to build a bigger and a bigger and a bigger dish. So to get something like on the moon would be extremely expensive, and it would also be a very slow and kind of weird orbit. So it's actually better for us to go to space and kind of close to the Earth originally, and then longer term, potentially put something on the moon.
All right, last question.
Yeah, thank you for the amazing talk. I was wondering of the fiery donut, like the lobes that you see, is this part of the signal or is this noise? And would you expect like a perfect donut? And if it's part of the signal, what can you learn of it?
So, okay. I would have said originally the kind of blobbiness here might not have been super physical and might have been an artifact of the coverage or whatever. As we've gone on more and we've done more of these Bayesian analyses, I am convinced that we have this southwestern region and then this little knot to the side. And actually, we learned a lot immediately from this. Because it's bright on the bottom, and this is funny, the reason I chuckle inside is because my supervisor, without any qualification, just ended his talk at the NSF thing with just, it's bright on the bottom, and everyone's like, cool, I don't know what this means. But what it effectively is that matter that's moving close to the speed of light has extreme Doppler boosting. And so stuff that's coming towards you will seem brighter than stuff that's going away from you. And what this tells us is effectively the azimuthal direction of the rotation of the material around the black hole. And I don't know if you're a physicist, if you know right-hand rule. If you ever did right-hand rule back in the day, point down and do this. And because it's bright on the bottom, you know the direction of the rotation is away from you. And so that's what this tells us, this bright on the bottom thing. And there's specific things we can talk about in terms of accretion geometry there, but the basic reason is it's moving towards you, and then the stuff on the top is moving away from you.
All right, I'm sorry for cutting the Q&A short. And Paul will stay with us until Friday, and there will be plenty of opportunities to ask and discuss more. And I'm also very sorry for rushing you guys back and forth for the photos. But the plus side is once you get your photo, we all have this beautiful red hue on the face, and you all look prettier than the fuzzy donut. Thank you so much. Let's thank Paul again.